Hi, it's time for another math easy solution. Today I'm going to go over a pretty interesting topic, and that's going to be on spherical harmonics and a whole lot of other stuff related to it. It's going to be quite epic. Alright, before I go further, note if you don't have time to watch this whole video, you could, in this case, just play it at faster speed. Top secret life hack, your brain gets used to faster speed. Here's a link to my tutorial. And also you could download and read the notes. It'll be in PDF format as well as on the Hive blockchain and article format. And you could also watch the video in parts. Timestamps will be, timestamps of all the parts will be in the description, as well as links of everything else, as well as a video sections playlist. After the video, I'll be making short clips of the whole video, so gonna be pretty epic. All right, so let's jump right in. So topics to cover. So we'll go over introduction to spherical harmonics, look at atomic orbitals and magnetic fields, and then I'm gonna go over a mathematical review. And then basically go over the Laplace operator and polar coordinates, Laplace operator and spherical coordinates, derive these equations, and then look at the solid spherical harmonics, solutions to Laplace equation and spherical coordinates, and then discuss the associated Legendre equation, or I mean it's a Legendre equation, something like that. And then go over spherical harmonics, solution to the angular Laplacian, and then deriving the real spherical harmonics, and then graphing spherical harmonics in Desmos calculator. Or more specifically, graphing real spherical harmonics in Desmos calculator. Alright, so let's continue further. So, introduction to spherical harmonics. Yes, I'll be going over the introduction and overview of the equations that are derived, and then go over basically atomic orbitals and magnetic fields. And those are basically the driving force behind why I am covering spherical harmonics now. Alright, so spherical harmonics are special functions defined on the surface of a sphere and have many applications in physics. And from Wikipedia, spherical harmonics originate from solving Laplace's equation in the spherical domain, in spherical domains. And functions that are solutions to Laplace's equation are called harmonics. And we'll discuss that in a bit. So the Laplace equation in rectangular coordinates, or in other words, x, y, z, the typical ones here's rectangular coordinates, x, y, z. Those ones, the Laplace equation is shown below. So here's the Laplace equation. It's basically the acceleration, or the this is the second partial derivative of u. Basically, it's a derivative of u, in this case, whatever the function is. Typically, I use f, but in this case, using u. So this is a function u of x, y, z, etc. And this is a point p on there. But anyways, so the derivative with respect of the function with respect to x only, so everything else constant, we're just looking at the rate of change of this one. And this is a second derivative. So in other words, this essentially what it's saying is that it's the rate change of x on its own, on y on its own, and z on its own, basically acceleration on each axis. While everything else is fixed. For a function in 3D space. So, and we'll go over that when we do the mathematical review. So, anyways, this is the second partial derivative of u in terms of x, plus the second partial derivative of u in terms of y, and then plus the second partial derivative of u in terms of z, and then this equals to 0. And note that the above equation describes steady state conditions, no sources or sinks, i.e. where things are in quote harmony, hence the solutions are called harmonic functions. Basically the acceleration on each axis is going to equal, when you sum all up, it's going to equal 0, so there's no net change in that respect. Alright, so this is Laplace equations in rectangular coordinates. So now the above equation can be rewritten to obtain the Laplace equation in spherical coordinates, and then uses r, which is the distance from the origin, like that, or the radius. And then you have theta, which is here. This is the polar angle, and you have phi. This is the angle about like that, but the z-axis, I think that's called azimuthal angle, or azimuthal angle. So this is the physics convention, like that. Spherical coordinates are theta and phi as commonly used, radial distance, slant distance to the origin, polar angle theta, angle with respect to positive polar axis, and azimuthal angle phi, angle of rotation from the initial meridian plane. And that meridian plane this is what it's referring to. That's the initial one there, and then you're just rotating it about this phi there. All right. Yeah, I'm pretty sure that is. Anyways, so going further, so this is, yeah, this one here is in rectangular coordinates. That's the Laplace equation. And now if you convert the rectangular ones to spherical, you get this giant equation, which is 1 divided by r squared. And then you have partial derivative in terms with respect to r of r squared and multiplied by partial derivative of f in terms of r. And then this one here, and then plus 1 divided by r squared sine theta, and then now you have the partial derivative in terms of theta of sine theta times partial derivative of f in terms of theta. So there's a partial derivative of theta of this whole term, then you have to do it of this one inside. So again, a lot of partial derivatives. Plus 1 divided by r squared times sine squared theta. And so 1 divided by r squared sine squared theta times by the second partial derivative in terms of phi of f, or function f. In this case, we had u, this one's f, it's just convention. U or f is typically used. So anyways, so now solving the above equation using separation of variables obtains the solid spherical harmonic. So if you solve this by assuming that you have the function f equals this right here, f is a function of r, theta, and phi, and then you could you assume that you could separate them to have 3 different equations that are independent of the others multiplied by each other. So basically, basically it's functions of this like that. Yeah, so that they're independent of each other. So assume that you could do the function like that. What you end up having is this setup here, f of r theta phi equals this one right here. This is the e. This one is the r function. And now this one is pnm cosine theta, where pnm is, we'll get to that in a bit, that is the associated Legendre function. Yeah, that's beyond the scope of this video, but I'll be going over that in a future one, deriving it. So anyways, so we're n right here. So we have n. These terms are n is 0, 1, 2, 3, 4. It could be 0, 1, 2, 3, etc. It's a non-negative integer. And m is equal to negative n plus 1, but dot all the way to n, like that. That is what m is, and it's also an integer as well. And then we have p and m, or p subscript n, and then superscript. There should be a subscript. How do we do this? I think it's like this. Yeah, well, minus. Whoops. All right, I just paused the video and just add the superscript, or the subscript there first, and then the superscript on top there. Yeah, so p and m like that. I'm not sure if we could put them stacked on top of each other. That'll be for another day. But anyways, so p and m is the of t. So now here where t is equal to cosine theta. So this one I set t equals to that, just so we have this part there. So the formula here. So anyway, so we're p n mt is the associated Legendre function with t is equal to cosine theta. So in other words, t is going to be an element of all real numbers between -1 and 1. So basically that's the closed interval. And that's because cosine is like this. So yeah, remember cosine is going to be a maximum 1, minimum -1. So t is in between there. And now here is the associated Legendre function, and I will not be deriving this in this video, but I probably will be doing it in another video. But anyways, that becomes this. So Pn m of t is equal to -m to the power of m times it by 1 minus t squared to the power of m divided by 2, and then times it by the mth derivative in terms of t of the Pn of t, where Pn of t is the ordinary Legendre polynomials, polynomials, and this is using the Rodriguez formula, and again this will be for another video, and where basically this thingy is this, where that equals to Pn of t is equal to 1 divided by 2n, 2n squared. 1 divided by 2 to the power of n times n factorial times d. This is going to be the nth derivative in terms of t of t squared minus 1 to the power of n. All right. All right, guys. This is absolutely ridiculous. This is quite amazing, though. So basically compacted together, the associated Legendre function equals to here, or compact together. I basically put this inside here, and now we throw this all in here, and then we get this. We get this giant formula: Pn m of t is equal to -1 to the power of m times by 1 divided by 2 to the power of n, n divided by n factorial, times by 1 minus t squared to the power of m divided by 2, and then take the nth into the n plus mth derivative of t squared minus 1 to the power of n. And this is in terms of t. All right. Fascinating stuff. So again, basically throw this entire thing inside here. Yeah, so that one there. And then t, replace t with cosine theta. So this replace t with cosine theta, and then throw this all inside to the other part. It's fascinating stuff. So anyways, so the general solutions to the Laplace equation are called solid spherical harmonics, as they contain both the radial term r and angular terms theta and phi. So in other words, solving this full thingy, you're going to get the terms of r, and it's the solid spherical harmonics, and you have the angular ones. Here's the angle ones, and then you also have the length r, it can vary and so on. So it's not just on a sphere, you can have a varying, multiplying by this varying r value. All right. So if we instead remove the radial term so that we obtain only the angular terms, then such solutions are termed spherical harmonics. Now this is solid spherical. Now here's a spherical one, which is what we're interested in for this case. So we have, this is going to be this symbol right here. You could also use this right here, this triangle. This is called a nabla or something like that. This is the, where this nabla squared, or this upside down triangle squared, is the Laplace operator or Laplacian. Like that, and I'll be discussing that later. But basically, if you have a function like this, the Laplacian is equal to this in spherical coordinates, and then you set it to equal to 0. That's the Laplace equation. So we have, this is the full thingy here. This was here. Yeah, this is just this part here, but then this whole thing equals to delta f. That's a Laplacian, or you can do the other one like that. F equals that. All right, just put that in there. Anyways, so that is that. So multiplying, so here's the way to get rid of it is you will multiply r on both sides. I'm just doing this just to a high level, and then I'll derive this later in this video. But I want to do a high level just to wrap your head around what in the world do people refer to when they say spherical harmonics. Because even though this is the solid spherical harmonics right here, but typically it's graphed without this right here for just pure spherical harmonics. All right, anyway, so multiplying r on both sides, so then if you multiply r on both sides, this cancels, whoops. Yeah, if you multiply by r squared on both sides, this cancels, this all cancels. And then multiply by 0, it's just still 0. So you get rid of all that, and you end up with this right here. So partial derivative of r, of this function in terms of r squared, and then this is partial f partial r. Plus 1 divided by sine theta times by partial derivative of this thingy in terms of theta, sine theta, and then partial derivative of f divided by, basically partial derivative of f in terms of theta. And then plus 1 divided by sine squared theta equals this, and then multiplied by the second partial derivative of f in terms of phi. All right, so we have that, and then that whole thing equals to 0. So in other words, this, and you can also put it using this thing here called the angular Laplacian. So get rid of that and put that this right here. So you can just write it as this. So partial derivative of this function in terms of r squared times by partial derivative of f in terms of r plus the angular Laplacian of f equals 0. So where this symbol is the angular Laplacian or Laplace Beltrami operator on the sphere, all right, and that equals to this thingy, which we just did right here. All right, so we have that. So now rewriting f. So basically, the next steps in the derivation, you will rewrite f. So this is the original one we had. R is in terms of the separated variables. R of r, p of theta, e of phi. This equals to r, capital R of r, times it by. Now we're going to define these two terms to get the angular parts only as y. So y of theta phi. So where y of theta phi is equal to p of theta times e of phi. So there it is. And now when you solve this, so solving y, we obtain the spherical, complex spherical harmonics. I'll put harmonics. So now if you solve this, this giant formula, I'm just doing a high level overview. Okay, you solve this right here by using separating variables, but for y like this, what you would end up having is, we have y n m of theta phi equals to n times it by p n m, that's the associated Legendre function of cosine theta, times by e to the im phi. So that's still including the r one because we have this r there. So we have that phi. Actually, no, we don't have that actually. This is the y one. No, that's separated. I mean, this one you solve for this part specifically. We're ignoring this one here. That is, yeah, we're just caring about the y one right here. And then this equals to this em phi, like that. That's the phi term. This is the theta term. Yeah, and this capital N is a normalization constant, usually equals to this giant thingy, n equals to -1 to the power of m times by square root 2n plus 1 times divided by 4 pi times by n minus 1 factor n minus m factorial divided by n plus m factorial. And the reason they have this giant normalization constant is so that to ensure that this following integral right here used in quantum mechanics for probability is equal to 1. And that's this right here. So integral from theta is equal to 0 up to pi of this right here of the ynm of the spherical harmonic of theta and phi squared times it by sine theta this is d theta, then d phi, where this integral from phi to 2 pi. So it's a double integral, and that'll be again for another topic there. But then that's whole thing is just to ensure that this equals to 1, because in quantum mechanics they use it for probability. So you need to have this normalized so that the total probability is equal to 1 when you sum up everything. Again, integral is a sum of pretty much every single thing there. So they kind of use that whole spherical harmonics, the equations on the sphere, as and then normalize it to 1, so that they can use it as a probability distribution for atomic orbitals and electron shells, as I will discuss soon. And this normalization setup here is also written like this. So integral from just the integral of this spherical harmonic squared, basically the absolute value. You just take that squared, and of this d omega equals to 1, where d omega is equal to sine theta d theta d phi. So yeah, that's something for a future possible video to just see how they get these exact terms. Anyways, the real sphere. So now this is the complex one, and the reason it's complex, it's called complex, is because you're gonna have this right here. There's an I there. There's an imaginary number there, but typically the ones that you graph in, like when you use a different calculator, just any calculator, they don't graph complex. It's not easy to graph, or just doesn't appear as well. So basically the real ones, so the real spherical harmonics are, I'll put this in bold, so keep that in mind. So the real spherical harmonics are defined such that the functions are real valued everywhere with no complex term I. The usual definition is given below and is almost always used when displaying spherical harmonics visually, since they exclude the complex phase factor e to the im phi, which is rotating about the z-axis. Remember, this is the azimuthal angle there, this phi. So basically you're going to have a rotation set up there, this right here, a rotation there, and that's for the complex. But for the real one, is ignore that. So we basically get like a scalar value, I assume, and you can actually visually see it. It makes sense when you graph it. So anyways, so this is how it looks like. So it was defined. I'm not going to go over exactly how they get this, but I want to emphasize this is what they do. But actually, I may or may not cover this in later in this video because I haven't fully written up the notes at the end. I'll be going that as I film this video and see what I come across. Because again, this is a lot of I cannot imagine how much just complexity they have in this spherical harmonics. Anyways, so the spherical harmonic, the real one is ynm of theta and phi is equal to. So if m is greater than 0, you have this setup: -1 to the power of m divided by 2 squared times by ynm plus, and then you have this -1 to the power of m times yn of and now you have a negative m. So yeah, they do this so that you get, there's a negative term there, so that's interesting. So they kind of throw that back in there, and again, this is the positive negative one, and it's just so it somehow cancels out all the complex terms. And now if m equals 0, you just replace m, just put that in there. So it's just y and m equals 0. And then if m is less than 0, you're going to have this setup: -1, m plus 1, and then now you have the I there because you're going to be able to cancel later in this setup here. So these ones I cancels within. This one cancels. It gets one I term that cancels here. So I divided by I is I times 2. Square root 2, and then you have y n, and then now m is absolute value minus minus -1 power of absolute value of m, times it by yn of negative absolute value of m. So again, fascinating stuff there. Yeah, I may cover this near the end of the video just to see what happens. Anyways, plugging in all the values into the above equation obtains the simplified form below, in which the proportionality. Yeah, the proportional symbol or the proportionality symbol, this right here, is used just to show the functional shape rather than the normalization constant. So then basically once you plug this in and basically simplify this, so you have this y and m, and you know what y and m is. That is this p and m there, and that's the Legendre, the associated Legendre function. So throw that all in there and simplify, you get this setup. So it's proportional to this, excluding the proportionality constant, n. So we got m is greater than 0. You'll have p and m is absolute value of m, and then cosine theta, and then cosine times it by cosine m phi. And then the second part of m equals 0, just plug in the 0 here for the associated Legendre function. And then if m is less than 0, it just equals to the pn. And then absolute value of m, you plug that into associated Legendre function, cosine theta, sine, and then absolute value of m, and then phi. Or you could write this down like this. You could take out this. You could just factor this out, and then don't even need to worry about the m equals to 0 part, and only worry about when it's greater than or equal to 0. So just throw that in, just remove it from there. So you have this cosine now, m phi, sine absolute value of m phi. That's for the last one. And then the complete, and now here is the full ones. So the complete, correctly normalized real spherical harmonics, I'll put harmonics, would be something like below, looks something like this. So y and m real of theta phi equals to n. This is the normalization constant nm, and then you just put all these ones are just this stuff. That's just this. And now you just put the n multiplied by all this in there. Yeah, so it's fascinating stuff. So where the exact value of the normalization constant is usually something like this. And I got this from actually Grok, because it was surprisingly well, and you can also make the formulas as you wish, and so on. So capital N of lowercase n and m equals to square root n plus 1 divided by 2 pi, and then n minus absolute value of m factorial, and then n plus absolute value of m factorial, times it by this setup right here. This is going to be times by square root 2 if m is not equal to 0, and then times it by 1 is if m equals to 0. So that's fascinating stuff. Again, that's for normalization, so that that giant integral is equal to 1, or just not giant integral, just the integral of over the full sphere is equal to 1. And that's the thing I want to illustrate here as well. So this is from phi. They have this angle from theta to pi. That's a polar angle. So you have from here to here. This is going to be actually no, it's over the whole thing. That's 80. That is from there to there. That's going to be 180 degrees, or pi. And then this one is from a full 360. So you can go full 360. This is going to be 2 pi. Like that. So they just basically have it on one quadrant, and assume you could do it on the flip side. So basically, it goes from 0 to pi. So this, remember this angle? So it goes to 0. If this is the beginning, 0 to pi, and then this one goes for 2 pi, full 360. That's interesting. And you sum that up, that equals to 1. That's on the top part. What about the bottom? Okay. That's an interesting little nugget there. All right, so we have this setup here. Yeah, just teleport over here. So thus, the full general solution to Laplace's equation in spherical coordinates is a sum or series over all possible n and m. So because different values that solve it. So again, this is a bit beyond. This will be like this, and then this is what the calculators and all that use. So basically, the function of the full general solution to the Laplace equation equals to f of r theta. Of r theta and phi is equal to the full series, or the basic summation from n equals 0 to infinity, and there's a double integral, and then there's also have from m equals to negative n up to n, Now you have, these are constants, a and m, and b and m are constants, and then you times by Rn, and this is remember, this is the function r of r. Before we had the C1, if you go back to the setup here, going back all the way and over here, yeah, this is basically this one here. Instead of C3 and C4, they just used a and m, b and m. Those are just constants. And that is the radial term. So that's the radial term. So this is the full giant equation there. So this is the radial term. That's just r of r, like this. I'm just using a and m, b and m, just for this case. And then this is going to be, and then times by the spherical harmonic part, the y and m of theta and phi. This is the angular term. This is the radial term. Then you would sum up all of them. This is a sum over all possible n and m. So that's the full solution, where a subscript nm and b and m are constants determined by boundary conditions, e.g. values of f on a sphere or at infinity. So that's some interesting stuff. Again, that's a bit beyond for today's for today's topic. I'm gonna write this right here. This is gonna be visualizations. I'll put it like this: visualizations of real spherical harmonics. So we went over all that. I'll just put this image, this heading. So visualizations of the first real spherical harmonics are shown below. So it looks something like this. Here's the first setup, and you have this one, different values there, and then this is an animation. So real Laplace spherical harmonics for top to bottom, left to right, and you can see the animation. Let's click this animation, see what happens. Animation should show it changing. It's easier to view, and let's see what's happening. All right, there it is. Yeah, so it's moving and so on. Okay, let's make it bigger. Yes, it's rotating, so you have some darker spots and so on. And so again, it's on the sphere. Those are the answers on the sphere. You have positive, negative values, the magnitude. So on here's the one that just everything is just the same value everywhere. That's interesting. Alrighty, so I'll close this and I'll go here. Alright, so note that the spherical harmonics can be visualized by distorting the sphere radially proportional to the magnitude of the values on the sphere. So if you take a value right here, let's say this is this would be, let's say, small. Let's say this is a high value right here. If it's a high value, you can distort it by making it go up, and this one would be 0, or it would go down. Then any parts will go up. So you can visualize it in 3D by having it proportional to the magnitude. So note that the spherical harmonics can be visualized by distorting the sphere radially proportional to the magnitude of the values on the sphere, thus obtaining the familiar lobes. Again, this is the whole point of this video, was for me to wrap my head around why there's lobes. So alternative picture for the real spherical harmonics. So these ones right here, that's a spherical harmonics, the real one. You can also view them instead of like this setup, you can view them like this. So this actually looks like that. That's interesting. So it's actually like, these are high value there. So in other words, this is like low, this is high value, and then this part here is low on the negative side. So it looks like this. So there's a positive, negative. So that's the orbitals there. And note that most the Wikipedia uses L. I use N just because I'm not writing L when I derive everything. It's just and they use an L like that. I'm not writing like that. All right. Right here, note that so right here, so we have these familiar setups here, and you get more complexity, different values of N and M, or L right here. So you have different values of L. There's L right here, or N, and then you have M like this. So you can go down 1, 2, 3, and then you can go extend out negative, positive, and you get these ridiculous setups there. So you get different values all in the sphere, and it's all perfectly harmonic. All right. And now here's a figure right here. Blue portions represent regions where the function is positive. That's blue. And then yellow for when it is negative. The distance of the surface from the origin indicates the absolute value of YLM of, again, L or N. I use N for mine. So theta, phi, in angular direction, theta and phi. So this is the absolute value of them, distance from the origin. So these are all distances. So at the sphere, this magnitude of that value is bigger than elsewhere. And now you have this flip side. This is going to be blue is positive, and now you have yellow for negative. So it goes negative there. So again, this is pretty amazing. Again, it looks like atomic orbitals. So in here is this an Instagram post that shows some pretty interesting setup right here. Yeah, this post right here. So spherical harmonics, Y, L, M. Again, they all use L. I just use N. Just because the first video I saw, the derivation used M. I mean used N. So Y, L, M of theta phi is equal to, this is E, I, M. This is the phi component. Yeah, but then they have it why is the phi coming from the top bottom? I don't know why they have it like that. Again, they use a different definition than the one I was using. And then this is cosine theta. So they're using it from like this. That's an interesting setup there. But why would they use it like that? Anyways, I don't know why they're using like that. Anyways, a spherical Laplacian. It's the solution to this thingy right here, and we'll go over that later. And that actually it stems from this part right here. Actually, it stems, and I will go over that in the definition. It stems from when we have this part right here. So we had this part right here, and then you could set both of these to different constants and so on, and then you get a spherical Laplacian setup there. And we'll get to that later. But anyways, I wanted to show this Instagram one just because it has some pretty cool stuff here. So again, here's some cool photos. This is on a sphere like this. This one has diagrams like that. But then now it distorts it. Now it distorts the edges on this one. This one I think looks like it's just a bit of distortion. That's interesting. But anyways, that's pretty cool stuff. And they use a different convention, but I don't know why they use different cosine theta. It's still using cosine theta, but it's not the polar angle anymore. That's point P. Anyways, that was just a random Instagram post. Not sure how accurate it is, but it looks accurate. But anyways, continue further. So now let's look at atomic orbitals. And yeah, the atomic orbitals are pretty much the driving force behind why I'm covering this. One of the driving forces. There's also magnetic fields, and also when dealing with basically alternative angle of physics instead of quantum mechanics, deal with the Einstein-Dinius ether theory, which I think it's pretty next level. Anyways, so interestingly, spherical harmonics resemble atomic orbitals, which describe the location and wave-like behavior of an electron in an atom, where L is often used instead of N, as I do in this video. Note that note that atomic orbitals are not simply radial distortions, as in pure spherical harmonics. So these ones are radial distortions right here, which is basically the magnitude on the sphere. They would just make the lobe go out. So make the lobe go out. And so they're not proportional to the magnitude of. So they're radially, they're not actually radial distortions. But they actually contain the radial term in the solution. So the atomic orbitals actually contain this part right here, basically. They actually contain the, I mean, not just that, but not just this part. They actually contain the R part. They actually contain this radial term. So they actually have so it's a solid spherical harmonic. That's how you would model them or approximate them and so on. So atomic orbitals are solutions to the Schrödinger equation, which is shown for the electron in a hydrogen atom, and its solution is below, as well as its solution. I'll put this as well as its solution below. Yeah, so here is the Schrödinger equation. Basically, it's this is E, and this is this symbol is capital Phi, I think. No, this is actually psi. It's like the trident one here. So it's actually psi, not phi. So that's psi, like that. So E psi equals to negative, and then you got this is the reduced Planck's constant h bar squared divided by 2, and this is mu, and so on. This is going to be, now we have the Laplacian operator of psi minus q squared divided by 4 pi e naught, or epsilon naught r, times it by the psi. And again, what that is, I'm just going to read the Wikipedia one. I'm not going to cover too much of it, just to get the picture of it. So here, psi x of t is a wave function, a function that assigns a complex number to each point x at each time t, and h is the reduced Planck constant, which has units of action or energy multiplied by time. And then where q, I'm going to make this bigger, q is the electron charge, r is the position of the electron relative to the nucleus, and then r is equal to this right here, r. This is the absolute value of the r vector. It's the magnitude of the relative position. The potential term is due to the Coulomb interaction, where this is epsilon naught is a permittivity of free space, and mu is equal to mq times mp divided by mq plus mp is a two-body reduced mass of the hydrogen nucleus, just a proton, so this is a p, and then of mass mp, and the electron of mass mq. The negative sign arises in the potential term since the proton and electron are oppositely charged, so that's why they put this negative sign there. Yeah, I think that's what they meant. Is it here or here? Well, it's two negative signs. Anyways, see what it says. Rising the potential terms in the proton and electron are oppositely charged. The reduced mass in place of the electron is used. This is apparently a reduced mass one. Since the electron and proton orbit each other about a common center of mass and constitute a two-body problem to solve, the motion of the electron is of principal interest here. So the equivalent one-body problem is the motion of the electron using the reduced mass. Interesting. So they just use that one body there. What interesting. So they're using a reduced mass there. So anyways, so here's a summary summary of terms via Grok II and their physical meanings. So E and psi is the total energy. That's E, total energy times wave function. So that's the, again, wave function is function that assigns a complex number to each point x at each time t. So basically, basically the value of. Yeah, it just has a complex value on it, and then somehow that's related to waves, and so on. And the operator is the eigenvalue equation. That's for another topic. Anyway, sign is and notes can be negative bound states, and then right here, negative. This is the h bar squared divided by 2 mu times by the Laplacian of psi, or the Laplace operator of psi equals kinetic energy of relative motion. So that's kinetic energy. Interesting. And then now we have, this is a kinetic energy operator, and then always positive contribution. Yeah, so that's always positive. Yeah, so this is a negative one. If this is always positive, that's why they put a negative there. I think that's how they do that. And then negative pulls electrons for, this one's also, and this one's always negative as well, because I have a negative there. So Q squared is positive. So attractive Coulomb energy, potential energy operator, negative pulls electron towards proton. So if this is negative, yeah, this is interesting. There's always there's always positive contribution. Yeah, never mind. That's always positive. So in other words, so they put a negative there, so that because inside term somehow becomes negative and then becomes positive. Anyways, that's for wrap my head around that. Anyways, so the main point about this is you take this right here, and then using separation of variables in spherical coordinates, you get this setup right here. Again, exactly what we were covering. So you get psi of r theta phi is equal to the r of r. This is the equation of the radius term only, and then times it by the spherical harmonic component there, or the angular component yl lm of theta and phi equals to now r right here, and you have this symbol right here. Yeah, and this term right here, yeah, this is actually just capital theta. So theta capital's like that. It's interesting. It looks like that. Or like this, something like that. That's pretty fascinating stuff. And then there is the phi, and this is capital phi, and this lowercase phi. Sometimes written like that, and I just like this one, right? I just like that. But anyways, that's similar to the capital one, like this. That's interesting stuff. Anyways, so where r are radial functions and y, ln, lm of theta and phi are spherical harmonics of degree L and order m. So that's what you call them. So this would be n in our case. So degree n, L, order m. This is the only atom. So again, this is the equation for if it's shown for the electron in a hydrogen atom or a hydrogen-like atom. I'll put that in actually. I'll put it. Yeah, and here quickly teleport here. Here's a Wikipedia. So a Schrödinger equation for the electron in a hydrogen atom or a hydrogen-like atom. I think that's pretty important. I'll put that right here. Oops, and then I'll paste it. Yeah. As well as the solution below. So basically the solution to this one here, you will get, so using separation of variables in spherical harmonics, we get this setup right here, and then we solve these. Basically we solve these, we get the, this is the only atom for which the Schrödinger equation has been solved exactly. Otherwise, you're going to need approximate solutions. So multi-electron atoms require approximate methods. The family of solutions are, so this is the for the electron around an hydrogen atom. So we have psi of n, l, m. So now we have three terms there. This is r, theta, phi, and this is going to be squared as a normalization factor, square root, and then we have 2 divided by NA naught, or NA0 to the power of 3 times N minus L minus 1. So this N is not the same one we use. This is like some other operator. That's why they use N there. The one we were using is this L is going to be our N. And then they're using some other term there for the actual term. So N is a separate one. So ours are L. So we have N minus L minus 1 divided by N's factorial divided by 2N, and then times it by N plus L factorial, times it by E to the R divided by NA naught. And this is the R component. Actually, no, this R component keeps going here. Times by 2R to the power of, divided by N A naught divided to the power of L. So this is the R component. This is N. This is R of R. And now we have, this is the new spherical harmonics setup. What it looks like. Actually, no, there's still an R there. This is an L, 2L plus 1 of, this is N minus L minus 1. So this is the new new angular spherical harmonic operator. So now we have 2R divided by N A naught. R is massive. So where A naught equals to, make this bigger. So A naught equals to 4 pi, this is epsilon naught h bar squared divided by mq q squared is the Bohr radius. And then L to L plus 1. Again, this is the associated Legendre. Now it's called the generalized Laguerre polynomials of degree n minus L minus 1. Okay, this is, it's like every time I think I grasp it, it gets next level. And this is not covering it in this video, maybe a future one. So N, L, M are the principal, azimuthal, and magnetic quantum numbers, respectively, which take the values n equals 1, 2, 3, L equals 0, 1, 2, n minus 1, and M equals to negative L, . So again, in our situation, L is n, and we don't have one for this one. Again, that's because this is a solid, this is basically using actual R values. All right, and now if we take a look at this here, this is the hydrogen wave function here, and I just want to make a quick note. I'll draw this in a different color. This uses, it's pretty much exact same formula here. This is the psi NLM, and there it is, psi NLM. I'll zoom in like this. Yeah, there it is. It's pretty much the same thing, but they have this rho sign. So, and that's because they put this L associated Lagrange function with a rho instead of this one where we had this. So basically they remove that, they add this one, and then they pull out the spherical harmonics YL and M term. So basically just rearrange it, but it's pretty much all the same thing here. All right, yeah. Now that we covered that, just go back over here. So basically this figure right here, this is cross sections of atomic orbitals of the electron in a hydrogen atom at different energy levels. The probability of finding the electron is given by the color as shown in the key at upper right. And note that the negative and plus indicate the phase of the wave function. So this darker ones, it just means that the phase is going to be negative, and this brighter ones is positive. But these can go either direction. It's going to be the same probability or similar probability of high probability of finding an electron. For example, in this region here, this would be high probability, and then this would be the other one will also be high, but in a different phase. And then these super bright ones would be on this phase of the wave function. There, so you have different probabilities, and then the black regions are the ones where you're not going to have you're going to have very low probability of finding any in these darker black stuff there. It's pretty interesting setup there, and you got all these different energy levels, different lobes, and so on. All right, and going further, so here's another figure. This figure is 3D views of some hydrogen-like, basically just any atom or ion with a single electron, atomic orbitals showing probability density and phase. These G orbitals and higher are not shown. Basically, you have this s orbital, and you have this setup here, and it goes on. Yes, and you have the next one, and so on. So it's pretty interesting stuff. And the table below shows the real hydrogen-like wave functions for all atomic orbitals up to 7s, and therefore covers the occupied orbitals in the ground state of all elements in the periodical table up to radium. All right, I guess I think the bigger ones have even bigger, more complex the electron configurations and more different layers on them, and so on. But anyways, here's just the idea of this. You get these just to get the idea of how spherical harmonics are used to basically help plot these orbitals, or the probability density function, or the wave function of just electrons around an atom. So that's pretty, or a electron around in hydrogen or other types of atoms. So that's pretty fascinating stuff here. And you get different shapes and so on. And then here's the more complex one going over here. And then and again, in this case, this is n. In our case, this would be n, but it has another term. This is the energy level n, and so on. And then they use L pretty much everywhere. I just use n for this video, just for derivation. It's pretty epic stuff. So no elements with 6f, 7d, or 7f. I just want to read these notes because it's pretty interesting. 7f electrons have been discovered yet. So that's over here. So there's on the f. This is on the L, or n is equal 3. And goes over to here. So this, yes. So there is no 6f. So none of these. 6 or 7, none of them have been discovered. And elements with 7p electrons have been discovered, but their electron configurations are only predicted, save the exceptional LR, which fills 7p1 instead of 6d1. And yeah, this LR, I quickly just went over here to Wikipedia. So LR, or Lawrencium, is a synthetic chemical element as a symbol LR, formerly LW, and atomic number 103. It's named after Ernest Lawrence, inventor of the cyclotron. Interesting, a device used to discover many artificial radioactive elements, and so on. That's pretty fascinating stuff. How does it even look like? Is there any images of it? All right. So that's quite a fascinating stuff. Anyways, that's for another day. Yeah, actually, again, I just wanted to Google it. So here's Lawrencium. Silver solid at 25 degrees there. That's its appearance. Looks like silver, and solid at 25 degrees Celsius. Pretty interesting setup there. And let's see right here. The most stable is half-life of 11 hours, but the shorter-lived is 2.67 is most commonly used in chemistry because it can be produced on a large scale. So does that mean it just like radioactive decays in two minutes? That's quite wild stuff. All right, let's continue further. All right, and for the elements whose highest occupied orbital is 6d orbital, only some electron configurations have been confirmed. That's using MT, DS, RG, and CN are still missing. And interesting, yes, there's other elements there. This is 6d for elements whose highest occupied orbital is 6d. That's over here. So you go to the D, you go to the 6 right there. Yeah, so this one, these ones here, the ones that is the maximum there, and it just says only some have been confirmed, and then these ones are still missing. All right, these are the real valued orbitals commonly used in chemistry. Only the m equals 0 orbitals where our eigenstates of the orbital angular momentum operator Lz. Interesting. And again, yeah, these are the real valued setup. Keep that in mind. This is the real valued, so it's ignoring that complex rotation there, and we'll go over that in a bit. So these are the real orbitals. It's kind of like a scalar, take a snapshot or projection and get that value. All right. Yeah, so only, and then it says here, only the m equals 0 orbitals where our eigenstates of the orbital angular momentum operator this. The columns, yeah, that's m equals 0. Yeah, so these are the m equals 0. Yeah, these are, again, this is just beyond the scope of today's video, or my head for now, until I understand what's going on here. For now, I'll be for another video. Again, this is just for deep diving into basically the motivation for going over spherical harmonics. Anyways, the columns with m equals plus minus 1 and plus minus 2 are combinations of two eigenstates. See comparison in the following picture. Anyways, I'm not gonna go over that. So this plus or minus 1. So that's these ones, plus or minus 1, etc. Those are combinations, and I think this would be combinations of even more eigenstates. And then the here's a quote from Wiki. So one should remember that these orbital quote states, as described here, are merely eigenstates of an electron in its orbit. An actual electron exists in a superposition of states, which is like a weighted average, but with complex number weights. And the quantum state after measurement is in an eigenstate corresponding to that measurement and the value measured. All right, here I quickly just bolded this eigenstate there because you see that a lot. You see the eigenvalues, eigenstate, and so on. So it's also from Wiki quote: numerical or analytic solutions in quantum mechanics can be expressed as pure states. These solution states are called eigenstates. Are labeled with quantized values, typically quantum numbers. For example, when dealing with the energy spectrum of the electron in a hydrogen atom, the relevant pure states are identified by the principal quantum number n, the angular momentum quantum number L, the magnetic quantum number m, and the spin z component sz. So basically, I think what it's just trying to say is the eigenstates are just like snapshots into the full solutions. You have the full wave function, and so on, and you take a snapshot with quantized numbers, and then that will be your eigenstate, one of the eigenstates, where you have these specific quantum numbers, L, N, basically N, L, and M, and the spin, and so on. So when you quantize, put a specific value in them, you get a solution, and those are called eigenstates. So instead of the, and now this is also from Wiki, so instead of the complex orbitals described earlier, so these ones are actually real. Typically all the ones I graphed are just real orbitals or real spherical harmonics. So instead of the ones we discussed here, this one's actually uses the imaginary setup there. The imaginary number I is probably somewhere hidden in there, I'm assuming, because you have, you're going to have an imaginary component inside here, and so on. And let's go further. Yeah, you actually go back here. It's either in there or it might be in here, and so on. I don't know what the, this is the full generalized like horrible number. So you're going to have imaginary numbers somewhere in there. It was going further here. So instead of using that complex atomic orbital, so instead of the complex orbitals described earlier, it is common, especially in the chemistry literature, to use real atomic orbitals. These real orbitals arise from these simple linear combinations of complex orbitals. Real orbitals are related to complex orbitals in the same way that the real spherical harmonics are related to complex spherical harmonics. So here's a psi real. You go, you put the superscript real, then put NLM, and then you have these multiples, this constant squared 2, this negative 1 power of m, times it by, now you take the imaginary part of psi, this is the wave function there, the imaginary part, and this is for m is less than 0. And again, notice here, if you have an imaginary, if this one has an imaginary number I, and then you're multiplying, but this is a negative 1 to power of m, well, we know that I is just equal to, well, negative 1, square root of negative 1. So in other words, squaring this equals to negative 1. So when you're basically throwing some negative 1s in there, you're going to eventually cancel out the I. So the whole idea is to cancel out that extra I there. So you have no complex setup there. And then for m is equal to 0, it's just the same thing. It's just nothing changes. And then for m is greater than 0, you get this right here. You take the real component and you multiply by this setup there. And then for this part right here, and this simplifies all down to this giant thingy there. So that's interesting. So I divided by square root 2 and times by this. And then for different values, you use absolute value, negative, positive m, and so on. So again, very, very similar to the same setup we had all the way back in our real spherical harmonics. And that's this setup here. So for the real spherical harmonics, we got this setup here. So those are the real. And then, but now we have the extra term. We have NLM. Other one we just had N and M, but this one's actually L. But yeah, so we had an extra term in the other one for the orbital. Yeah, so we got this whole setup. And then this is if psi, put this also note here. So if psi, NLM is the real one of R theta phi equals to R NL of R times by Y LM. This is the spherical part, theta phi, with R and L of R, the radial part of the orbital. This definition is equivalent to just stating this right here, psi real, NLM. Yeah, it's basically the same thing here. Just put the real one there. Yeah, this one doesn't say real. This one, same thing where YLM is the real spherical harmonic related to either the real or imaginary part of the complex spherical harmonic. Interesting. So this complex is real. This one, okay, I assume this would be the complex one. This is, yeah, they don't put real there. This put real here. Okay, interesting. Setup there. Yeah, so earlier I said real. Yeah, this one's not the real. This one is equivalent to this, where this one is just a real component of that complex spherical. It's fascinating stuff. Anyways, animation continuously varying superpositions of between the P1 and Px orbitals. I'll show you some superposition of states. So again, this is It's a bit beyond the scope of this video, but it's, I just want to see the animation. It's pretty cool. So here's orbitals and states, and it's all changing. So you got the superposition animation, yeah, of continuously varying superpositions and so on. There's one type of superposition. Let's see it moving in. All right, so that's how you go from the states and so on. So notice all the colors too. So that's very fascinating colors. Yeah, this is super. So I think that's what I mean by superpositions of states. So this is the yellow and red. Now this one has like colors are all over the place. So note that the superpositions are the separated lobes chosen so the complex terms are eliminated and not the rainbow eigenstates or pure fundamental solutions. So that's interesting. So they separate the eigenstates. I mean, they separate the complex terms. So these are the real ones. So you have this setup here. So you could view it this way. Actually, yeah, this is very fascinating. This is superposition. That's pure fundamental. And here, separate them. So if you separate the complex terms, you're going to get this. If you include the pure fundamental solutions or complex setup, you're going to get something like this, where you put them all together. So it's, you get the rainbow ones. This is fascinating. And I'll just say, yeah, fascinating stuff. And a bit beyond the scope of this video and my head for now. I'll eventually grasp when the world's going on here. So atomic orbitals S, P, D, F, M, eigenstates right, and superpositions left. And yes, actually, so the left is superposition. Continuously varying superposition. So note the superpositions are separated lobes. Okay, so these are superpositions on the left, and they put this on the left here on purpose so that you don't get confused. Because this sounds like super. Yeah, okay, I got this mixed up a few times. So it sounds like this would be on there, but no, the left is this one here. These are the separated one. I was asking Grok AI all this. So these are separated ones. I assume this too, or so on. And then this is the SPDF eigenstates. Put them all in like that. Interesting. So these are separated. Remove the complex one. This is including complex, and this is removing. I'm pretty sure that is. Anyways, fascinating stuff, and a bit beyond the scope of this video and my head for now. All right, that's amazing stuff. And now I'm going to go over magnetic fields quickly. And so likewise, magnetic fields can be expressed as spherical harmonics, as expressed in Lori Gardy, aka Fractal Woman's paper. So here's paper she published also on the Hive blockchain. It's pretty cool. So for a magnetic multipole, she calls that because, her view is there's no magnetic monopoles. It's always a multipole. You always have a north and a south. You can't have it separated. So the scale, similar, because the electric charges, you can have a plus and minus. This one, you always have a north and south, or minus and plus, so you always have a two poles. So the scalar potential outside sources can be expressed as... Alright, I quickly paused video and just did some research on this scalar potential outside sources. Basically, I asked actually Leo AI on the Hive blockchain instead of Grok AI, because I thought the answer was a bit better if I click this. And then it's also on the Hive blockchain, so it's public and and it's decentralized and immutable, so pretty cool. So here's the thing. You could just go hashtag ask Leo. What does the magnetic scalar potential outside sources mean? And it says this physics concept from electromagnetism. The magnetic scalar potential is a mathematical function used to describe magnetic fields in regions where there are no electric currents or changing electric fields. That's what quote outside sources mean. Yeah, so basically it's a mathematical function describing mathematical fields away from a source or a source of current, etc. That's just a simplified one. For example, if you have a magnetic, if you have a magnet right here, and assuming it's according to the Einaldino's theory of basically rotating current or rotating ether right here, this produces a magnetic field. And now these are the outside sources. And so these are away from the source of the current there. That's a magnetic field. So it's a mathematical function and so on. I believe it has some physical component, but that's for another day. Anyways, this can be expressed as, and also, before I even go further, and also cool thing about this is on the Leo AI, because I could just go send a link to a different reply in that same thread. So you go right here, and I asked it about the magnetic field. Is the negative gradient of the scalar potential. So how can there be a magnetic field if there's no electric current? And it says, great catch. This is where outside sources come from, and the magnetic field does exist in those regions, but it's generated by currents elsewhere. So in other words, in the magnet. All right. Anyways, going back here. So here is the scalar potential. Looks like something like this. where we have capital letter phi like that. This equals to it's a double summation, and now we have our usual this thing here, the associated Lagrange function or similar setups to it, or something like that. And then this is the YLM, that's spherical harmonics there. And then now the magnetic field is then obtained as a negative gradient of this. Again, remember this one, that's like a partial derivative and so on. So the negative gradient of that. So, and then basically now we're measuring the component of B, this B field, magnetic field of, and this is again, that's scalar potential. And now if you, the magnetic field is the negative gradient. So measuring it with a Hall sensor gives a scalar projection that depends on the orientation and then producing lobes and nodes analogous to orbital probability patterns. So it's pretty interesting. So if you have a Hall sensor measures the magnetic field, but then it basically has it's kind of like this. It only has one direction it measures. So if you have a magnetic field going this way, it will basically take the component that is this one here. That's what it would measure. So if you have magnetic field pointing to the right, for example, left or right is north or south, then this thing you would measure is 0. So this Hall sensor measures is 0. So basically here is the these are magnetic field vector lines. Now these this is the isopotential lines, these lobes. These circles there, and this is perpendicular to these vectors, and basically it just means that these are the same magnetic field strength. For example, if this would be measured voltage or whatnot, it'd be the same strength everywhere. It's the same, and these are same. It's kind of like a gradient, if you look at a map and you see the elevation heights and so on. And and now if you do the real magnetic field, so basically if you just highlight all the ones that are near up. All the ones near up and circle them, you get this, and that's what basically the Hall sensor would measure. Is if you were measuring all the horizontal ones would be like 0, so we measure in black. So if you do it all in the up ones is red, all the down ones is blue, you get these weird you get these very similar lobes. And again, there's a Hall sensor diagram there saying if you're measuring from that orientation. So this is the projection effect, and so on. And here is a magnetic field like this. Here's using the Fractalwoman's proprietary software from her work using MRA scans and so on. Here's cross section, and you get these lobes in 3D and so on. So quite fascinating setup there. I just wanted to show that. And also here's a note I found on the website online. So figure any complex magnetic field can be expressed in terms of a sum of weighted spherical harmonics of different orders. Order 0 is a constant value. Order 1 contains simple linear harmonics, here principally directed and labeled in the Cartesian coordinate system as z, y, and x respectively. The second order has 5 harmonics called z squared, zx, x squared minus y squared, zy, and xy. Order 3 has 7 harmonics, a few of which are illustrated. As the order increases, so do the number and complexity of the harmonics. And again, these are complex magnetic fields. And here is the directly on the sphere. So you get the sphere, you got a whole bunch of shapes like this. And this is actually quite fascinating stuff. And then you got these different orbs. Again, these are all because you're changing the number of L, M, L, or basically N and M. Or you could do the L instead of L. Or how do you write even an L? Yeah, instead of the M there, and so on. You get the different shapes. You change different integer values. You get all these weird shapes. Again, this is fascinating stuff. A lot of this is again above my head, beyond the scope of this video. But I just wanted to show this. And here's this is MR magnetic field mapping performed. I think this is a part of the MRA scanners or something. MRI. Is it MRI? Yeah, this part of questions and answers in MRI. So this is fascinating stuff. So again, they're dealing with spherical harmonics in the professional setting there at the medical and so on. Complex fields such as B actual are commonly described using a mathematical formulation known as spherical harmonics, or the 3D analog of Fourier series used in other MRA and so on. A closely related Taylor series taught in elementary calculus books. Underlying concept is that any field can be expanded to a sum of weighted terms reflecting each spherical harmonic component. Interesting. Yeah, so that's again fascinating stuff here. And I just want to do that again. That's the driving force behind why I'm covering this specifically. All right, and if you made it this far, let's take a look at that mathematical review now. But again, the timestamps are all in the description, so if you want to skip the initial introductory part, and again, which is a lot of it is just me trying to wrap my head around the practical applications of spherical harmonics. And now we're going to go into the nitty gritty. But again, even just understanding how they're even formulated, it's still still have to wrap my head around exactly. But I'm getting it anyways. So mathematical review now before we start deriving a lot of the equations. So Laplace's equation is a second order partial differential equation named after Pierre Simon Laplace, who first studied it in 1786. A partial differential equation, PDE right here, is an equation which involves a multi-variable function and one or more of its partial derivatives. A multivariable function is a function with more than two arguments, such as the volume of a cone. So, for example, volume is equal to, well, it's dependent on the area of, this is the area, this is cross section right here. This is area of the base, and h, the height of the cone. So basically, if you have a low one, you're going to have a low volume, and so on. So that's a multivariable function. So volume is equal to 1 divided by 3 area of the base times by the height. And here is another figure. So where r is the radius of the base of the cone, and h is the, actually you write it as well. This is the pi r squared, is just the area. That's just pi r squared is the area there. So volume equals 1 over 3, so 1/3 pi r squared times h, where r is the radius of the base of the cone, and h is a perpendicular height of the cone. Going further, so a partial derivative is a derivative of a multivariable function with respect to one of those variables with the others held constants. For example, you could take the derivative of this volume right here in terms of, you could do the partial derivative v of in terms of in terms of h, for example. So basically, this would just look at the rate of change of this height here, ignoring this one here. So you set it, you can go at wherever value, and then basically the height changing. This is the volume changing with height, and so on. So that'd be pretty interesting. So it'd be something like this. So you'd be like changing the volume. What's the rate of change of that volume just by doing that? But then if you include the height, and if you include the height and r, you're gonna get something like this. And then so basically, think about the component. So basically, this would be the rate, the acceleration going up, or the rate change, and then this one is this is v over r, like that, and the top one is h. So anyways, so the partial derivative of a function fxy ... with respect to the x direction is denoted by any of the following ways. So you could go f of x, fx prime, go partial xf, d, capital D xf, d1f, and this is one I'm most used to, is basically this or this. So partial f, partial, you have this partial sign. It's like that. That's an interesting symbol. I forgot what that's called. Actually, I just quickly asked Leo AI. This is actually, it's also called del's, or partial, or del. Anyways, so it could be thought of as the rate change of the function in the x direction. So basically, again, similar to this one. This would be partial v, partial h would be in this upwards direction. All right, fascinating. So for a function f, x, y, and z of 3 variables, Laplace's equation is, so now we're using the f instead of the u, as I did earlier in the video. So the second partial derivative in terms of x of f, plus the second partial derivative of f in terms of y, plus the second partial derivative of f in terms of z equal, and then all this equals to 0. Hence, there's no rate change in this respect. So that's why the solution is harmonic or in harmony with nature. So a function that obeys this equation is called a harmonic function, and the Laplace equation can be written using the Laplace operator, or Laplacian. So you could do this. This is the triangle there. Delta, or the divergence operator. So now you have the upside down one, or of the gradient f. So this divergence one is this gradient thingy, upside down triangle, dot, or I think it's called nabla. And then the gradient is, this is the gradient. So if you do the dot, this is the divergence operator times by the gradient there. So what this means is, so this basically, so here's the Laplacian, Laplace, or the Laplace operator, delta f equals to divergence squared f, and then it's just equal to this dot, this one, and then this all equals 0. And then basically you have to get to this all just equals to that. All right. And the nabla symbol, this upside down triangle, written as an upside down triangle and pronounced del. Okay, this one's also pronounced del. I thought this was del. All right, anyways, I'll just say that partial. Denotes the vector differential operator, and this just equals to basically the partial derivative of each term. So that is what that is. The gradient, yeah, that's this part right here. So you can just do this right here. Delta f is just the first partial derivative of every single term. So you just remove these. And yeah, that'll be the del. And now you do the second del, second divergence operator. The gradient is the vector, this is the gradient is the vector field or vector function delta f, or del f, whose value at a given point gives a direction and rate of fastest increase. Yeah, again, this is the this is velocity, or the rate of change. And then this would be the acceleration. Remember, that's acceleration. This one is just the velocity, or the rate of change. In coordinate-free terms, the gradient of a function f of r may be defined by, yes, now we're dealing with the gradient, so df just equals to, this is the del f dot dr, where df is the total infinitesimal change of f for an infinitesimal displacement of r, and can be seen to be maximal when dr is in the direction of the gradient f. There. All right, so this is pretty fascinating stuff here. This is a dot there. Okay, so this is the figure. The gradient represented by the blue arrows denotes the direction of the greatest change of a scalar function. And yes, that's the greatest change there. The values of the function are represented in grayscale, and an increase in value from white low to dark high. So the high value, and this is low value there. There's a low value there, and so just showing the direction of where the function is changing. This one is moving, moving towards a dot there. This moves to the right, to the left, and this is used to denote the, for example, magnetic or electric field. This one, for example, electric field around a charged object, and it's pointing inwards. So that's pretty fascinating. So in 3D coordinates, the divergence is just the sum of partial derivatives, and uses the dot product notation as a mnemonic device. Basically helps memorize, to aid in remembering. So for example, div f is just equal to, I think it would be similar to all this. Anyways, that was for another day. Yeah, anyways, go back here. So div f equals to the divergence dot f, and this just equals to, the partial derivatives right there. And again, it's using dot product, where you just multiply each of the components and add them up. So this is just partial derivative of x, partial in terms of x, partial derivative in terms of y, partial derivative in terms of z. Dot, this is the fx, fy, fz components. And then basically what you do is multiply this by this by this, and then this by this, and add them all up. So that's just a way to, or multiply it in terms of just take a partial derivative. So that's equals this. But in this case, we're doing this of the gradient there. So we already have the gradient. So we already have this of f, and then we do it twice. So basically, you're just doing it twice. So it's pretty cool stuff. And here's some more interesting stuff. So divergence of two vector fields in 2 dimensions. So if you have, let's see how this is, the partial derivative of, this is the x term, where it's greater than 0, it would be going outwards like that. Interesting. Oh no, this is where the x component is going outwards. This is in 2 dimensions. So the x and y are both expanding. So the rate change is both expanding, and that the and basically the divergence, or this is the gradient. I think that would be called gradient. Let's go back here. Yeah, this is divergence operator. So go back here. Going back here. So basically, if the divergence of this is the rate change is increasing up in the x direction and y direction, and then you also have the divergence dot there is also increasing. So basically, that just all means it's all increasing. So it's expanding. But if it's all negative, you get this. Yes, it's all going decreasing, so on. And then if it's all equal, you basically have no divergence. It's all equal. In other words, you just have straight lines. So that's pretty fascinating stuff. So these ones, you could think of it as charges. This would be minus, to be plus, etc. And this is 0. That's no charger. Anyways, that'll be for another day, but I just want to wrap my head around that. All right, fascinating stuff. So now Yeah, now that we got over this quick mathematical review, just basically all this stuff, multivariable calculus, partial derivatives, and so on. And now let's take a look at the nitty-gritty. So let's look at the Laplace operator in polar coordinates. All right, just some notes on this Laplace operator in polar coordinates and in the general spherical harmonics. So I will generally follow the derivations shown in videos by Michael Dabowski from the Mike the Mathematician YouTube channel for this right here. So one, converting the Laplacian in polar coordinates, converting the Laplacian in spherical coordinates, and solving the Laplacian to obtain spherical coordinates. Again, Laplace operator or Laplacian is the same thing. So I've also used some help from Grok AI for when the above videos are lacking. And and I also may be using the Leo AI as well on the Hive blockchain. So to help in obtaining the Laplacian in spherical coordinates, let's first obtain it for the simpler but related polar coordinates. So that's basically the way he uses is he does it for polar coordinates and then he just throws it in there for spherical coordinates. So let's solve the Laplacian in or the Laplace operator. Solve the Laplacian. I'll say the Laplace operator. The Laplace operator or Laplacian in spherical coordinates. Let's first obtain it for the simpler but related polar coordinates. All right, so in polar coordinates, what this means is, well, we're going to have actually the Laplacian delta f. This equals to, again, you could use the gradient setup or divergence setup, this like this. This equals to, and it's only going to be in, so we basically have to convert rectangular two-dimension into the polar coordinates. This is going to be the partial derivative of f, the second partial derivative of f in terms of x, plus the second partial derivative of, this is going to be of f in terms of y. Well, this is going to be just like that. Don't put a 2. Make it like that. This is going to be, in the way it's written, it's like this, equals to 0. So that is again, this is in 2 dimensions. This is in 3 dimensions. It's 3 dimensions, and then this is 2 dimensions, and now we need to convert this into polar coordinates and recall polar coordinates, and then also find the relation between x and the polar coordinates x, y. So if we have, I'll just write this. So this is the x and y, like that. This is x, this is y. Let's say we have a point P right here, and the distance is r. So we have point P, and this is the angle, this is the polar angle. This is going to be theta. So this is r and theta, like that. And so now this distance, let's say this distance is x, this right here. This full thing is x, that's y. So in other words, this would be x equals 2, and then recall that the sine, this would be the y. This y is equal to, so recall that the basic trigonometry, and this is the origin. Basically, this is the origin. Yeah, and then basic trigonometry, you have the sine of theta is equal to opposite over hypotenuse. So in other words, we get y over r. And then we can just move this y over to the, r to the other side. So we get y is equal to r sine theta. And likewise, x is going to be, well, cosine theta equals to adjacent over hypotenuse, x over r by definition. Move this over to the other side. So we get x is equal to r cosine theta. So that's fascinating stuff. So what that means is, and also we have Pythagoras as well. So Pythagoras, or a Pythagorean theorem. Also Pythagoras, let's put it like that. So we also have now the side squared equals r squared. So in other words, r squared equals to x squared plus y squared. So we have that. So put it all together, we have x is equal to, I'll put this like this, x is equal to r cosine, because we're converting to polar coordinates. So we got to put these x and y in terms of polar coordinates. And y is equal to r sine theta, and then we have r squared is equal to x squared plus y squared. Box this in. All right, now the next step is, well, let's write out the first partial derivative of f in terms of x and y by using the chain rule for partial derivatives and its associated tree structure. And that's by, first of all, if you look at this right here, because we want to get this in terms of r and theta. And this is right here. So we'll take the first partial derivative just to show you what this means. So this is the second partial derivative in terms of x. And then we're going to use this associated tree structure. So I haven't covered tree structure before, but the general idea is pretty much the same, and it's using chain rule for partial derivatives, or just chain rule in general. So if we have, for example, a function f, and then you make a tree, so it is a function of r and theta in spherical coordinates. So we want spherical coordinates. So it's a function of r and theta, but then r and theta. So r is a function of x and y. Theta is a function of x and y. So there's theta here. You could write this as a function of x and y. So then this is going to be x and y, and this is going to be x and y. So we will have to use the chain rule. So basically this is the tree structure. I'll put this right here. I'll just put this yeah, I clearly just moved it over there. So I'm going to go tree structure, just so we have the things in point there. So now the partial derivative of f now in terms of x. So we have to go well, there's two parts right here. So we're going to have this equals to a partial derivative. So we have to go over to this part. So we have to go, it's going to be partial derivative of f, and then partial derivative of r, and then holding this x, this part constant. We'll put this right here. This is what the guy in that math video was, how you would do in his derivation. So we put this right here. This means hold constant, or keep constant. Keep constant. All right, so we keep that constant. So that's the thing. It's partial derivative. And the reason it's partial is because we're going from initially this part to here, and then we're going to go the reverse way and add those up. And then we're going to have to multiply using, again, chain rule. This is going to be just multiplied by, this is going to be partial of, no, now it's partial of r. So it goes, r is a function of x. So now we go partial of r, partial derivative of r in terms of x, and where we hold this y constant. So keep constant. All right, and then we add the next term. So then we go partial f of theta. And where the r is constant. And then dot partial partial of theta. And then this is going to be partial x. And this is at y is constant. So there it is. All right, so that's the partial f partial x. So now the next one is going to be, I'll just say likewise. Put it here, and then this is going to, now we have to take the derivative of f in terms of y. But again, we want the r and theta converted to it. So now these are both functions of y. Yeah, so it's going to be actually pretty much the exact same thing, but we just replace x and y. So what I'll do is I'm going to copy this. I'm going to paste this here. I'm going to move this here. All right, so now we have this. And then this just becomes, yeah, we just flip everything. This is going to be partial derivative of f in terms of y. This is going to be, then this is going to be right here, y, and then this x is constant. And then this one here is going to be y, and that's x. It's exactly the same thing. So because both directions go from here, and now you have to split up to go left or right. So we go here now. This one goes here, and then it goes straight down. But in both scenarios, we use the r. It's basically, the first one's always the same. That's so fascinating stuff. All right, now that we have this, let's go for this. And I just want to make a note, I will cover partial derivatives more closely in future videos, but the chain rule is similar to that for normal derivatives from my earlier video. So recall, just for just general functions, the chain rule, if g is differentiable at x and f is differentiable at g of x, then the composite function f, g right here, yeah, f of g, is basically it's like f is a function of g, is defined by f of x equals to f of g of x is differentiable at x, and f prime is given by the product. So basically you take the product f prime of x equals to lowercase f of, f prime of g of x times it by now the inside derivative, g prime of x. So in Leibniz notation, if y is equals f of u, and u is equal to g of x are both differentiable functions, then dy over dx, so we do the inside one, is equal to dy over du. So we take the outer derivative, times it by the inner. Yeah, then du over dx. Again, exactly the same thing we did here. So we had partial f in terms of partial r, and then multiplied by partial r in terms of partial x, and likewise for the y side and the theta side. So fascinating stuff. Anyways, so we can solve the first partial derivative of f in terms of x as follows from our polar coordinate formulas. Yeah, so if we go, so we have this setup. All right, and now we basically throw them all in here. So we have, this is the first partial derivative of f in terms of x. So we'll go partial derivative of x. Actually, we could just copy paste the whole thing, so it saves time. Otherwise, I was taking many hours for this video. So it's just because a lot of terms. It's more complicated than it looks, is what I'm saying. But spherical harmonics, I think just the terms are just so big. So there it is, like that. Alright, yeah, so we have this, and then we, from our polar coordinate formulas, well, we take a look at what we have. So what I'll look at is this here. I'm going to look at this r squared right there. So that r squared, if we squared both sides, and also basically I want to get this term right here first. Let's get this term. This is r and x, because we have r and x there. So this equals 2, because we want to convert these ones basically to polar coordinates, this one to polar coordinates. Because this one is pretty much there in polar coordinates. So now what we're going to get is this equals 2, or I mean, r square root is equal to x squared plus y squared. That's just basically this one right here, using Pythagoras. So that is that one. We square root both sides. So now this also, just write it a bit neater. This is going to equal to x. This is x squared, y squared. This is power of 1 over 2. I mean, yeah, 1 divided by 2, or 1/2. Just put it like that. It's easier to take the derivative. All right, so now we have this, basically now this partial derivative right here, the partial derivative of r in terms of x while holding y constant. We can solve that by going, well, partial derivative of r in terms of x while y is constant. So in other words, we just take the derivative of this, but keeping y constant, so in terms of x. So this is, recall the power law, this goes down, so it's going to be 1/2 times it by, I'm just going to do the full, just understand this, and then we subtract 1 here. So we're going to go x squared plus y squared, and then 1/2 minus 1, so that, in other words, minus 2 over 2, this is 1, and basically 1 minus 2 is negative 1. So we're going to get a negative 1/2, like that. So when you get 1/2 subtract by 1, just negative 1/2. And then we keep going by using the chain rule inside, derivative of the inside where y is constant, that goes to 0, so we're going to get a 2x. So in other words, this 2 cancels, and this one is just put that in the denominator. So we're going to get a x over square root x squared plus y squared. And well, we know what this is. This is just r. That's just this part here. So that's just equals to that. So in other words, this equals to x over r. And we already know what we already know what x over r is. X over r is just cosine theta. That's just basic trigonometry. So that's just x over r is just equals to the cosine theta. So adjacent over hypotenuse is just cosine theta. So this equals 2. So we've replaced the x now with a cosine theta. So we have literally got rid of it and included a polar coordinate. So we got rid of the x, now we have a polar coordinate. All right, so we have that term. But now the next term that we can try to solve is this one here. This was an r. So the next one we want to get rid of is this x right there. So this partial derivative of theta there. So now, before we get to that, I'm going to go is note that tan of theta, just basic trigonometry. Well, tan of theta, recall definition, is just going to be sine theta over cosine theta, or just by definition, opposite over adjacent. So in other words, it's going to be y divided by x. Like that. So that's about y divided by x. Because we want to take the derivative of theta in terms of x. So we need to solve this one. So basically, this is just y over x. So in other words, theta, this equals to, recall inverse functions, theta is equal to the inverse of tan, so tan negative 1 like that, of y of x. Yeah, so that's what we have there. And so now basically we could take the partial derivative of theta in terms of x while keeping y constant. So we're going to go, so thus, yeah, it's basically, I'll just put an arrow like this. So now we got a partial derivative of theta in terms of x while keeping y constant. This equals to, well, recall that this equals to, yeah, I'll show that in a bit. So basically, the derivative of this one here, this just equals to 1 divided by 1 plus the inside function y over x squared. So that is the derivative of this inverse function there. And I proved that in my earlier video. And I'll show you a screenshot soon. Like that. And then now we take, using chain rule, the derivative of this y over x in terms of x while keeping y constant. So in other words, this is just going to be a, this part right here. Yeah, this is the same thing as writing again. You could write it as y times cosine negative 1. So the derivative is going to be, put the negative 1 down. So we're going to get a negative, I'll put in negative 1. I'll just put a negative. And then we subtract 1. So we're going to go y, and then minus that is going to be minus 2, or just put a square like that. Yeah, just put it like that. That's it. Or yeah, I put this power negative 1 like that, just easier for me to solve the derivative inside. So now what we'll do is multiply this x squared inside everywhere. So multiply that all inside and see what we get. So now we're going to get equals 2. We're going to get a negative y on the top. Just move the y on the top there. The bottom's going to be, well, 1 times x squared is just x squared. And now this is y squared divided by x squared. In other words, we're going to have y squared there. The x squared cancels. So this cancels with this one. So this just equals 2 plus y squared. And we know again, x squared plus y squared, that is just r squared. So again, that's this part right here. So r squared equals x squared plus y squared. So in other words, we got rid of, well, one of the stuff we got rid of. We got a negative y over r squared. This is r squared. Equals r squared like that. Let's put it like that. Yeah, that's just r squared. Yeah, but so we have this, but going further, what we could write this as is, well, this just equals to negative y, and then divided by r. So put a negative y divided by r. Let's put a y like that. Divided by r times it by 1 over r. Yeah. So in other words, this is just r squared. Separate that. So we have this, and then we know that negative. We know what y over r is. Scroll back up. Y over r is just sine theta. So that's just equal to, yeah, this whole thing is equal to negative sine theta. So this equals to negative sine theta divided by r. All right, so we solve this. So this is negative. Like that. Let's put it above like that. Yeah. So anyway, so that is what is, and we got rid of the x and y terms. Yeah. So put a line here. So thus, the partial derivative of f in terms of x and in polar coordinates is going to equal to. So we have the first term. This is cosine theta. So we have this part here is just be partial f in terms of partial r, and then where this is constant, we can just ignore that. It's just that's a given. And this one's going to be cosine theta. And then this one is going to be over here negative sine theta divided by r. Yeah, and then we have this del f over del theta. So in other words, partial f in terms of theta. So this is going to be cosine theta, and then we have partial f over partial r. Yeah, partial f in terms of r, and then we go subtract, and now this one's replaced. There's sine theta r. Now we have a partial f, partial theta. And again, these ones you could put this here and put a r constant, or just leave it. I'll just ignore it. You could do the same thing here, but it's this. But it's pretty yeah, it's given. It's just assumed to be the case. So that is that. And just a quick note, I'll recall from my earlier video the derivative of inverse tangents. This is from earlier video, screenshots from the calculus book. So the formula for the derivative of the arctangent or the inverse tangent function is derived in a similar way. If y equals to inverse tan or arctan is tan negative 1 x, then tan y equals x. Basically, that's just what it means. Where you solve this in. In our case, it was theta. And then differentiating this latter equation implicitly with respect to y, x, we used implicit differentiation of this setup. We get this, the whole setup, and then basically we get this over here. Derivative is equal to 1 divided by x squared. And that's the one I used right over here. This is a derivative of this one here. We got to this part right here. It's 1 over the x squared, and in this case, x is y over x, like that. And also here's a figure of this, so it's for completeness. So figure 11 shows the graph of f of x equals inverse tan and its derivative right here. Notice that f is increasing and f prime is always positive. The fact that this one here, tan of the inverse tan, is between plus or minus pi over 2 as x goes to plus or minus infinity is reflected in the fact that that f prime of x equals 0 as x goes to plus or minus infinity. So yes, the derivative. So basically this function right here. So here is this is the function is tangent. Here's inverse goes from -1 to 1 as x goes to plus or minus infinity, and this one goes to 0 as plus or minus infinity. This is the derivative. Notice how it's peaked at the center and it goes there. So it's always positive even though this one goes negative positive. Fascinating stuff. Anyways, let's go further. Similarly, for the partial derivative of f in terms of y, we have, so we basically do the same thing and we get something similar to that. We'll just take this for completeness and just do this. I'll take this thingy here, copy it, and this is the y component, so put it there. So we have the same exact setup there. We know that r is equal to, so r is equal to square root x squared plus y squared, and then basically the partial derivative of r in terms of y while keeping x constant. Yeah, like that. This is equals to, this is going to be same thing. It's going to be negative. It's not negative, 1/2, and put this at the bottom. Is going to be square root x squared plus y squared, and derivative of this is 2y there, like that. Again, exactly the same setup we did over here. So derivative of this goes down below, put the y on top, there's a 2y, then 2's cancel, and we're going to go, this cancels, we're going to, and this is r. Yeah, this is r. So this equals 2 y over r, and this equals to, move some space here, and this equals to, well, sine theta. All right, just move that over, let's box this in. So that's sine theta, and again, that's our sine theta, and that is because y over r, as we showed way earlier, that is just sine theta. Yeah, so it's sine theta. All right, now the next setup is, going from the partial derivative of theta in terms of y. We'll just take this again. I'll just take this just for completeness, take both. So write those down. Put an arrow like that. I'm just put a line like that. All right, so we have this, and then we take the partial derivative of theta in terms of y, keep x constant, and again, this is put it for completeness. But it's pretty much given. You don't need to always do that. This equals 2, and this is going to be, well, 1 divided by 1 plus this thingy squared. Yeah, this is going to be y over x squared, like that. Now it's going to be times it by, well, derivative of y over x in terms of y. That's just going to be 1 over x. Yeah, so what I'll do here is I'm going to multiply by this by x over x so that we have an x squared at the bottom. So then we expand this all out. We get x there, and then we have an x there, x at the bottom. 1 times x squared is x, like that. Plus this one here, y squared, and then there's an x squared. These cancel, so we're just going to be left with a y squared, and then this is just, again, r squared. So this equals to, yeah, x over, and then x over r squared, which equals to, again, you just put x over r times it by 1 over r, and then x over r is cosine theta, and then over r. So that is what we have there. And again, x over r, as always, I'll scroll there. X over r is equal to cosine theta, just basic trigonomic definitions, and that's just from adjacent over hypotenuse. All right, thus, let's put it all together. So thus, the partial f of partial y in polar coordinates, this is right here, equals to, well, this is going to be this part right here. We just shown that this is sine theta. This is sine theta, and this other one is going to be cosine theta over r, and then we just put this there. So that's going to be, this is going to be sine theta, and then partial f over partial r. And again, where theta is constant, that's a given. That's hence the partial sign, like that. And then this is going to be plus cosine theta over r, and then partial f over partial theta. So yes, fascinating stuff there. So we got both of these partial derivatives, and we're going to have to do this again. All right, so now we solved this, and now got these two. Now let's find the second partial derivative of f in terms of x. So we'll take basically this one right here. So we'll take this, and I will circle this. All right, and then the thing is, we need to do the second derivative, because remember, the Laplacian in polar coordinates is just this right here, the second derivative. The second partial derivative of f in terms of x plus the second partial derivative of f in terms of y squared equals to 0. So we need to get the second derivative, so we have to throw this all in here. So we want to get partial, second partial derivative like this, del squared. This is going to be x. This is in terms of x squared equals to. Now we take the partial derivative. So partial derivative of x of our partial derivative in terms of x of our partial derivative of f in terms of x. So we do it a second time. All right, so this equals to, and what I'll do is I'm gonna go paste this. I'm gonna put this right here. Let's put it like that. And let's erase this. Equals to partial over partial x, and then put this right here, like that. And what I'll do now is I'm going to call this star. Let's put this a star like that. I'll put a better star. Yeah, so that's a star. So now what we have to do is, well, this is partial derivative of x of partial derivative of f of x. We have to throw this back inside because we know that this partial derivative in terms of x is that's going to be, well, this. So in other words, we need to throw this back inside here. So we need to take the derivative in terms of r and the derivative in terms of theta. So this equals to, so the second derivative is going to equal to cosine theta, and then partial f is going to change it now to the star. All right. So there it is. Yeah, put that better. So there's our star, and then minus, same exact thing, so partial derivative, sine theta over r of partial, now we replace the f with partial r, and now it's going to be star. Well, yeah, so we got absolute monstrous there. And yeah, made a mistake here. This is theta. So partial star over partial theta. Because remember, this is the partial derivative of x, and now we have to do it again. So that's fascinating stuff. So now we have to solve this all. All right, so this equals 2. All right, yeah, so now this whole thing equals 2. Well, we have to just start solving these derivatives there. So we can take the partial derivative of this in terms of r, and then this one in terms of theta. So this whole thing equals 2. I'm going to put this entire thing here. So this, now we're going to get an actual equation. So this is this part right here. So the second partial derivative, because I'll box it in, of f in terms of x squared is equal to, it's going to equal to cosine theta, and that's this part right here, and then we have to put a box, and now it's going to be, well, the partial derivative of this in terms of r. So this one is a theta, so this doesn't change. This is going to be now the second partial derivative of f in terms of r. So that's going to be cosine theta, partial derivative of f in terms of the second partial derivative of f in terms of r, like that. All right, and now minus, this is in terms of r there. So yeah, this one is just in terms of, this one's not in terms of r, it's in terms of theta. No, but the thing is, the function f is a function of r. So we have to take, you have to use chain rule on that end. So in other words, what we're going to get is, this is going to be a minus, and then take the derivative of, we'll take the partial derivative of this one first, because this is a f, that is in terms of theta and r. So we need to take the partial derivative of that. I'll put the full thing, sine theta r, and now we take the partial derivative in terms of r of this right here, partial f over partial theta. Yeah, like that. And the reason, now we have to do basically chain rule. Yeah, that's the, because we have to apply chain rule. So now the next one is we take derivative of this part, and so on. Again, it's a minus, put a minus again there, minus, but then the sine of theta is equal to, actually no, not sine of theta, I mean there's an r at the bottom there. So now it's going to be over r, so we have to take the derivative of that, 1 over r, that's going to be, well, it takes it down there, we're going to do a plus. So this is, again, that's just going to be, this is r to -1. So put the 1 down, we're going to -1 r -2. So in other words, we'll have a negative, and the negative times a negative is positive, and this is going to be, well, sine theta over r squared, like that. And then this is, this is a partial f over partial theta, like this. All right, so here just shrunk it in and moved it over there. So now that's the first part there. That's basically this part. Now we take the second part. That's this part now. So now we got to go subtracted by minus sine, or try to write it smaller, sine theta over r. And now we have to take the partial derivative of this in terms of theta. All right, so it's going to be very similar to before. All right, yes, very similar before. So I'm going to go right here. So we have, this is in terms of r. So let's take that one first. I'll put the cosine there. Cosine theta. And then we're going to have a, this one's going to be partial derivative in terms of theta of, this is partial derivative of f in terms of r. Like that. And then this is going to be, and then we have to use chain rule. That now take the derivative of the first one. So that's going to be, now derivative of cosine theta is just sine theta. Partial f, partial r, like that. And you actually made a mistake here. This is a negative, yeah. The derivative of, you have to be very extremely careful here. The derivative right here, yeah, this part right here. So chain rule, the derivative of cosine is negative sine. Yeah, so this one's negative sine derivative, but then if you go other way around, sine goes to positive cosine. So just keep that all in mind. That's very, very important. Otherwise, you're going to get the wrong answer. All right, so we have this. All right, so let's see what the next setup is. So now we have to subtract, this part here. So now we go over to this negative side and then take the partial derivative in terms of theta. All right, so that means we're going to get a negative sine theta. We'll do the first one here, sine theta. I'll shrink this after. Sine theta over r. Let's put it sine theta over r, and then this is partial f or partial f squared, or second partial derivative of f in terms of theta. And then we go to the next one, minus. Now this is in terms of in terms of theta. So sine is going to be, well, minus that is just going to be cosine theta. Cosine theta over r partial f over partial theta. Like that. All right, here I quickly shrunk it and move it over here. Hopefully I got everything correct. And so on. But yeah, that's pretty wild. So likewise, we have the second partial derivative of f in terms of y. So what I'll do now is, well, this is the this part right here. I'm going to copy this because I will use that exact same setup. So likewise, we'll do, we need to solve for the second partial derivative of f in terms of y. Make this a bit smaller. Okay. All right, here I just wrote that better. Again, to go re-emphasize, because again, in 2 dimensions, we need to get the second derivative. So second partial derivative of f, we got this one. So we got this, now we have to do this, and we have to add them up and cancel a bunch of terms, and hopefully it all cancels out. Hopefully it all simplifies and is correct. And then we get this one here, and then that equals to 0 for the Laplacian, and so, or Laplace equation. So now we have, likewise, this equals to, well, this just equals to partial of, this is just going to be partial over partial y. It's partial derivative in terms of y of partial f in terms of y. So we know this equals to, let's put this like this. This equals to that. So let's put underneath. Okay, that equals this. So it's the big parts. And this is going to be equals this over y, like that. It's partial derivative in terms of y of this whole thing. All right, and then this thing, we'll give it a star as well. Yeah, just to make sure that these are different. Yeah, this cosine, that's the other one. That's this one right here. So we're going to do exactly the same thing as before. We're going to recursively put this inside. We're going to put this inside f. And then we're going to put this inside the other f. And solve it accordingly. It's again just recursively doing it. So then this is going to be, put this all in one giant equation. This is going to be partial f. It's the second partial derivative of f over y. This equals 2. This is going to be now sine. And then this is going to be now take the partial derivative of this part right here. Actually, I'll do it for completeness first. This is just going to be partial of r of star. Like that. And here, quickly just erase that and move it over here. Yeah, just so it's the same format as this right here. And then we'll put this one here afterwards over there. Get rid of this. It doesn't, it's not a 2. It's a partial. All right, so we have that. Yeah, this can be quite fascinating. And then the next one's going to be, well, this is going to be plus cosine theta over r, and then partial of the star in terms of theta. So it's going to be partial star. Perfect, like that. All right, yes, now we have this, and now we'll do that thing I wanted earlier. So basically partial, I'll try to see if we fit it all in. Partial of f, the second partial derivative of f in terms of y equals 2. So we put this here, sine theta, and now we put a giant block, and now we take the partial derivative of this thing in terms of f. So that's going to be, well, sine theta has no r component, so it's going to be like that. Second derivative of f in terms of r. And then, yeah, like that, squared plus. Now the next setup here is, we'll just do it over the same thing that we did likewise. In the other one with the chain rule, we'll do this one. We'll do derivative of this one in terms of r. And then plus derivative of this one in terms of r. So this is using chain rule. It's going to be partial over partial r over now partial f over partial theta. And this equals 2. Yeah, and now the next setup is, well, plus. Yeah, plus this one here is this is a 1 over r. In other words, that's going to be, well, that's this r divided by -1. Move it down. It's going to be -1 and then r squared, like that. So that's that. So we have a negative now. So this is going to be negative cosine theta over r squared. And then this other part is going to be, yeah, that's this one or this one. I mean, yeah, the same thing. Now this is going to be just that by itself. F over theta. Yeah, because again, that's chain rule. Put that in like that. All right, here, just shrunk it and moved it over here. And now we take the other part, this one right here. So plus cosine theta over r. And now we take the partial derivative in terms of theta here. Yeah, the other one is in terms of r, now in terms of theta. Well, this one is, yeah, throw that in that. This is the star one. So I'll do the same convention. I'll do this one first and using a chain rule, and then the second one after. So this is going to be, so the sine theta stays. And now this is going to be partial of theta. And this is going to be now partial f, partial r. That's just that. Yeah. And then using chain rule, the next setup. Derivative of sine is just cosine. So this is going to be plus cosine theta, partial f, partial r. Like that. And now the next one's going to be on the other side. Plus, we'll do this one here. So this is going to be just chain rule cosine theta over r. Leave it like that first. Do the derivative of this one. This is going to be, this is partial squared of theta squared. Like that. And now we have a cosine over r. The next one is going to be now, this is just going to be minus now. Minus sine theta Because cosine, derivative of cosine theta in terms of theta is, yes, it's that. Divided by r, partial f over partial theta. Like that. Box that in. All right, here I just shrunk this and put this in as well. So yeah, we have two equations now. This is the partial derivative, second partial derivative of f in terms of x. This is the second one in terms of y. So now note that by symmetry of second derivatives, also called the, I think also called the Schwarz integratability condition, or Clairaut's theorem, or different variations of it. We have basically, so get note right here, this will simplify the entire thing. Because if we have this partial of theta times, partial derivative of this function. So this is partial f over partial r, and this is partial of this whole thing of theta. It's the same thing as if you rearrange these. This is the same as having this. These are equal. So these are equal. And that is by this thing I might cover it in a future video. Symmetry of second derivatives, or Schwarz integrability condition, or Clairaut's theorem. What we have is this partial derivative of theta. And again, just works for just if you have a y or x, just flip them around. So the partial derivative of f in terms of r, the partial derivative of that in terms of theta is equal to the same thing if you reverse them. You just reverse these. They're still equal. Same thing as partial of r, and then partial f, partial theta. So this will greatly simplify the setup. Make this a bit better. Alright, so now we have that. Now we can put it all together to obtain the Laplacian, or the Laplace operator in polar coordinates. So what I'm going to do is, well, we have the, it's basically the Laplacian polar coordinates is equal to delta f. You could write it as this squared of f. This equals to the second partial derivative of f. This is going to be of f second of f over, in terms of x, plus the second derivative of f in terms of y. So this is the Laplace operator. The Laplace equations just set them equal to 0. So that's the Laplace operator. And now we're going to put these all together. So this equals to, and I'll put a giant thingy here. I'll just put it like this. What I'll do is I'll take this one here, copy, and paste it. So we have this. So it equals to this, equals this, and then we have to do a plus now. Well, we'll do the plus after. Now this part here. And then we're going to cancel a whole bunch of terms and also use this symmetry of second derivatives to get rid of all the other terms. So that's this right here. And now this is going to be a plus. All right, so now let's take a look at what we can come across. So here's one thing we could notice first. This one, notice here, this is a cosine and a cosine. Those become squared. Over here, there's a cosine and actually no, not there, over here now. So there's a sine and a sine squared. Well, what happens there is, and I'll just write these out and see what happens. And this is the same term, it's the same exact term. And remember, sine squared plus cosine squared is equals to 1. All right, so let's write that down. Let's write this cosine. This is going to equal to cosine squared. Now put a block. Cosine, or put a normal block like this. I'm just a bracket cosine squared plus this one right here, sine squared, and we just multiply that inside, plus sine squared. And that's going to be, and they both have the same factor, so second partial derivative of f in terms of r, like that. Yeah, so, and we know this is just equal to 1. Yeah, so that gets rid of that. So we have already simplified that. So we have these two. So I'll just, we'll just ignore those. So now the next one is this right here. So sine theta over r. Yeah, sine theta over r, and now we have this partial derivative in terms of r of the partial f over partial theta. So we have this, and remember we use this condition, so we just need to look for another one that's partial of theta in partial r, and then see if it matches up. And lo and behold, let's see what we get. we get it should be somewhere here. Yeah, we get, this is sine. Yeah, this is sine over r, but notice what happens here. So this is sine over r, but there's a cosine here. So multiply this, so you have a cosine sine over r, and this is negative, and now we have a positive. So this one right here, I'll circle this, and now we have this cosine over r, now we have a sine. This is partial theta, so notice the flip. It's partial r, it's partial theta, partial f, partial r. So we use symmetry. These cancel. This is minus, this is plus. And these are exactly the same thing. So these cancel. So we've already canceled one of them. So I'll remove this. So we've canceled this and this. And we've already taken account for this one. So we've accounted for this. We've canceled this. Now the next one here is this sine theta. So now we have a sine theta over r squared. And now we have this. This is a partial of f over partial theta. All right, so we have to take a look at this, and also we have to also account for this. So we have a cosine there, multiply the cosine sine, so we have a cosine sine, and then we have this r squared. Well, and this is positive, and then we have this. So we have to look at somewhere else. We can actually just look within our own thing. This matches this, and then we have this one here, sine. Well, we have this negative. This is a negative sine over r. Now this is a negative cosine over r. So in other words, we're going to have a positive right here. Wait, actually, we shouldn't even be doing that. They'll actually add up. So that's the wrong one. So, but again, I'll keep this in. I don't want to remove this part of the video. Oh, that's pretty cool. So we have these two. So what I'll actually do is if we just go back to the bottom here. So now we have, this is a cosine over r. There's a negative sine over r. So now we have the same setup. This is r squared. So we have an r squareds add up. So we have an r squareds. Now we have a negative sine cosine, and then we have this delta f over delta theta. So this cancels, because it's the same exact thing, but negative. So this is a cancellation. So this cancels with this. So now we have that cancellation. Now let's go to the next setup here. So now we have a sine here. So we have a negative sine r multiplied by the inside one here. This is going to be cosine theta. And now we have this part here. We're going to use the same symmetry as before. This is a delta. This is a partial over partial theta, and then partial of partial r. So we're going to have to get the reverse by using, again, symmetry. So we take this, we look at something similar on the other side, and that setup is going to come across in, and well, where would it be? Well, this one canceled, this part here canceled with this. So then this should be somewhere over here, I think. Yeah, this one right here. So that's always a symmetry. If this canceled with this, then this one here has to be this one here. It's basically this one corresponds to this, and this one corresponds to that. All right. So now if you look at this one here, there's a partial over partial r, and then this is partial of partial theta. So now these are the same. These are equal. So these are equal by symmetry. So by symmetry. So we have by symmetry is equal. And then this is a cosine. I'll just erase this symmetry setup. Okay. Now we have a cosine theta over r times sine. So we have a sine cosine over r. And now here we have a negative sine cosine over r. So then those cancel. There's the same exact thing, but negative. So this part right here cancels with this. All right, so now the next setup is here. So far we've only added this part here. We haven't added anything else because those are all just canceling out. Yeah, so now we look at this part here. Let's see if this would cancel or not. This is, this one right here is sine theta, partial f over partial r, and then there's a sine, this is going to be sine squared over r. Negative, this is going to be positive, negative becomes positive. So, and then, so now we have a negative sine, positive sine squared. And then if we look at, so this one right here, if we look at something similar, that's going to be right over here. We need a cosine actually. And this one, there's a divided by r. So we need one that's divided by r. And that's going to be right here. Yeah, this one here. So if you look, this is partial f over partial r. This is cosine, partial f over partial r. This is cosine over r. So now we have a cosine squared over r. And this one is there like that. So in other words, we get these two. So I'll just circle this and I'll erase it after. So we multiply these and then this and this. And then we can have these exact same factor like this. So this is going to equal to plus. So plus, this is going to be a plus there. We'll put a 1 over r, get this out of there. 1 over r. Actually, I'll put the 1 over r, yeah, let's put it in the front here. This is 1 over r. Now we have a sine squared. Yeah, and again, recall this is just a trigonometric identity, just basic one, Pythagorean identity. Cosine squared plus sine squared equals 1. Now this is going to be like that, sine squared. And this is the factor partial f over partial r. So now this is going to be here, cosine squared, and there's an r there at the bottom, so we could factor out the r. This is going to be cosine squared, and now we have a partial f over partial r. Yeah, so that is fascinating. Now this equals to 1. So now we need one more term. Well, so now we solved these ones. So I'll just erase this now. And I'll erase the ones that, yeah, we already included. So now the next setup is looking at over here. All right, so now we look at this. This is going to be negative sine. This is going to be positive sine squared over r squared. And now we have, this is a partial f squared. And then we look at the next one that has the same factors as partial f. This is one here. And yeah, this one, notice here, this is a negative, it'd be positive sine. And then there's to be, yeah, positive sine squared, and there's a divided by r squared. This one here is cosine. So we have the exact same thing, positive cosine squared over r squared. And there's the exact same setup. I'll delete these after, so I'll circle this so we know what we're writing. This is going to equal to, this is going to be plus, so these are all positive, sine squared. I'll just put a 1 over r squared like that, so we have it there, so we don't forget. Now we're going to get a sine squared plus cosine squared. And again, this is when dealing with sphere, you're always going to get these sine squared theta plus cosine squared theta. This is equal to 1. And this is, next one is going to be, well, this is the second derivative there. The second partial derivative of f in terms of theta. Like this. All right, so we got that. And let's just erase all this. Because it's, we got them. I'll only keep the crossing out ones because that's what we need. Now the last one is this. What happens here? So we have a negative sine over r. And then this will be positive sine. So negative, we'll have a positive sine, cosine. Yeah, sine, cosine, positive, and then divided by r squared. And then this is partial f over partial theta. And let's see where this matches up with. Yeah, so we need to find this partial f over partial theta where it's not crossed out. And that's right here. So we have a negative sine, and then to be positive. So this will be positive sine cosine over r squared. This r multiplies. Now we have this one here, sine theta. Times it by, this would be negative, and this would be sine cosine negative, and then divided by r squared, and this is this is partial f over partial theta. So in other words, this cancels. So we found one. These are exactly the same, but it's a negative sign. This is the top one's positive. So this cancels with this. Yes, and there's nothing else. We went over all these. There's nothing else we haven't covered here. So we included this part here, is already included. This is the f over r is already included in here, and this one here is already included. So we've already included everything. So what I'll do is, yeah, I don't need to circle anything else. So that's canceled. So we're just left with, yeah, so we're left with now, by removing all these ones there, we're going to be left with, yeah, we're going to be left with, I'm going to write this one in the first one. So we're going to be partial, and I'll put this all like this. So thus, we're left with, and I'll put this thingy there. Or instead of that, I'll just put thus. Thus, delta f is equal to, and this is going to, yeah, this is going to equal to, this is going to be this, yeah, this part right here. So we get rid of the ones. So this is partial, second partial derivative of f in terms of r, plus, this is 1 over r now, 1 over r, partial f over partial r. All right, this is fascinating stuff. And then plus 1 over r squared, so 1 over r squared. Second derivative of f in terms of theta. Alrighty, so we have solved it. And here, just fix it up, and yeah, so that is our answer. And then double checking with Wikipedia, we obtained the correct answer. So Wikipedia has it like this partial derivative here, and you can take a partial in there, and then we got it over, then basically solve it out. We get this part right here. So there's two ways you could write it. This one here, partial, yeah, there it is, exactly that. So the partial derivative, the second partial derivative of f in terms of r plus 1 over r, partial f over partial r, and then plus 1 over r squared, and then this is the second derivative of the second partial derivative of f in terms of theta. Absolutely unbelievable. So the amount of the cancellation here, again, it gets symmetry. Again, we're dealing with circles, polar angles, yeah, spherical coordinates, spheres, and so on. We get that. So pretty fascinating stuff. All right, and now that we've solved the Laplacian or the Laplace operator in polar coordinates, now let's take a look at the Laplace operator in spherical coordinates. So now let's determine the Laplacian or Laplace operator in spherical coordinates by first converting rectangular coordinates into spherical coordinates. And again, the polar one, we were dealing with the basically 2 dimensions. Now the spherical, it's 3 dimensions. So if we recall, this one right here, let's go all the way back up here. This is the Laplace operator in polar coordinates, was in 2 dimensions like this. So that's just the x and the y second partial derivatives. And now we're going to be looking at, including the z component. So going from spherical or just from 3D into spherical. So what we have is, here's the Laplacian delta f like this. Yeah, delta f, and you could also write it in this gradient divergence mumbo jumbo. This equals to delta f. This is the second partial derivative in terms of x. This is, just write it down in rectangular coordinates first. Why isn't this writing? No, let's write that better. Okay, this is, I don't know why my pen's not working. Okay, there's x squared, and then plus the second partial derivative in terms of y, so like that, and then plus the second derivative in terms of z. So that is the Laplacian, and setting it equal to 0 is a Laplace equation, but we'll just leave it like that. All right, so we have this. So now what we end up doing is let's first convert the, basically write x and y and z in terms of. All right, so let's draw our 3-dimensional setup. Now we're gonna, it's gonna be similar to our polar coordinates, but now we're doing in 3D. So let's draw the z. This is gonna be our z axis. And all right, that's the z axis. Draw the x axis. It's gonna be like this. All right. That's the x, and now let's do the y. The y should be, let's make it like this. There's the y axis, and let's say we have a point going like this up to here. And that's a point, and now we're going to give it a polar coordinates, r, theta, phi. So r is the radial distance. That's going to be r to, from the origin. And now the theta, that's a polar angle from the z-axis. So that's a polar angle. And then the phi is the azimuthal angle, or however you pronounce it, goes all the way down to the bottom. And now this is the horizontal distance to this right here. And this is a right angle like that. And I'm going to call, this azimuthal angle is phi. And I'm going to put this s. This distance is s. So that is the distance s. And I'm going to draw this parallel line as well, to all the way across here. So it's going to draw a parallel line across here as well. And this is a right angle. It's the same thing here, right angle, this is s. So that's s, that's s. And what we get from here is, well, s is equal to, this equals to, well, we know this is, there's r, there's hypotenuse, there's our s, there's our theta. Well, we know that using basic trigonometry. This equals to sine theta is equal to s over r. So move the r to the other side. This equals to r sine theta, like that. So that is very, very fascinating stuff there. All right, so now that we have that, the next setup is, we have this distance here. So this distance from here to here, this is our y component. This is going to be, using, again, basic trigonometry. this is the sine of phi. So let's do the sine of phi. Let's try that again. So sine of phi, this equals to, well, opposite over hypotenuse over s. Move that over there, so we get y is equal to s sine phi, like that. So s and sine. And this is going to be important to use this, because we're going to use the Laplacian and polar coordinates twice. Alright, and now let's get the x component. X component is going to be over here. That's the same thing as over here. X, you could put it over there, or x here. This equals to, well, now cosine, using basic trigonometry. Cosine phi equals to adjacent over hypotenuse over s. Whoops. No, we got this. Now we move this s over to this side. This is going to be s times cosine of phi, like that. And now lastly, we just need the z component. This is a z component here. And I'm going to put a z over here, like that. And that's because z, well, we look at the adjacent now. So if we take the cosine, or I'll put it actually here, cosine of theta, this equals to, this is the top one, equals to z over r. So move this over to this side. So now z is equal to r times cosine theta. So keep that in mind. There's theta and there's phi. So we got that. We have a lot of stuff now. So what I'm going to do is I'm going to write two sets of equations. Let's say we have x, because we're going to use this as well. So x equals to s cosine theta when we do the using the Laplacian polar coordinates for our proof in spherical coordinates. So that is s cosine phi. That's that. And then we have y is equal to s sine phi. And now the last one is s right here is equal to r sine phi. S is equal to r sine, sine theta, So sine theta. So now that's how we connect theta and phi. And lastly, we have s right here. Well, we know s in terms of using Pythagorean identity, Pythagorean theorem, x squared plus y squared equals s squared. So we get s is equal to, and now we'll just square root it. I'll just do the square root. So we know the length of s is actually just x squared plus y squared. Yeah, that's the s. That's the horizontal distance up to here. Again, that's using Pythagorean theorem. And now we're going to put a line like this. So that is, we're going to use these. And what we'll actually do is we're going to actually use the Laplacian on polar coordinates on this plane and on this plane. So that's going to, because if we have the phi and we have a thigh, I'm going to undo all this and see what happens. Okay, one more. Yeah, we got that. Okay. And let's go back here. And now we have, just plug in our s. S is equals to, well, r sine theta. So we have x is, and then we'll include the z as well. So x equals 2. Now this is in 2D. And the other one is the 3D setup. So we have s is equal to r sine theta. But I'm going to put the sine theta afterwards. So I'm going to go cosine phi. And then put this right here, sine theta. Yeah, sine theta. And then the next one's going to be y is equal to r sine phi. And then sine theta. Sine theta like this. Oops, why isn't it writing? I hate when it doesn't write. Alright, yeah, it's working again. So sine theta. Oh, it just stopped working. Okay. Well, let's try it again. Okay, there it is. Okay, there's phi, theta. Now we have z is equal to, well, z is equal to r cosine theta. R, put a dot, cosine theta, like that. And lastly, r, and the distance is going to be, well, equals to, now in 3D, x squared plus y squared plus z squared. So we got this all. And I'll recall the earlier formula that I proved for basically Pythagorean theorem in 3D, or distance formula in 3D, and this is 2D, this is 3D. And so yeah, you can see the parallels of that. Alright, now we have this. I just want to quickly recap on the distance formula in 3D and 2D from earlier video. Here's distance formula in 3D. Distance between P1 and P2 right here. is just going to be equal to, well, yeah, this right here, square root of the difference in the components x, y, and z. But in our case, since it's going from the origin, the x1 is 0. So these are all 0, and then all squared. So squared, then all square root. So we just get these setups right here. R equals square root x squared plus y squared plus z squared. And then in 2D, the z's all just are 0. So those vanish. All right, so now we will apply the Laplacian in polar coordinates twice to find the Laplacian in spherical coordinates, once for the x, y terms and once for the z, s terms, as I explained earlier. So here's the x, y terms, this one here. Yeah, this right here. So this is the x, y terms, and there is the, this is going to be z, s terms, like that. So we have those two. There's the angle, and there's the polar angle. Yeah, this would be the polar angle, and this would be the polar angle, and the horizontal side. The azimuth one, basically we take it in 2 dimensions. This will be our new r, and for this case, in this one we have r and z and so on. So let's do it for the x, y component first. But before that, let's find the polar. Yeah, so let's get the Laplacian in polar, not polar. Okay, so let's just copy this. So we have the Laplacian like that. So let's just put this, and we're going to apply this twice. All right, so let's take a look at the bottom part there. So if we look at just this bottom section here, x and s, what we get is, I'll just look at it like this. So this is our x, this is our y, and then we have, this is going to be our s now. This is our horizontal distance s, and this is the origin. And now we have the azimuthal angle phi, and now I'll move it like this actually. I'll move it a bit better like this. So then this is the distance here. This is the distance y. I'll move it across even further. I'll drag this across. This is our point. And here I just quickly fix that up. So this is our y, this is our x, and this is our azimuthal angle. But now it's going to be our polar for this specific case. And this is the distance s. And this is going to be our x, like that. All right, so for this case number, we know x is equal to s cosine, cosine phi. And then again, we have x equals cosine phi right here. S cosine phi, then y is s equals sine phi. And then we have y equals to s sine phi, again, just opposite over hypotenuse, sine phi. For this, what we end up having, well, in this case, we're going to have our s is equivalent to r for this formula, for all these formulas. And then our theta is going to be phi. So basically, and phi is equivalent to, but the 3 dots is for equivalent, we're going to replace this with that. So we're going to replace this with it and get our setup. All right, so we take the Laplacian now in terms of x and y, so we get the Laplacian of f equals to, this is the second derivative of f in terms of, this is going to be x, like that, of s, and plus second derivative of f in terms of y, so this is the second derivative. This equals to, well, this equals this entire thing. So I'll copy this whole thing, copy. So this equals to, I'll just paste it here. I'll just put it maybe at the bottom or maybe up top. I'll just put it here. Actually, I'll put it here. This equals to this whole setup. There's a partial. And here quickly just added the partial, fix it up, move it over here. But now we have to replace all these terms. So we replace the s. This is this part right here. And replace the r with an s. Replace this with an s. Places with an s, and replace the s, and here this is going to be phi now, and it's going to be s, like that. So that is our Laplace operator in polar coordinates for this x, for this xy triangle, or that point, like that. All right, so now that we have this, and likewise for the zs term. So this is the xy term. This is part at the bottom. Now we're doing this part right here. This is the zs term. So let's just draw that out for completeness. we're going to get a setup that looks like this. This is in 3D, just because it's dealing with that. But this is the y, and so we have the point going all the way across here. And then this is our angle. This is our theta. There's our z. And now this distance is going to be, this is our z axis. This is going to go all the way across there. This is our s. Like that. So that's pretty much, yeah, what we have there. And yeah, let's make it look like it's 3D. Like that. All right, so there's s. And that's what's connecting the two is the s. All right, so we got this, and we know that, well, z, again, z using just, we already solved it before, this is right angle. This is just cosine, this is r right there, r cosine theta, as we solved earlier. This is r cosine theta, and again, just using basic trigonometry. It's going to be adjacent over hypotenuse, move the r. And then likewise, the s is equal to the sine of that. So r sine theta. Like that. So we have that. And likewise, we're going to take this entire setup here. I'm going to just copy this. Yeah, this entire Laplacian. I'm going to go right here. This is the polar coordinates one. So I'm going to paste this in here. And now, in this case, it's instead of this one, we had the s is equivalent to r, phi is equivalent to theta. Now we have basically this z is equivalent to x, and then s is equivalent to y, just in the equation. So basically, we have to replace this with z, yeah, I should replace with the z. Replace with the z. So this one's replaced with z. Let's write this better. Whoops. Okay, one more time. I don't know why my... Let's try this again, yeah. I'm going to need a new Surface Pro. And then this is going to be, remove the y. This is going to be s. And now these ones, well, this is, because we're dealing with r and theta, we could just use the original formula. So we don't even need to switch those up. Just use the original formula. This one had those exact same setups. All right, just highlight that. Just move it over here and just paste it nicely. And move this over. So this goes here. And shrink it a tiny bit. Yeah, so there is our two Laplacians setups. All right, now that we have these, I'm just going to put this right here, F1. Yes, this is basically, because this one's dealing with R and theta, so we don't need to change anything. I'm going to call this actually F2, or just the second one. This is Laplacian 1, just because we're doing, yeah, there's two of these, and we're going to add these up and do a whole bunch of magical stuff. All right, and adding these together, and we can see the why we want to add those. Well, if we look at this delta F1, or the Laplacian of the xy, well, we have this term. This is the second partial derivative of f in terms of s, and this one matches up with, well, this one here. So if we just equate them, we'll have one side with this, so we can actually cancel stuff out. So we're going to have a delta f1, or just put this Laplacian of f2. This equals 2, so this is the second partial derivative, is the x and y. So second partial derivative of f in terms of x plus second partial derivative of f in terms of y, and then plus this one right here, the z and s, and then it's going to be z plus the second partial derivative of f in terms of s, like that. All right, so now we have this. This equals 2. Let's just add these together. I'm just going to copy and paste this whole thing. And then paste it over to the other side. So we copied it right here. That's F1, like this. And what I'll do is actually, I'm just going to, I was thinking maybe should I make it, no, actually, no, yeah, this is fine. Yeah, we accidentally added this as well. So we're going to erase this. I'm going to erase that. So this equals 2. I'll move this here. So move it over here. And I'll make it a bit smaller. So there it is. And now this is going to be plus. Now this is the F2 one here. So there it is. And copy and paste. Move it over here and fit this all in nicely. Yeah, so we have all this. And yeah, just fit this all in properly. Yeah, so we have all this. So those are the two. And now notice what we have is this is going to be our left side. This cancels with this one. There's our, yeah, so now we got rid of that one. So we pretty much have everything, but we want to get rid of the S terms. Well, we have S. We can easily write that S in terms of, well, r sine theta. So we already know that. So we know S equals r sine theta, but then the only thing that we need to change is this one here. So delta, I mean, this is a second, or the first partial derivative of f in terms of s. So we just need to get that out of there, and we can get our Laplacian. Because now we can basically have our Laplacian here. There it is. This is the Laplacian of, I mean, this is the second derivative, second partial derivative of f in terms of x, and in terms of y in terms of z. And that is our Laplacian in spherical coordinates. So we got rid of this one. Now we just got to determine this right here. Alright, so what we can do here is, well, we could use the chain rule in our tree structure setup thingy as before. So I'm going to circle this so that we know that's what we need to solve. And we're going to go over here. I'm going to circle this actually. Now, so S is a function of R and theta, but it's not a function of phi. Remember, phi is here. But it doesn't matter what phi is. You can have S doesn't change. It just becomes a circle. It just becomes a giant circle, and it's all S is constant. So in other words, phi, it's not a function of it. So what I'll do is I'll draw our tree structure. First, I'm going to write S. I'm going to put S equals to, I'm going to first actually put tree structure. Tree structure or chain rule, etc. Basically, we have our F is a function of, well, we know that's R, theta and phi, and then we have r as a function of s, and then theta as a function of s, but this one is not a function of it, so we can just ignore that. And we could see that this right here, well, r is a function of s. We could easily say from here, this is s equals a function of r, so that means also r is a function of s. Likewise for theta, but also if we go over here, so r, so remember, s is equals to this part right here. So in other words, the first half is just s. So in other words, this inside here is just s squared. Yeah, so that is a function of, I'll just put that like this. Yeah, so r is a function of s, and then we also have, yeah, the theta. I'll just rearrange it, and you'll have our, yeah, we'll have our function of s there. Anyways, so what we have here now is, so now if we take this delta, I mean, the partial derivative of f in terms of s, we're going to get a partial f over partial s, and then using, again, chain rule. And then change, so that's our tree structure, there's our chain rule now. We're going to get partial f over partial s equals to, well, it's just going to be partial, yeah, partial using our chain, this one here, we're going to get these two paths. We could go over this side as well, and then, but then just show that it's 0, so it doesn't change anything. So this becomes partial f over partial r, and then times it by partial r, or partial s, and then plus partial f over partial theta, times it by partial theta over partial s. And lastly, this is going to be, well, partial theta, partial f, I'll move it over, and I'll shrink it over. Partial theta times it by partial theta, phi, partial phi, over partial s. Now this one here is just 0. Yeah, and this is, again, this is 0 because s is a function of r and theta, not phi. So that is that. Yeah, and yeah, keep going further. And also here I'm going to write s equals that. Well, it's also equal to, just put it for completeness, equals to r sine theta. So that's what it equals to, r sine theta. So that's what s is equal to. All right, so the next setup is, well, we gotta get rid of these partial s's though for our Laplacian and spherical coordinates. So we're gonna get rid of, we have to just convert this one and this one here. So these are the two we want to convert. So I'll put a 1 right here. and then 2. So for the first one, well, we know that this is partial r, partial s. So we know that r is equal to, and then in terms of x, y, that's this part right here. This whole thing right there. Square root x squared plus y squared. Square root x squared plus y squared plus s squared. Plus z squared. And then x plus y squared is just s squared. Let's write this down. Okay, this is z. And then this is going to be equal to square root s squared plus z squared. So what this means is, well, the partial r over partial s is going to equal to, well, this is going to be square root s is 1 over 2. Bring it down, and then we're going to have at the bottom like that. It's going to be a square root s squared plus z squared. This is in terms of s, and then z, leave that constant, just constant. And then we're going to take this derivative inside using chain rule, 2s. So this cancels. Yeah, we're left with, and also this part right here, this is just the top. This is just this. That's just r. So this equals to r. So in other words, we get the 2's cancel, we get an equal to s over r. So that is one thing we get. So we get rid of this partial s, so we just got s over r. Now the next one is this 2, 1 there, so I'll write 2. This is going to be for this partial theta over partial s. So we have to get that. Yeah, so for this one, well, we got to get this one in terms of s. Well, what we can do is note that we know that s is equal to r sine, it's r sine theta. So r sine theta. And we know that z, so if you go back to what z was, z right here, yeah, z is equals to r cosine theta. So we take the, and the reason we do this, we're going to cancel the r's. And then z is equal to r cosine theta. So now we can even simplify it further. So what we'll get is a s over z equals to r sine theta over r cosine theta, which equals to, these cancel. This equals to, well, yeah, this is going to equal to tan theta. So in other words, we get a, we're going to get a theta is equal to inverse, this is going to be tan, inverse tan or arctan of z over s. S over z. So that is what this one equals to. Yeah, so thus the derivative, and here's quickly move it over here. So thus the partial derivative of theta over s, and then keep z constant. This equals to, well, we already solved this way back. I'm just going to scroll all the way back up. Yeah, and here I quickly teleported here. So remember this one. This is the same formula we had before. And so derivative of the inverse tan of x is going to be 1 over x squared. Well, 1 over 1 plus x squared. So if we go all the way back here, what this means is this is going to equal to 1 over, it's going to be 1 over 1 plus, and then this whole thing squared, s over z squared. And then we have to use chain rule, so the derivative of s is just 1. It's just going to be multiply 1 over z. And then as before, multiply top and bottom by z, so we have a z squared at the bottom. And then multiply that in, so we have a z squared, just 1. That's afterwards, okay? And then we have, this is going to be z squared, and multiply this out, the z squared cancels in the bottom, and we have a z squared there, and at the top is just z. So then this equals to z over the z squared plus, and now this is going to be s squared. Yeah, and then that's, that is it, because those combine. And now what is z squared plus s squared? This is just going to be r squared. Yeah, remember that's just r squared. Remember z squared plus s squared plus z squared, and then square the whole thing. That's just we'll get r squared. So get rid of those. So then that is r squared, but also z. We know z is equal to this right here, equals to r cosine theta. So this equals to r cosine theta over r squared. In other words, this equals to cosine theta over r. So now we got rid of these partial s's there. All right, so thus what we have is, thus, our giant, this part here, so this is this right here, this whole thingy, and we'll get rid of that 0 there. Or actually I'll just copy and paste the whole thing, and this, just for completeness, paste is right here. So this whole setup, so thus this part right here, and then remove these. This equals to, it's partial f over partial s, and again that is used for this right here. So that is this whole part, and then we're going to throw this all in here and then get our Laplacian and rearrange and do a whole bunch of stuff like that. So this is going to equal to, well, we're going to have this partial f over partial r, put that in the side. This first one's going to be here. S over r is now partial r over partial s. So we have s over r, and then we have this partial f over partial r. And then plus, and then remember this one goes to 0, so we don't really care about this one. This is going to be cosine, this is going to be partial theta over partial s, so partial theta over partial s. So it's going to be cosine theta over r. Right here is added, yeah, cosine theta over r, and then partial f over partial theta. Yeah, so that is some fascinating stuff. And then the other part just vanishes. So that is what we have. Alright, so thus our Laplacian, or Laplace operator in spherical coordinates becomes, and basically we're going to put all this together. So we're going to take this, these terms, throw that inside where, well, this is equal to partial f over partial s. Throw that inside, inside here. And then basically, yeah, we have this already canceled, and then basically we obtain, and then just simplify the terms, and we obtain our Laplacian in spherical coordinates. That's this whole giant thing there. So what I'll do is, just to make it easier, because we have this ability on OneNote and this Surface Pro, so I'm going to copy this whole thing and then just go from there. So this would be, I'll just paste this here. So we pasted this here. So what happens is, now what we'll do is, well, this is gone. This is gone. Erase this. I'm going to keep the circle there. And then this is going to be just general Laplacian. So delta f, just general Laplacian, which equals to the second partial derivative of f in terms of x, and then added to the y1s and z1s. And that is what we get. All right, so we have is, I'm going to put this equal sign here. So this equals to, and I'll move this over to the left, maybe make it somewhere around there, and put an equal sign here. Or just put it like this. There's our equal sign. Okay, so there's our equal sign. This equals all this. And then I'll do is a copy and paste is the same thing. And again, I have this circled, this partial f over partial s, because we can throw that in there. So we'll put this all in here. So this becomes here. So this equals to this. And what I'll do is I'll move this over. Yeah, I'll move this a bit better like this. Well, actually, or delete this. Yeah, so we're gonna actually, this thing gets deleted, and then move this all the way over to the right. All right, so then we have that. I'll put this actually better. This equals to, yeah, this equals to 1 over s. Make this a bit smaller. 1 over s, and now we have this whole term. So we're gonna copy and paste this thing inside. Right, so that becomes in here. So that is what, I'll move it over here. Make this s a bit neater, and then put a bracket. So that is this whole part. That gets over there, and then move this over. Yeah, this whole giant thingy inside. All right. Oh, here, just quickly zoomed out. I don't know why it's not working properly. Okay, move it over. And yeah, that's what we have. And I'm gonna shrink everything. All right, here I quickly pause the video and just move everything around and shrunk it. So we have all this. And now the next step is, well, we could just expend it all and see what we obtain. And I'll put this in the order that we want. Typically it's written. So we have this one here by itself. Yeah, this right here. So this one, we'll put that first. this equals to partial, the second partial derivative of f in terms of r. So put that first, that's for the r. And now the next setup is, well, if you multiply this 1 over s over here, this s would cancel. So when we multiply that inside, yeah, so that would cancel. I'll put a cancel like this, and then we have this 1 over r, partial f over partial r, and that's all. We also have another 1 over f. 1 over r partial f partial. So in other words, we can combine these two. Yeah, so this one here, I'll put a combine those two. So this equals 2 plus, that'll be just 2 over r partial f. And the reason I'm doing that first is because we want to get all the r terms. This is all the r derivatives, I mean. This is all the partial derivatives in terms of r. Put that all over there first, and there's none else. All right, so the next one is get the theta, just because typically it's r theta phi. So we'll get this one here. So this one just write it by itself. So yeah, we don't do anything special with this one. So this is going to equal to plus 1 over r squared partial f over partial theta squared, like that. That's the second derivative. And now we get the other term. It's this one right here. So that's that part. And that's going to be, well, we'll multiply this inside 1 over s, this cosine theta over r. Well, let's just write that out. This is going to be, this part. I'll circle this. Actually, I'll not circle these just so that it's easier, because it's hard to see what's going on. So these parts right here, I'll put a line underneath the ones that we've covered. Okay, so now this one is going to be cosine theta over SR. Well, we know that S, go back here, S is, we already know that S is equal to R sine theta. So that's what S equals to, and we have it circled here. S equals R sine theta. So in other words, this just equals to R squared. So now there's an R already, so R squared sine theta. And this is, again, is just S times R. That's S times R. And now we add the other term, that's this right here, partial f over partial theta, like that. All right, and here's move things over, and now we just add the last term, and then I'll have to shrink everything, make it fit. And the last term is just this part here. I'll just, there's not enough time to circle, I'll just put that there. This is the last term, this is the phi, so that's going to be just put itself, and then S, again, S is just R sine theta, so we're just going to write this as 1 over R squared sine squared theta. Phi. Yeah, actually, no, that's theta. And now we have the second partial derivative of f in terms of phi. And then put a square like that. All right, then here's moved it over, and now this part here just equals to this is just s squared. All right, that's just s squared. All right, so this is this is our Laplacian. We pretty much have it, but typically we'll simplify it a bit just so it matches up with Wikipedia. So this is equal to, and I'll just put a or. I'll just put this. I'll just put another equal. I'll just put it like that. Or, now let's do or. Because it's it's still a Laplacian, but just to simplify it slightly more, we're gonna get partial, this partial squared. The second partial derivative of f, or in terms of r, and then plus. Well, we'll keep this 2 over r, so to keep the first one, 2 over r partial f over partial r. Let's write this neater, partial f over partial r, and then plus this part. Yeah, now this theta terms. So typically what the calculus book for some reason does this way. So this part right here, what it does is, also I'll just put a line like that. This equals, actually I'll just ignore it, it's pretty obvious. So for the theta terms, it takes out a 1 over r squared sine theta. So it does that, but it also writes this one first. So then we take out a r squared sine theta, so as a bracket, and now this one's gone. So this is gone, and now it just puts a sine theta on top, so that it is there. So what we get is a, actually no, we don't get a sine theta there. I mean over here. So this is the first one. It puts this first now. It writes that first. So we have this cosine, and then we get rid of this r. We factor that r squared sine theta. So we're going to get a cosine theta, and then partial f over partial theta. So now this is the term where r goes away. So it put yeah, that's just because it does it afterwards for some reason. Anyways, I was trying to match with Wikipedia. This is going to be now now we put a sign, so that when you multiply this inside, you're going to get 1 divided by r squared, and then sines thetas cancel. So we're going to get this. All right, so that's what we get, and then this is going to be sine this partial f. And it's a second partial derivative of f in terms of theta. So like that. And then lastly, we add our last term. So this is going to be now 1 over r squared sine squared theta, and then partial f over partial phi squared. Put this phi a bit better. Like that. All right, so I yeah, shrunk it all in there and then fit it all in. Now we're going to box this whole thing in. And this is our formula. So there's our Laplacian. And yeah, so now double checking with Wikipedia, we obtained the correct answer, which lines up with the third variation of the formula, which is quite astonishing. So we could write it like this, and then this one is, they haven't done the partial derivative yet on this one here. So if you take the partial derivative of this one, remember using chain rule, take the derivative of one of them, and then yeah, partial derivative of this one here, and then leave the other one constant. So remember, that's going to be, well, this will be the second partial derivative, and then this one here will cancel with this. We get this part. Yeah, so anyways, you could derive that, and so on. You could go on. But anyways, we get the third variation is on Wikipedia, and this is exactly this one here. So you can look at it. Partials, the first one is I'll zoom out a tiny bit so you can see them both side by side. So they're side by side. So this is the second partial derivative of f in terms of r. There it is, and there's a 2 over r. There's a 2 over r. There's partial f over partial r, partial f over partial r. 1 divided by r squared sine theta, and then we have this cosine, and so on. And there's the partial f over partial theta. Sine theta, second partial derivative of f in terms of theta. And then you have a squared there. 1 over r squared sine squared, and then this one here. Oh, we forgot this part here. There it is. Yeah, that's this one right here. So I forgot the squared. Anyways, oh, I think I probably did. I probably just accidentally deleted. But anyways, there's the second partial derivative of f in terms of phi. Like that. So absolutely fascinating stuff. All right, and now that we've solved the Laplacian or Laplace operator in spherical coordinates, now we could well, find solutions to them, and those are called solid spherical harmonics. And again, there are solutions to the Laplace equation in spherical harmonics. So solid spherical harmonics are the solutions to the Laplace equation in spherical harmonics. Oh, it's good that I emphasize that. And then I say solid because it includes the radial term, like these r's there, so that even though solutions are in a sphere, but the r changes. So the r, you can have it. So basically, it's a solid. It goes within and without. Basically, the r is going to vary. So it's going to be basically if you have a sphere, it's the entire solid in and out. That's what its solutions are for. And regular spherical harmonics are just on the sphere, where you basically set r equals to 1, essentially. Now, but these are the general solutions. So anyways, so Laplace equation is just the Laplace operator or Laplacian set to equal 0. So all you do is take this and just set equals 0. So that's the Laplace equation. And you're dealing with harmonics, because when it's equal to 0, it's in harmony, and nothing's in and out. It's just always equal to 0. So that is that. So from the Laplacian and spherical coordinates, r theta phi, we can write Laplace equation as follows, and that's just basically this. I'm just going to copy our solution. So there's our solution. So we could write it. First, I'm going to write this down using the Laplacian delta f sign. Also equals using this inverted nabla sign, or inverted triangle. It's the same thing as writing that, and this equals to 0. So in other words, we get is this giant formula right here. This right here equals to, or actually I'll make this better. I'll move it down a bit. Yeah, this equals to 0. Yeah, so this whole thing. I'll put it like that. I'll just put it like that. Yeah, so that is what we get. So this whole thing equals to 0. And again, recall the spherical harmonics, just because I'll be uploading this in sections, so might as well just refresh it as well, because this video is pretty giant. So there's the XY axis, this is the Z, and then we have an R like this. This is our distance, and this is the theta. And now if this goes down like that, that is going to be our horizontal distance. And this is the angle phi, and this is r theta phi, like that. And this is right angle triangle. And also recall that again from above, x is equal to r cosine phi sine theta. Y is equal to r sine phi sine theta. Z is equal to, Z is just going to equal to, you look at this right here, r cosine theta. And then r is equal to square root, just the distance formula, x squared plus y squared plus z squared. Yeah, so that's what we have there. And again, we have it all the way, when I derived this right here, we already went over this. I'll scroll all the way back up. Yeah, so I already solved these ones for x, y, z, and r. So those are it. And there's the derivations. You could watch that earlier in the video or in the separate video on Laplacian in spherical coordinates, which I'll upload as a separate video after I upload all these, after I finish this video, and so on. Yeah, so that's what we have. Alright, and now that we have basically this Laplacian, the next step is we can apply the separation of variables to obtain, and basically we're going to try to find our function f, and we're going to assume that f can be written as a multiplication of three functions, that e of function of, this is a phi, times it by p is a function of theta, and r, capital R is a function of r. So we're assuming that that the function f could be written like this, and then I'm using the terminology in the YouTube channel, the Mike guy on YouTube uses this terminology. I'll just follow that along. All right, so we have that. Now the next step is get our Laplacian in spherical coordinates. So I'm going to copy this. I'm going to go right here, paste. All right, so I'm going to move it like this. This is going to be paste here. All right, so we have this, and now the next step is, well, actually, before I even do that, I'm going to make it smaller. So make it smaller, and then multiply both sides by r. So, or anyways, so now we're going to multiply this by r squared. Yeah, so do that. All right, so if we multiply this out, we're going to get some cancellations here. The r squareds cancel. That's why we're doing that. And this will cancel. We'll just have a left an r there, and this one's going to be an r squared there. So in other words, we're going to get, so this becomes, we're going to get an r squared as the first one, so r squared. And now instead of writing partial derivative, second partial derivative of f in terms of r, well, yeah, this right here, well, we'll just put the f inside. This just is the same thing, because these are functions, these are just functions of phi and theta. So that means that if we take the second derivative of f as in terms of r, so second partial derivative, these ones aren't included. So this just equals to, and I'll put our f now. This is going to be, our f is going to be equal to e times p times by r double prime. So this is just a, this is just a second derivative of r there multiplied by these. These are treated as constants when we're taking partial derivative of f in terms of r. So we just set the other ones as constant. So I'll put this r like that. So that is what that equals to. And now this part here, we're going to get a plus 2. And this is the first partial derivative of f in terms of r. That's just r prime. So this 2r r prime. And actually, I just don't make a mistake. So it's going to be e times p. Yeah, so e times p times r prime. Because those are, again, we have to include those constants for that partial derivative. Yeah, so they're not actually constants, but they only are when you take the partial derivative. So now, the next setup, this one's gone. So we're going to have a plus a 1 over sine theta. 1 over sine, and also before we go further, so the guy on YouTube, yeah, he does it this way. So first, so we would, instead of using this way, we'll take out, write it as the form partial partial of derivative over partial theta of, and this would just be sine theta partial f over partial theta. And you can see this is the case because this is just chain rule. So take the chain rule. So derivative of sine is going to be cosine theta, then times by partial f over partial theta, and then plus sine times derivative of this right here. It's going to be the second partial derivative of f in terms of theta there. And again, that's just, again, if you go back to the Wikipedia setup here, so this giant thingy, same thing as this, partial over partial theta of sine theta, partial f over partial theta, like that. All right, and so the reason they do this, well, the YouTube channel did this, the Mike guy, it's just it's a bit simpler. So you have less f over there. So now we're gonna get a, now it's gonna be sine theta, and then times it by this one is the partial derivative of f over partial, yeah, this is basically partial derivative of f over partial theta. That's just gonna be the derivative here. We're gonna write now e. And then EP prime. So we're going to get a times by E P prime times by R. So those are the constants now. The P is a derivative there, as opposed to the R, like that. And yeah, we're at the partial derivative, so this will move it over. I'll move this over here. So this is going to be, and I'll put a square bracket. We're gonna, because we need to include this part right here. So that's going to be partial over partial theta of this, like that. Yeah, actually we don't need to do a squared bracket, but we'll just keep it like that. Yeah, I thought we were gonna use the second one anyway. So that's what that is. And then the last one is this part right here. That's just going to be plus, put them all in here and I'll shrink it. Yeah, this one's going to be, let's put a plus like that. This is 1 over sine squared theta. And now this is the second derivative, so everything else constant. This is of the phi, so that just equals to E phi double prime, and then we have PR. And then the whole thing is equal to 0. Like that. Alright, so here's just shrunk it, and we have it all over here. So now the next step is, then this is gonna be like this. What I'll do is, I'll put it like this. Next step is gonna be, well, we're gonna divide every single thing out by P. I'm just gonna, instead of putting it there, I'm gonna put it like the whole thing. Actually, I'll just do it over here. So now we multiply the whole thing by 1 over E, EPR. So we get a fractions on each thing, and we cancel out all these extra terms. So that's why we do that. And here it's quickly shrunk everything in here. So we have all that. So then this ends up equaling to, so we're gonna get an R squared, and then EP cancels. So then these cancels with this. So again, that's the whole idea. Is you just cancel everything out. So we're going to get an EP, E dot P, and then over R. Yeah, this is EP. No, EP is canceled. Yeah, I mean it's cancelled. So we're going to get an R prime, and then over R. So R is not cancelled, so we have that over there. So R over R. And then likewise, we're going to get an R, 2R squared, EP, R. So basically all the ones that the R is not there, so EP is gone. So we get an R prime over R. Yeah, this is over R, so in other words, we can combine these are EP, those cancel, put these all together actually. So this will be a plus 2R, R prime over R. And now the next setup is going to be 1 over sine theta. And then we have, yeah, it's 1 over sine theta, and then this one here, these are constants, so it doesn't matter, we could take those out. The EP is our constants. And then those cancel out. They're constants within this partial derivative. So those just cancel out. We're going to get a partial over partial theta of sine theta, and then E. No, E's gone, so now we just have a P prime. And then the only thing divided by is going to be this P, like that. Yeah, just divide out the whole thing there. We just put it over everything. Like this, over P. That. Alright, here's fix that up, and then lastly we're going to get a plus, this one right here, 1 over sine squared theta, and now this one here, the E, the P's are, those are gone, so we're just going to get an E double prime over E, like that. Just put it like that. Alright, so that's what we have. We could, yeah, divide it out or just leave it like that. So anyways, E. double prime, and this whole thing equals to 0. Yeah, because then when we multiply the 0, 1 doesn't change anything, so just 0. Alright, and here I just shrunk it, move it over all into one line here. So now the next step is, well, we can now set the equations equal to their corresponding separation constants. And again, these all equal to 0. So in other words, these are the E functions are in here, there's the P ones in here, and this R ones are in there. So yeah, these are 3 separated functions, but they all equal 0 at all times. In other words, these are all equal constants. So this one's a constant, etc. This one's a constant, this one's a constant, these are all C1, also C2, etc. So these are all constants. So in other words, we can just set these all equal to their own corresponding separation constants. And to ensure a periodic solution with the middle function to be set as the difference between the constants, thus ensuring the overall equation sums 0. So basically we just choose this one as a constant, this one as a constant, and this one as the difference. Yeah, and then this one's as the difference between the two. All right, and the constants typically picked like this. So for the first one, we'll look at this part right here. So we'll just look at the, in this one here's, this one typically is written just like these two parts right here. So we'll ignore the sign squared for now. So basically this one is written like this, E double prime of E. And this one is, these are both functions of phi, remember that. So E is a function of phi, going back here. So E is a function of phi. And then this is over function of phi. Yeah, so now this one's equal to negative m squared, and we'll go over that in a bit. And now the next one is this part right here. So this whole setup is, this is going to equal to r squared, r prime, and this is going to be, again, it's function of r. I'll split them all just for completeness. And then plus 2r, and then this is going to be r. Yeah, r prime. The other one's r double prime, and this is going to be a function of r divided by r, and this, for completeness, is function of r. And now this equals to the function that this one's set up as is equal to n, and then n plus 1. And the reason is so we get the associated Legendre function. Yeah. All right. We'll explain this in a bit. All right. All right, here it's quickly shrunk that in. So if we have these set to these constants, and then this one here is going to be the difference between the two, or just, yeah, this one equals to the negative of that. Yeah, so that equals to, let's put this whole thing there. Actually, I'll just copy and paste the whole thing. And just leave it like that. So I'm going to copy this, paste there. Yeah, this one here. And move it here. Yeah, so this one here, this just equals to the negative of those. So it's going to be equal to, so it's a negative, well, we'll put this negative here, there first. So we'll take the n plus 1. So put a negative n plus 1. And then the next one's going to be, well, minus, but it needs to all equal 0, so we have to include this 1 over sine squared, because this one is the negative m. So basically, it's going to be negative m, but then we're negating that, so it's going to be, well, positive m. Positive m squared over sine squared, like that, sine squared theta. All right, so we have that. So thus, and again, the reason is so that thus we'll have on this left side here is going to be n plus 1. So this is so they all equal to 0. N plus 1. Now we're going to have the middle term is going to be negative n plus 1, then plus m squared over sine squared theta. So again, this is the middle term, like that. Let's put it like this. I'll just leave it like that. This is the middle one, and then the last one is just going to be this part right here, 1 over sine squared, and be minus, because this one is going to be negative m squared. So that's going to be negative m squared. So negative m squared over sine squared. Yeah, so it equals 0. So again, these cancel, these cancel. So again, that's the whole idea. That's the whole idea of it. All right, so now we have this, just to go over some notes here, so, and also solving all of this equation. So the first constant, negative m squared, where m is an integer, is selected such that we have a periodic solution. So this one right here. So if we take this and write it down, so if we have e to the phi over e double prime of phi, the second derivative, over phi, I mean e to the phi equals to negative m squared. What happens here now, we could write this as, we'll multiply this over to this side, and then drag it over. What we end up having is move it there, then drag it over. We get an equation like this. We have an E double prime. So we have, again, partial differential. I think this is, I think it's just a differential equation or whatnot. This is going to be now m squared E phi, E phi. This equals to 0. All right, now the way to solve these, and I haven't done too much of this in my actual video series, but I'll probably do that for later in the future. But nonetheless, to solve this, what we'll do is assume, assume that E of phi, so you can find a solution that's an exponential, equals E to the R phi. So in other words, or actually, instead of using the R, because we already have R for here, I'll just call it A then. E to the A phi. So now if we have the solution is like this, so assume that that is a solution, and we can actually prove that it is, then find A. So we just have to find this this A variable or constant or whatnot. So anyways, all right, so we have this. Well, if we take the derivative of this, derivative E to the E prime of phi, this equals to, well, again, just the derivative of an exponential function is just itself. So it's going to be, well, and also, but then you put the A down. That's afterwards. So this is going to be, well, E to the A phi, and then do the chain rule. Derivative of this A phi is going to be A, like that. Yeah, because the derivative of phi would just be 1, and there's just a constant there. So that is that. Now the second derivative is going to be E double prime of phi. We do the same exact thing. So this is a constant, doesn't change anything. Just leave it A, then E A phi, chain rule, put that down, put the A down, so squared. So that's what we have there. So thus what we get now is, now we'll take this entire thing. So E double prime, double prime of phi, that equals to A squared, like that. So A squared E A phi. And then this one here, m squared E of phi equals 0. Plus m squared, and then we'll have a E to the, this is just going to be, this is E A phi equals 0. All right, now the next step is, well, I'm going to divide both sides. So, and the right side 0 doesn't change anything, E A phi. So then, and what ends up happening is these just cancel. So that's all that happens. So we're gonna get a squared plus m squared equals 0. Yeah. So in other words, we get A. Yeah, A is going to be, well, it's A equals to. This is going to be moving over to the other side. So we're gonna get a negative m squared, and then yes, be square root negative m squared. Yeah. Actually, before we even write that, I'll just write this down. We're going to get an A squared equals to negative m squared. And the only way to do that is using complex numbers. So in other words, we're going to get an A equals to, and then this equals to plus or minus squared. Because again, you can have minus times minus. It's going to be positive, and plus positive times positive is going to be minus. So this is going to be negative m like this. Yeah, this is going to be m squared. Yeah, so in other words, this equals to, well, I'll keep going, plus or minus. Negative 1, yes, negative 1 m. Yeah, this square root, the m squared, just get rid of that. And this is just I. Yeah, this is I equals I. So imaginary number I, which is defined as a square root of negative 1. So in other words, we get A is equal to plus or minus I m. Yeah, so thus we have the solution E of phi, and this is a solution. So E of phi is equal to E, and then this is going to be, this is going to be EA, which is plus or minus. So A is this right here, EA phi. It's going to be E, plus or minus IM phi. So there it is. So we replaced. That's what A equals, and then we just replace this A with IM phi. Yeah, and then with plus or minus IM. So that is the solution. That is actually just one solution, but then, now general solution. General solution is actually a linear combination of the two. Because this is plus or minus, so the general solution is, you can actually, this is a linear combination of this. We're going to get E of phi is equal to I'll put a C1 as a constant, e to the power of positive im phi plus C2 e to the power of negative im phi. So basically you take a linear combination of the two solutions. So that's plus or minus that. And then let me just box this in. So we box this in. So fascinating stuff. All right, so now we have that. Going further, so again, yes, C1 and C2 are constant. So note that the general solution allows for writing every possible solution as a linear combination of two basis functions. And this complex exponential function right here, again, that's complex exponential, are equivalent to trigonometric equations via Euler's formula, as shown in my earlier video when I went over Euler's formula as a matrix. But again, I went over this right here. So Euler's formula, e to the ix, it just equals to cosine x plus I sine x. And then there's Euler's identity, ei pi equals -1. That's when you put in pi in here. This one becomes 1. Whoops. This one becomes 1. This one becomes 0. And then that vanishes. So we get ei. That is pretty fascinating. So anyways, so that's the periodicity for our solution. And again, I'm just diving into why they're using negative m squared as the constant, because the video that Mike on YouTube doesn't actually explain why, and then I had to ask Grok AI for that. Anyway, so that's the periodicity for our solution is, and that's basically converting this into the trigonometric equivalent. So basically, we'll take this EIM like that. Yeah, we'll just take the positive side. So we have, this is going to be phi, e to the phi, capital E to the phi equals to exponential e to the power of im phi. Now this equals to, by Euler's formula, equals cosine x. So it equals cosine. And again, this is ix, so basically m phi. So this equals the cosine of m phi plus, and then this is going to be I sine of m phi. All right, so that's since it's equivalent to the trigonometric setup here. Now we know cosine and sine, they repeat every 2 pi or 360 degrees. So 2 pi radians or 360 degrees. So basically periodic slash repeating, or just repeats. I'll erase this a bit better. And again, it's driving the point why we picked negative m squared. So repeats every, and in this case, it's going to be, well, 2 pi. This whole thing needs to be 2 pi. So we'll have to go 2 pi divided by m. And that's because this thing, to get it to equal to 2 pi, we need phi is equal to 2 pi over m. So that this m cancels. So when you multiply by m, this cancels. So that's what phi is. So basically, it repeats every 2 pi over m. And you can go right here. So 2 pi equals to m phi. So in order for, 2 pi equals to m phi, we need basically phi, to move over the phi to the other side. So phi is equal to 2 pi over m. So every time this, and then you can put an integer, basically it cycles over and over again. So you can multiply this by any number of integers, and so on, and just keeps going, cycling back and forth. So that is that. And you're actually going even further just to drive home the point of this. So the selection of the negative sign negative in negative m squared allows for our specific complex solution, and the squared ensures we get m to be integer values, and thus our solution is periodic about 2 pi or 360 radians right there. I'm going to change this to 2 pi. And here, just quickly change it to pi, so or 360 degrees. And again, that's because phi is the azimuthal angle. So remember this phi is the azimuthal angle. So, and then it goes to full 360. We want a periodic, and it basically get the exact same solution. As you repeat, it should have the exact same solution. Actually, I'll draw that as well, just so we drive home the point here. This is going to be our y, z, x. So basically, any solution, if this is the horizontal distance to the point, we want this phi to be the same thing. So if you have phi, then if you go from here all the way around, if we go all the way around like this, I'll do this setup like this. Yeah, this is going to be phi plus 2 pi. So that's 360 degrees, yeah, 5 plus 2 pi. So we want that, basically we want it equal to the same thing. So in other words, we want e to the phi equals to e to the phi plus 2 pi. So that's what we want. Again, for our spherical harmonics setup. Yeah, so we want those equal. So now if we plug this in, this 2 pi inside our general solution right here, we're going to get a C1, and then e to the, this is going to be negative, yeah, this is going to be I m phi plus 2 pi, like that. And then plus C2 e to the negative I m phi plus 2 pi, like that. All right, and if we go further, if we separate this, we get is a setup like this. This is going to be C1 e to the I m phi, same thing as just add them up, and it's going to be e to the 2 pi. Yeah, I m 2 pi. So that's what that is, because you can multiply that inside, just basic power rules. And then C2 is equal to the e negative I m. And then this is, yeah, negative I m phi, and then times it by e to the negative I m 2 pi. Yeah, so in other words, if this equals to e to the phi, well, we want this right here. I'll put a want equals to 1. So we want this equals to 1. So that's what we want. And then also this one here, we want the e to the negative I m 2 pi equals to 1. Want equals to 1. So that's what we want. So that so then we're just left with the general this equation. So basically we're just left with that if it's equal to 1 there, and it's actually equal there only if m is an integer. So in other words, and also note, this is Euler's identity. This one right here. So e to the I. Yeah, actually make a note. This is Euler's identity here. But we're going to deal with 2 pi. This is pi. So if we want to just deal with 2 pi. So basically, note that e to the 2 pi, yeah, e to the I 2 pi. And we just plug this in our equation. This equals 2, well, cosine, cosine 2 pi. Yeah, this is Euler's identity that we're doing 2 pi. We're not doing this one. So we're just doing the 2 there. So this is going to be cosine 2 pi. This equals to cosine 2 pi plus I sine 2 pi. All right, and what happens here is, well, we know cosine 2 pi. Just we'll just do a recall. I'll just draw this out. So this is theta, and now if we have a cosine, it's going to look like this. Cosine is going to look like that. That's cosine, and this is going to be cosine. And notice how this is at 2 pi. So it's equals to 1. So this is equals to 1. Yeah, this one equals to 1. Equals to 1. This part right here equals to, well, 0 actually. I'll change this to red. Or I'll change the color to red. So this one's going to be like this. And then basically just opposite of that. Yeah, it's going to look like that. So this is sine phi. I'm sine theta. This is just the graph there. I'll go back to black. So in other words, this is 0, and this equals 0. So this whole thing equals to 1. Yeah, so thus e to the I 2 pi equals to 1, and then, but we want e to the I m 2 pi equals to 1. And that is true if there's an integer. So you just multiply by 2, it just goes back, it just cycles every 2 pi. So this is just cycles every 2 pi. If you go to another one, go to the 4 pi, so multiply 2 pi by 2. So 2 pi times 1, it's over here. If you times it by 2, you get over here. If you times it by 3, you get 6 pi, and so on. So in other words, it just repeats, and on and on. So in other words, if it's an integer, it just repeats. So thus, e to the I 2 pi n, or let's put it at m right here, actually, m, equals to 1, if, yeah, or I'll say if m equals integer. Yeah, and this equals, it could be plus or minus, it could be, yeah, negative, I'll put dot, 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 -2, -1, 0, 1, 2, dot, dot, dot. It keeps going on and on. All right, yeah, so I just moved it over here. So thus, we have now, again, now we know why we picked negative m squared. So thus, e to the phi equals to e to the phi plus 2 pi. So it repeats every single time. So on our spherical setup here, our spherical domain, every 2 plus pi goes exactly the same thing. So it doesn't matter which radiance you do, if you could do cycle over and over again. So again, so e to the phi equals e to the phi plus 2 pi, or 360 degrees, or 2 pi radians, if m equals integer. And that is what we wanted. And that's our periodicity. And again, that's why it was chosen. And I want to dive into that, just so we have some idea of why we're picking this. And then likewise, yeah, and if we scroll back up here, so the equation, this one right here now, so we're going to solve, so we solved this one here, and again, we defined m, negative m squared, so we get that repeating setup there in the solution. Now this one here, we actually get the Euler-Cauchy equation, that's what it's called, and then, but then the combination of both, when you throw this in there, what we end up getting is eventually the associated Legendre function in there, which is much more complicated and beyond the scope of this video, but I'll just put that in there. I won't solve the exact formula directly in this video. Anyways, but so we're going to go over this one right now, and then go over why it's n times n plus 1. But ultimately, it's to get that associated Legendre function when you combine them both. So let's examine the second separated function and its chosen constant n times n plus 1, where n is actually a positive integer. And this yields the Euler-Cauchy equation, which we can solve via substitution. All right, so so let's go back up there again. I'm just going to copy and paste that formula. So this was the constant we chose. N times n plus 1, n is positive integer in this case, so that's pretty interesting. Let's times it by here, but the idea is the same. You're gonna get, you want specific types of solutions on the sphere. All right, so we have this r squared times the double prime of r plus 2r times r prime, and then divided by r equals n times n plus 1. So what happens now is, well, we can multiply this on this side and then move it over to this side, so we have an equation equaling 0. What we end up getting is a r squared r double prime plus 2r r prime, and then this is going to be multiplied over there, so we subtract a negative, this is going to be negative n times n plus 1 times r equals to 0, like that. All right, now for the solution for this one, we're going to do similar to before. We're going to assume, and it's always that exponential function, which is very useful in mathematics and physics and so on. So let's assume r of r, the solution is going to equal to of the form, or actually, we're not doing the exponential one. It's just a power one, actually. No, forget what I said. Anyways, so r to the power of k. So let's say we have the solution is like that. So if we have that, well, if we take the derivative, r prime, anyways, r prime of r, this is going to equal to, well, the k goes down, then we have r, and then it's going to be k minus 1. And the next one, the second derivative is going to be, I'll just do this here, r double prime of r equals 2, and then put the k down. So we're going to have a k here, and then we have a k minus 1 times by r, k minus 2, like that. All right, so we got that. So now we can combine these all together. So we're going to get an r squared. Yeah, so r squared times it by this whole setup there. That's going to be k minus 1. And then this is going to be an rk minus 2, like that. And then plus, the next one's 2r, and then r prime is going to be k minus 1, like that. And then lastly, we're going to get negative n times n plus 1 times it by r, which is just going to be r to the power of k. And this whole thing equals to 0. And now we could start simplifying some stuff. And we could simplify it by, well, these powers right here, this is r to squared. These can combine, so what we end up, and also we can multiply the k inside. So this becomes, I'll just do it like this. This becomes k squared, k times k, and then k times 1, negative k, like that, put a bracket. Now r squared, and then this is r minus 1. That just equals to, yeah, that's the same thing as r. Then you can add these powers using basic properties of power, a power function. So r squared times r to the power of k minus 1 equals, you combine them all together. So we get an rk. So the 2 minus 2 just vanish. All right, and then plus the next setup here, we have a 2k, and now we have an r to the power of 1. Put those together, we just have an rk. Like that. And then we have a minus n plus 1 rk equals 0, like that. Yeah, so we have rk everywhere, so we just divide everything by that. Divided by r to the power of k, so this cancels, this cancels, this cancels. So we're end up with, we get a k squared. Yes, we get a k squared minus k. So we have a minus k there. I'll just put them all together. Yeah, let's put it all together right here. Minus k. Yeah, then plus 2k minus n plus 1, like that. This equals to just, yeah, it's going, and then it's all equals 0. Just simplify it one more time. This k squared, and add these up together, so we just get a plus k. So 2k minus k is 2k, it's just k. Minus n times n plus 1 equals 0. All right, and now we can apply the quadratic equation here, quadratic equation, and recall this. This is equal to, so if we have, just using basic one, ax squared plus bc, ax squared plus bx plus c equals 0, then the solution is going to be x is equal to, it's going to be, well, negative b. I'll write from here, then I'll show you the earlier video on this derivation. So negative b plus or minus square root b minus 4ac divided by 2a. So we have that. Yeah, so that's just a quadratic equation. Let's put a circle like this. So then we put that inside. So we have k in this case. So we have k squared k, and this one is c. So we have k equals to, well, yeah, k, and in this case a is 1. So we have, yeah, basically I'll just put it like this for completeness. So this is going to be a is equal to 1, b is equal to 1, b is equal to 1, and then c is equal to negative n plus 1. So we just replace it all there. So we have k is equal to, yeah, k is equal to, so we have negative b, so negative 1. Yeah, negative 1, I just fixed up that circle. So negative 1 plus or minus, and then, yeah, so b is just 1, a is 1, so that's be plus or minus. This is going to be, yeah, and then we put b is 1, 1 squared is just 1, and then minus 4ac. So what's a is 1, so then we multiplied by, it's going to be plus now because we have this n times n plus 1 is c. So we have n, and then n plus 1. Like that. All right. And then divide this by 2 times 1. It's just 1. Yeah, let's put it for completeness. Put a 1 like that. Yeah, anyways. Yeah, so just divide by 2. Yeah, anyway, let's remove it. Anyway, so we got that. This equals, so I'll just put it for completeness, actually. It's for completeness, just so, because if we put 1 there, and so yeah, 1 squared. Put a squared there as well. So this equals to, yeah, this equals to, just fix up the square root sign. So we have a negative 1 plus or minus. And then I'm just going to multiply this inside. So 4 times n, we'll have 4n squared, put it over here, n squared. And then 4 times n times 1, that's just be plus 4n. And then last one, this is 1 squared, just 1, move it over here. And then divide it by 2. So that equals that, but also we could note that, and let's put this setup here. Note that if we look at this 4n squared plus 4n plus 1, well, we know what that is. Because these are just squareds. If we just have a thing called, yeah, 2n plus 1, if you expand and then squared, what happens if we square this? Well, again, just use your mind here. So this can be 2n times it by itself. So it's going to be 4n squared plus 2n times by this one right here, plus 1. The times 1 is going to be plus 2n. And now you do the same thing on this side when you square it. So this times by this one, then times it by itself. Then times it by itself. So we're going to get a plus 2n, just FOIL it all out. And let's move it over here and plus 1. So in other words, this equals to 4n squared plus 4n plus 1. So we could just factor that out. Just complete the square or whatnot. It's pretty straightforward. So I'm just going to leave it like that. So what this means is now we could write k. Let's put the k is equal to -1 plus or minus. Now it's going to be, well, 2n plus 1 squared. Yeah, a squared and square root divided by 2. So then the square root cancels. We're going to be left with a -1 plus or minus 2n plus 1 divided by 2. So in other words, what we end up having is, well, two sets of functions equals to, like this. This equals to, yeah, this equals to negative. So if it's plus, yeah, we're going to have, I'll fix that up a bit better. All right, so it can be either -1 plus 2n plus 1, and then divided by 2, which equals to, well, these ones cancel. We're going to get a 2n over 2. That just equals to, yeah, 2n over 2, which equals n. So we get this one. Or we get -1 minus 2n minus 1 over 2. So what we end up having is a -1 minus 1 as -2, and then minus -2n. So in other words, what we get is, and take the negative out, we're going to get a negative. And then this is going to be a divided by 2. So yeah, this will be a -2 minus 2n divided by 2. So the ones cancel. So, and then take the 1 out. We just get a n plus 1. All right. Yeah, basically, yeah, that's what we get. And I'll just circle these. So that is our solution. We got two solutions for k. And yeah, I just want to, just for completeness, because I usually do that. So this one here, again, just to show you what it's like that. This becomes -2 minus 2n divided by 2. Take it out, take the n's out. We're going to get a, and then cancel this out. We're going to get a, yeah, n plus 1. All right, that's all it is. These cancel. We're just going to have a, yeah, that's all we got. Anyways, I'll leave it like that. It's pretty straightforward. Yeah, because I didn't want to keep extending this past there. Okay, that's pretty straightforward. So then, thus, general solution. I'll just put it like this. So that is the solution. So right now, so basically, that is what e to the k is. Yeah, I mean not e to the k, r to the k. So that's the basis solution, like that. And here I'll just write thus. Yes, I'll just write the basis solution is going to be r of r is equal to r. Yeah, so it's going to be r. Yeah, it's going to be r to the k, which is r to the n, or r to the -n plus 1. Like that. So that's what it is. Or you could write it in this format. Or actually, instead of that format, I'll just write this as one. Or you could write r of r equals to, like that. So that is our two basis solutions. And then general solution is the linear combination of them to have all possible types by using just a constant setup. So we'll have a general solution using these, what these are called as basis solutions or something like that. And it's going to be r of r. R of r equals 2. And then we're going to put just set up like this. Yeah, just put a constant a and then times it by the first solution, first basis solution, r of n, plus constant b, and this is going to be r of n minus 1. Like this. I mean, negative n plus 1. Yeah, let's put it like that. And also, just to match up with our setup, because we had the constants here. If we go back up to the constants we chose it right over here, C1 and C2. So we'll just put C3 and C4 instead. So those are just constants. We'll just put C3 and C4. So C3 Rn plus C4 R negative n plus 1, like that. So that is our solution. And here I just have to write it down. So again, note that the general solution is a linear combination of the two basis functions, these two right there. So a linear combination, just different constants and so on. All right, and also recall my earlier video on the quadratic formula, which we used over here. And also this will also note this square right here. So when you expand that out, notice how we have this multiply this inside there. So this 2n, there's a 4n. There is 2n plus 2n. Anyways, so you recall my earlier video. There's a link to it there, and this is the quadratic formula. I just want to derive it quickly, just for fun. So here we have the ax squared plus bx plus c equals 0, and then using completing the square. So if we have x plus d squared, and again we have this at x squared plus 2dx plus d squared. And what you could do here is the next setup would be, in this case, write it in this form. So divide by a. So we get a x squared over, divide by a on both sides. We're going to get a, let's do it quickly just for fun here. B over a plus times x plus c over a. Now the next setup is we want to get rid of this x there. So we want to have a, completing the square setup, we'll have an x plus b over a, well, 2, divided by 2, because when you multiply it, you'll get this setup. Remember here? There's a 2 there, so divide by 2, so when you multiply it, we get that, and this is going to be squared, and then but then we also have to, because we're going to get this, we're going to get this part squared, so we have to get rid of that, so it won't be any extra set up there, subtracted by this whole thing squared, so this is b squared over 2a squared. And then we still have this one, bac equals 0. Yeah, so that's pretty much what we get. This setup here is just this. And then you solve it, you get this equation. So we have this exactly the same setup here. And then move this over to the other side. We're going to get a negative c over a. And then we get this setup right here, plus b squared over 2a squared. And then to get this, we're going to square root it. And then we subtract by a whole thing by b over 2a. And then simplify, you're going to get this quadratic equation. Anyways. I want to refresh my own memory for that. So let's continue further. Continue further, and also hopefully you followed that quick derivation. But yeah, we'll watch my video here for more in depth. Anyways, now let's solve the middle term in the Laplace equation, and this term is key to spherical harmonics. All right, and let's scroll back up to that middle equation setup here. So we solved these two here. So we've solved this one. We got this one here. We got this one here, and now the last one in this giant Laplace equation, when we separated the variables, that's this one right here, the one with the p, or the sine, or the thetas. So this is the one. This is the one we want to find, and this is the one that's key, because that's the one with the associated Legendre function. So we set up this setup here. Yeah, so we set up this right here. I'm going to circle this now. I'm going to just copy and paste it, it's just easier. Let's copy this, and let's move it all the way down here. So let's try solving this and see what we come across. All right, let's paste it and move it here. All right, so we have this, and let's do the same thing. Multiply by p on this side, move it over to this side, and drag it here, and get an equation equaling to 0. So we get a, and then we get over here 1 over sine theta partial. Then we have a partial over partial theta of sine theta times by p prime. And now this is the multiplied by p there, so minus, this thing is going to be plus now. Plus, and I'll put a giant bracket, so a plus, and we're going to have a n times n plus 1 of a minus m squared over sine squared theta, and then times it by p equals to 0. Like that. Alright, so now that we have this, and now the next step is, well, we wanted to get this into the associated Legendre formula setup. But again, that's beyond this video, but that's the idea for here. So we're going to go into, I'm going to go let, so I'm going to now let t equals to cosine theta. So if it's equals to cosine theta, now recall the trigonometric identity, so we know that the cosine, or I'll do it like this actually. Actually, it doesn't matter which way you do it. I'm going to go sine squared theta plus, cosine squared theta plus sine squared theta equals to 1. Recall this identity, so in this case, we're going to replace this with t. t squared. So we're going to get a, yeah, if that's equals to t squared, yeah, well, actually, let's do it all in one go. So this equals to, so that equals to t squared. And what I'll do is I'm going to change a sign in terms of t. So we're going to get a, so basically that's t squared. And then move it over to the other side. We're going to get a setup like this. Sine squared. Sine squared theta is equal to 1 minus t squared. In other words, sine theta is equal to plus or minus square root 1 minus t squared. All right, and let's just take the positive value on this one. Yeah, typically that's usually what happens, but I always show the plus or minus just because it's always there. But anyways, everyone just takes a plus sign. So we take a plus, and so what that means now is, well, then, and actually before we go further, well, we gotta solve what this is. This is derivative in terms of theta. And these are, and this one here's partial derivative in terms of theta as well. You could just still write it as d over d theta, just because it's a sine theta, and that's also theta. So what we'll do is, I'm gonna write this. So this derivative right here. So this is gonna be p prime. Let's write p prime equals to, well, dp over d theta, and you could say partial, but again, in this case, the partial is all set up. I mean, there's no other variable in this scenario, so you can just write d over dp, it doesn't matter. So this is going to equal to, and again, where theta is a function of t. So in other words, we're using the chain rule, so this equals to d, this equals to dp, dp over dt. So this is the same thing as this one right here. Yeah, because now t is a function of theta, so that then times it by using chain rule, dt over d theta. Yeah, and this equals to, well, dp over d theta, dt, times a dt over d theta. That's just going to be, well, derivative of cosine theta is going to be negative sine theta. Negative sine theta there. All right, so what this equals to now, well, if we look over here, this is a 1 over sine, and then we have that partial over partial theta, or d over d theta of this function there. So in other words, we could rearrange this so that we have a, move this sign over to the other side, we're going to get a 1 over negative sine. I'll just put a 1 over negative sine theta, and then this is going to be over to this side here. Yeah, this is going to be, let's move it like this, this over to there. This is going to be dp over d theta. This equals to dp over dt. Like that. So I will box this, because now we could replace this whole thing here. This gets replaced now. Or better yet, this part. Yeah, this part gets replaced. Alright, so let's just start changing everything up. So this is going to go, I'm going to make this zoom out a bit so that I could put this arrow like that. Yeah, so right here. Alright, so we're back in. Yeah, alright, here I just fixed that up so that arrow just, thus, we're going to get now, this becomes 1 minus, and also there's a note, there's a negative there too. So this becomes negative dp over dt, or it's going to be the function inside, so d over dt of this inside. That's going to be, well, sine squared. We know sine squared is equal to just the positive of here, square root 1 minus t squared. So we're going to do a square root 1 minus t squared, and then times it by, we'll make this a square bracket, and that's because the next one here is p prime, and well, we know p prime is just going to be equal to this dp over d theta. That equals to dp times it by negative sine theta, where sine theta is equal to this one. So it equals to negative 1. This equals to the negative of sine theta, which is 1 minus t squared. So this becomes over there. And yes, put that like that. I'll just put it like that. And then we have this dp over d theta. dp over dt. Box it in. And then the next setup is just add the remaining terms here. I'll just copy this setup here. Actually, no, yeah, I don't need to copy. I'm just going to put like here plus now. plus a square bracket. This can be n times n plus 1. And then minus, and then it's going to be an m squared divided by sine squared and times all times by p. M squared divided by sine squared is equal to 1 minus t squared. So 1 minus t squared times by p. And this whole thing equals to 0. Alright, here I quickly just shrunk everything in, fixed it all up. Yeah, so we have this now. And now these two combine. Well, this is just, and also there's a negative right here. So you can move the negative inside and basically just get rid of all this. This one becomes positive now. Yeah, that becomes positive. Yeah, so that becomes positive. And also here now we have a square root t minus 1 minus t squared times square 1 minus t squared. Well, the square roots add up, so 1 half plus 1 half adds up. So this is equals to 1 minus t squared. So what that means is, well, we can take this now derivative using a chain rule. And this using chain rule, what we'll get is, so we're gonna get right here. I'll put it like this. So yeah, put this like this whole thingy. Yeah, let's put a better arrow like this. So we're gonna get a 1 minus. Well, first of all, this 1 minus t squared, and then take the derivative of this one here, dp over dt. So we're gonna get a second derivative. In other words, we're gonna get a p double prime. And it's yeah, we don't need the partial one because it's all just in terms of t there, like that. And then plus, now we have to take the derivative of this one here. This is going to be, well, negative. This is a derivative of 1 is going to be 0. Derivative negative t squared is going to be, put the 2 down, minus 1. So we're going to get a minus 2t, and then just regular p prime. And then plus, this setup, this whole thingy is just going to be a n times n plus 1 right here. Yeah, fix that up, n plus 1 minus m squared over 1 minus t squared times by p equals to 0. And here, just move the arrows around. I'm going to box this whole thing. And this is all we need to get to. And I'm not going to basically solve this directly because this is something that's actually been studied a lot. This is the associated Legendre function. All right, and yeah, so this is pretty much what we need to get to. And now we're going to just plug in the solution from Wikipedia and so on. So this is the associated Legendre equation. Notice exactly the same setup here, and I'll probably do videos in the future deriving this, the exact solution. Yeah, in a separate video. But anyways, yeah, otherwise it'll be way too outside the scope of this video. So this is the associated Legendre equation, and notice this is exactly the same thing, but we'll replace x with t in our case here. And this is a this is a second derivative, d squared over dx squared. That's the second derivative, that's just p prime. And they write this PLM setup there. Notice the PLM, and that's because there's this setup L, and there's M here, and there's an N here. But now we're using N. So in our case, we use N, and we use t instead of L and x. But we solved the m there. Notice here, and then there's minus 2x. Yeah, that's the 2t. Now there's the, this is the derivative right here, dx over dt. That's just p prime. That's p prime. There's the, and then there's plm. That's just the solution to it. Anyways, that's p, and there's n times n plus 1 is L times L plus, times L plus 1. Then there's minus m squared over 1 minus t squared. And then this is m squared divided by 1 minus x squared. And there's PLM, or p. And a equals to 0. And then you can also write it, or this format, d over dx, and this setup here. And this is exactly the same setup we had. We just expanded it out. That's this part right here. D over dt of 1 minus t squared times it by dp over dt. And this one's d over dx of 1 minus x squared times by the derivative of this p there. Yeah, exactly the same thing. So where L and M are integers and refer to the degree and order, not a power, of the associated Legendre polynomial. So it's not a power, it just refers to some other degree and order, respectively. So the degree, so the degree is L, and then the power is m. And also, but it's not an actual power. Order. The order is m. And this is for the equation. And this is where those whole idea of magnetic quantum numbers arise as well. Because basically, you plug in these into this giant solution, which I'll get to. And those give you your respective solutions. Anyways, the above equation has non-zero solutions that are non-singular or regular, and means P remains finite, bounded, continuous, and differentiable, so it doesn't blow up to infinity and other stuff like that, on -1 to 1 only if n and m are integers. With this one, yeah, I wrote n here. I'm just going to replace it here. I meant m. Initially, I wrote it with... initially, I wrote it just converting everything to the one I'm using. So I'm using n here, just because the mic guy on YouTube used n. But anyways, for the Wikipedia, they typically all use L, but again, L is hard to write like that. Anyways, and m are integers with so where m is less than or equal to L, and m is greater than or equal to 0, or trivially equivalent negative values, replacing m with negative m. So it'd be the same thing, and but you could replace it with negative. The solution is given in terms of the Legendre polynomials PL of x. So this is the associated Legendre function or equation, and the solution is given in terms of the normal Legendre polynomials. This is what I mean. It's beyond the scope of this one of this video. So m is greater than or equal to 0. And again, I haven't covered this before either, so this will be new to me. But anyways, so PLM of x equals to -1 to the power of m. And so this is the solution of it. And then this is going to be times by 1 minus x squared to the power of m divided by 2 times by the mth derivative in terms of x of PL of x, where PL of x is the Legendre polynomials. All right, note the factor -1 to the power of m is known as the Condon shortly phase, but some authors omit this phase factor, which just rotates and shifts the phase or angle, etc. Just multiply by -1 and so on. And so when this becomes when m becomes like even number, this will be positive. When it's odd number, it will become negative. Anyways, yeah, and those are integers again. Remember, they're integers are integers, yeah, so L and M are integers. So, and also where PL of x is the Legendre polynomials is the solution of the Legendre equation. So this is the associated Legendre equation, and this is the normal Legendre equation, 1 minus x squared times second derivative of PL of x minus 2x, and then this is times it by derivative of this PL of x. Plus L times L plus 1 times the PL of x equals 0. And then by Rodriguez formula, so we can obtain PL of x. And again, this is what I mean by all we had to do was get up to here. And then there's a bunch of research done on this specific form here. And again, that's why these constants were picked as well. So we get the solutions in those other ones, and we have the difference. We get the associated Legendre equation. All right, so then by Rodriguez formula, we can obtain PL of x. We can obtain PL of x as... this is going to be as, and then PL of x equals to 1 divided by 2 to the power of L times L factorial. So there's a factorial showing up somehow. And then times it by dl over dxl. This is the Lth derivative of x squared minus 1 to the power of L. All right, so this looks like some Taylor series type stuff, it appears, I think. Anyways, I'll see what happens when I derive it in a future video. So then PLM can be expressed as, if you just throw this inside. So if you throw this PL inside this solution here, so that's this one here, throw it inside. So now the mth derivative of this right here. So then the PLM of x can be expressed as PLM of x equals to -1 to the power of m divided by 2L times L factorial, divided by 2 factorial. So we have, this is the PLM of x, we have this one here, and then we have to include these two terms, and then we multiply by 1 minus x squared power of m minus m divided by 2. That's from the associated part right here. And then we have, now it's the PL of x. Now we take the mth derivative, and even though we already took over here, this one here, the Lth derivative of this. So we're going to have to take the combined derivative, the L plus mth derivative of x squared minus 1 to power of L. Yeah, so I told you all this is, I don't know if you guys are ready for this. Anyways, the derivation of the Legendre polynomials are outside the scope of this video, but I may cover them in a future video. See Mike the Mathematician's playlist for now. So there's a playlist there on solving these. I'll click this to see what happens. So if you click the playlist, it has a bunch. He kind of like fast forward derivation, so you might get lost. And then, but hence why I'm doing these videos in a slow motion fashion. All right, so it's loading up. Yeah, there it is. So it's spherical harmonics associated Legendre equation and so on. Legendre polynomials. Okay, epic stuff there. I'll close this. So now, plugging all of this together, we obtain our solution for the solid spherical harmonics, and again, in terms of the associated Legendre polynomial. So in terms of this giant thingy, but we'll use n instead of L. Yeah, so what we're going to get is... well, let's just find our starting point. So I'm going to put the, first of all, and we're going to get solid spherical harmonics. Yeah, plugging all together in the solid one, again, includes the radial term and so on. So let's just go back to put it all together. So I'm going to write now our starting point where we started off with the Laplace equation. But instead of using the one I wrote, I'm just going to take the one we solved earlier from, and then show it on Wikipedia. So we go back up here. So f is equal to a function of these right there. The separated variable. So we have this right here. We can copy that, or I'll just copy this one here because this is what we solved in the earlier in this video. That's this part right here. So I'm going to write that. It's just more compact. And then we go back into here and start putting it all together and erase this. All right. Okay, paste it, and we have this. Okay. So thus we have f. F is a function of, let's put it all together, equals to, in separated variables, e of function of phi times it by p. Or actually, instead of even that, I'm going to erase it. I'm going to say f is a function of, I'll put this as r theta phi, and this equals to now, this equals to our setup, equals to separated variables, separated function e as a function of phi, times it by, and I'll write the r one first, in the middle there, r of r, and then times it by p of theta. The reason put that at the end because that's the associated set of their PLM. So now this equals to, so we're gonna get now this equals to, I'll put it like this. Yeah, this equals to, well, the first one is gonna be, well, we know that one was just C1 e to the im phi plus C2 e to the negative im phi, like that. And that's we can go over there. That's the one we solved earlier. Let's go back all the way there just to show you. Again, it's like, how do you get all this in there? So this was the one I derived here. So C1 e to the im phi plus C2 e to the negative im phi. And then the second one is going to be this one here. That's the, this one's going to be C3 Rn and then C4 Rn, r to the minus n plus 1. All right, so that's going to be, again, that's why we put those in order like this. Then times it by C3 r to the n plus C4 r to the negative n plus 1, like that. And then lastly, times it by p of, this is going to be, now this is the Legendre, so instead of Lm, we have Nm. All right, instead of x, we have t, so go back up here. So we have t, and remember what t is equal to. T is equal to cosine theta, so we just plug in cosine theta in there. So we're going to get, replace everything with what we have, times it by p n m. So instead of L, we have n. So instead of L, we have, we have m there at the top there. So where's the equivalent there? Yeah, so we have n, m. And then cosine, instead of x, instead of t, we have cosine theta. All right. And here I move this over to this side. What I'm going to do is I'm going to box this whole thing out because this is our solution. This is our solution. And for completeness, let's put in our p and m, our associated Legendre function. So where we'll go t is equal to cosine theta. This t is equal to cosine theta. And right here, so and we have Yeah, so we have, this is going to be our p n of m. I'm going to put a t now instead of cosine theta. So that equals 2. And then we put this setup here. So this is going to be negative 1 to the power of m. And then times by 1 minus x squared power of m minus 2, divided by 2. But that's going to be a t. And it's dm over dxm and then pl of x. So that's going to be now negative 1 to power of m times it by, I think there's, 1 minus, it's going to be right here. 1 minus t squared power of m squared. So 1 minus t squared power of m divided by 2, and then times it by dm over dtm, the mth derivative of Pn of t, the regular Legendre polynomial. And we could see this. Again, just double check quickly. This is the PL, negative 1 power of m, and then 1 minus t squared to power of m divided by 2, and then this one dm over dtm, like that. So there's dtm, there's 1 minus t squared. Pn of t, and then now lastly, or keep going, and Pn of t, the regular Legendre polynomials, this equals to, let's scroll up to it, that's this part right here, so 1 divided by 2n divided by, n factorial, so 1 divided by 2 to the n factorial, and then the next setup is going to be, well, this can be the nth, or the L or nth derivative of t squared minus 1 power of n, so this is going to be the nth derivative of t squared minus 1 power of n. So that's what it is, I think. It's double, there it is, minus 1 power of n. And it's fascinating stuff. And so now we put it all together, or we can go write down the whole thing, and then Pn of t, or actually we could probably just put it all into here. So Pn of m of t is equal to this part right here, negative 1 power of m, and then combine it with this part here, so we're going to get a 2 to the power of n factorial. Now we have this part right here, 1 minus t squared m divided by 2, and now we combine these derivatives of this thingy. That's going to be the nth plus mth derivative in terms of t of t squared minus 1 power of n. Unbelievable. All right, here's shifted it. I'm going to bold this in. All right, and if we go back up, just double check, that's this formula. So we have PL of x, this is 1, negative 1 power of m, and then this can be 2L, L factorial, or in other words, n, 2n, n factorial. That lines up, and then 1 minus t squared power of m divided by 2, and then there's the L, n plus m, and then this is going to be t squared minus 1 power of n. Yes, absolutely fascinating stuff. Alright, now that we got this, we pretty much did the bulk of the work, and now the next setup is just look at spherical harmonics, which is the solution to the angular Laplacian, but again, we pretty much have that already derived. I'll just discuss it, and so on. So the solid spherical harmonics includes the radial terms r, so you can see these r there, but there's also r everywhere here, so we have to get rid of those when we do the angular Laplacian. So while the spherical harmonics in general typically are just in terms of the angular terms theta and phi. So there's the theta and there's the phi, and so on. So if we recall, so this is the Laplacian, and then here's the solution, f of r of theta, function of r, theta, and phi equals to e phi r of r, and then p theta, and this equals to this giant thingy here, and there's the associated Legendre functions. We have these two power ones. This is the e, this is the r, this is the p, and that is just this one here. I just got Grok AI just to write it in a formula form. So this one right here, and we got this exactly the same setup there. So we can combine the radial terms as a function y. So that's typically what's written. So if we write f of r and theta and phi, this equals to, we'll call this r of r times it by y. So we just combined those two together. Or we'll put it all together first, just to show you, so for completeness. So here's the r of r, p theta, e of phi. So this equals to combine these into y of theta and phi. So this equals to r of r, and then y of, this is going to be y of theta and phi. So in other words, so this one is just going to be this one. Actually, no, not the r. It's going to be just this one and this one. So that's going to be the solution. So in other words, we're going to have y of theta and phi. This will just equal 2, and this will just be just this first part. So c1 e to the I m phi plus c2 e to the negative I m phi, and then times it by the associated Legendre function Pn of m of cosine theta. So that is just that. So this is pretty much the spherical harmonics, which excludes the r function there. So we're not accounting for that. Essentially, we could graph these on any sphere just to assume the radius is r equals to 1. Alright, yeah, so that's pretty much it, but just for more info and context, so this function y, is typically considered as the solution to the angular Laplacian or Laplace-Beltrami operator on the sphere, which can be denoted by this one, this wedge squared, or denoted as this one right here, Laplacian s squared. That's interesting. But this one is the typical one there that I like using. Alright, yeah, so the next setup is, we'll go over right here, because again, this is the Laplacian, angular Laplacian, but then there's an r squared there, we gotta get rid of that. So what I'm gonna do is I'm gonna copy this, and then paste it here, just to save some time. Yes, we have this, and now I'm gonna go times it by r squared. Yeah, times the whole thing by r squared, so we basically cancel out this, cancel this out, and we're gonna get, now we're gonna get an r squared of this Laplacian equals to partial over partial r, and then r squared partial f over partial r, and then plus 1 over sine theta, and then partial over partial theta, then sine theta partial f over partial theta, and then plus 1 over sine squared theta, partial, the second partial derivative of f in terms of phi, like that. This equals 0. And again, just going over just typically how the spherical harmonics are written, as there's solutions of it, because when you exclude the r term. So we have this. Yes, we have this. And now note this whole side here. This one doesn't have any r terms. This one has r. This one doesn't have any r terms. And now this is the angular Laplacian. This is going to be written with that wedge set up there. And this is of f. So that is our angular Laplacian. So we could just write it all like that then. So we can go partial over partial r of r squared partial f over partial r. Yeah, we have that then plus, this is the Laplacian f equals to 0. And well, we know that f, so f is going to be equal to our new setup now. F equals to r, this is number rpe, but then we're going to just change this into, well, r and y. And y. So that's what we're going to write it as, because again, we know that r is just, f is just a function of that. So, f is a function of r, theta, and phi, and it equals to r times it by, y. We're just going to use this y equals to this p times theta. P times e. So that's what we have there. And also to get this partial derivative, well, we know that this is going to be now the partial derivative of f in terms of r. This equals to, well, these all gets treated as constants, this and, well, the y. So in other words, that just equals to, as if it's nothing there. It's just y times r prime. Yeah, r prime, like that. Yeah, which is just y dp dr over r over dr, like that. So what we get is, so note, I'll put this note here. Thus what we get is, now this is going to be derivative d over dr, because we don't need to, because it's all just be in terms of r. And this one's like a constant. We just take it all out. Just take the y out. So just take the y out and move it. And then we have the inside is going to be r squared, and then this is going to be, dr over r, like that. And then plus the Laplacian, well, there's no r terms in here, so we can just take that out. Yeah, because it could just be whenever they're inside the f, we just factor it out as if it's a constant. That's just going to be ry. So this is going to be r Laplacian of y equals to 0. Next setup is, well, divide both sides by ry as we did before. Again, we already solved this in the other format in solid spherical harmonics. So we divide it out, we're going to get a d over dr of r squared dr over r. And this is 1 over r, like that. Plus, then this r cancels, we're going to get a, we're going to get a y, and a Laplacian over y over y. Yes, we're going to get Laplacian of y divided by y equals to 0. And now, typically, what you do is the exact same thing as before, set this equal to a constant, because none of these are all only dealing with y terms, so the angular theta or phi. This one's only dealing with r. So then, but if it always is 0, then in other words, they have to both be constant. This one is chosen to be, this equals to n times n plus 1, as we did before in the Euler-Cauchy formula setup. This one's going to equal to negative n times n plus 1. All right, and again, if we scroll all the way back up to the Euler-Cauchy formula setup, that is this part right here. It's exactly the same thing we did right here. So we had this equation. This is the r squared r double prime. It's the same thing we have. We just have just do applied chain rule. And we set it equals to n times n plus 1. And then we ended up getting this whole setup here. This right here. C3 rn plus C4r power of n minus 1. Power of n negative n plus 1. And that's going to be, this is set up here. So that's this. Like that. That's what we do. And got that. And again, I remember that before it was just a chain rule. You just apply here. So if you take the derivative of this r squared, it's going to be r squared and then r double prime and then plus 2r and then r prime. So again, that's the same thing. But we're only worried about this one. We're only focused on this one because typically how it's written. I'm only going over this just because of the context of how it's written, like y is a solution of this angular Laplacian setup. So we get this part right here. The angular Laplacian of y divided by y equals to negative n times n plus 1. Or you could write it as multiply this over there, then move it over to this other side, so we get the typical equation involving equaling to 0. So we're going to get a Laplacian of y plus n times n plus 1 times y equals 0. Equals 0. So that is typically how it's written. And then y is a solution. Yeah, y is a solution to this where the angular Laplacian of y is equal to this setup. But then that's angular Laplacian of f. So we copy this and change the y, f2 and a y. And paste this. All right, so that's what we got. And then this becomes a y. Becomes a y. A y. Fascinating stuff. Yeah, and here I'm just going to circle this whole thing. Yeah, so it's pretty, should I circle it or not? But anyways, put it like that. Yeah, actually here I circled it. Yeah, so that's that. Typically how it's written, and then where y is, again, be a solution to it. And I'll just circle this right here. So, and then equals to that. I'll say y is a solution. Y is a solution. Alright, yeah, and here I just typed it out and said, so y is a solution to the above equation involving the angular Laplacian, and maybe this might be capital L, maybe. Anyways, and then we have y of theta and phi equals to this setup right here. There's the C1 constants e to the power of im phi plus C2 e to the power of negative im phi plus, and then times it by the associated Legendre function Pnm of cosine theta. So it's fascinating stuff. And this is this one. Actually, I'm not going to circle this. That's just that's the angular Laplacian. This is the solution we solve. I mean, this is the equation we have to solve, and that's what we get. And so we're going to move it like that. Move this up a bit, and yeah, the next part is we're going to have to solve for the real spherical harmonics. Alright, so going further, let's derive the real spherical harmonics. So the real ones basically remove all of these imaginary terms out of there. So you don't have any of those imaginary terms. So the real spherical harmonics are defined such that the functions are real valued everywhere with no complex term I, with a typical definition shown as follows. So it's typically written like this. or defined, I guess. So we're going to call this y real n m, and then this is a function of theta and phi. This equals to, it's going to be a giant thing. And again, we went over this in the overview / introduction, just to get an overview of what we're trying to achieve with this spherical harmonics. But now this is the definition like this. We'll go over some of the terms in a bit. So it's going to be -1 to the power of m, and then divided by square root 2, times it by y n m. And this is the complex one. This is the real one. This is the complex, which is just basically this part right here. Y n m plus -1 to the power of m. I'll make this regular bracket like that, the square bracket, and then y n minus m, like that. And this is for m is greater than 0. And then this is equal, so basically it's equal to that, but it's if m is equal to 0, then we just get y and 0 like that. This is just m equals 0. And then lastly, for m is negative, we get this term, -1 power of m plus 1 divided by I square root 2. And then we have the same setup, put a square bracket. Y n absolute value of m minus, this is going to be minus -1 to power of m, or absolute value of m, and then y n, and then this is the term negative absolute value of m, and then this is for m is less than 0. And here I quickly just move this over to the other side, added this square bracket. So, and now before we go further, so note that the complex spherical harmonics are chosen using the pure complex exponentials, i.e. the basis solutions. So instead of using this full linear combinations right there, yeah, so rather than the linear combinations, going back here, yeah, so rather than using this giant thingy there, we're only just gonna use these right here, like that. And because, again, those are still solutions, basically we're going to use the basis solutions rather than the linear combinations. And this term right here, y, n, and then a negative m over there. So this one right here. So inside this, when we get the real one, we're just going to use the basis one. I'll explain in a bit. And then for this term, we're going to define that, defined via the following complex conjugate form, i.e. flip the sign of the complex rotation angle term, because this makes important formulas and operations in quantum mechanics cleaner, simpler, and more elegant. And again, there's a link to the Grok AI explanation for that, so that is for another day, but apparently that makes it just much easier. So, and using the proportional forms, basically ignoring the normalization constant discussed earlier, we obtain, so for these yn m and this yn negative m, what we get is, we get y n m, the complex form, is going to be proportional to, because yeah, we're ignoring the proportionality constant, so p n m, the associated Lagrange function p n m of cosine theta, and then multiplied by just the basis solution, eim phi. So that's the plus one. Yes, in other words, we just do this one here times by this, and there's going to be a proportionality constant, etc., which ensures that the probability integral thingy equals to 1. So that is that, and then we have y n negative m is going to be proportional to, and now this one's going to be written like this, -1 to the power of m, and then p n m, yeah, so it still has the m there, and I'll explain why it's still there, cosine theta, and then this is going to be e negative I m phi. Alright, so now we have this, and again, I just want to elaborate more on this. So note the complex conjugation in the above definition. Again, that's just using this negative there. And if you go to the wiki, go back to the wiki right here. So if you go right here, complex conjugate right here, for the rectangular one, you just go z equals x plus I y, then you just flipped it to negative. So negative iy. This one's theta there. This one's going to be basically negative theta. So basically, the complex conjugate of a plus bi is a minus bi. But in polar form, because we're dealing with spherical harmonics. This is going to be the angle there. So r e I phi is just going to be r e negative phi. Yeah, I phi. Yeah, so in other words, what we have, I'm just going to write this, how this is easily written. So we have y n negative m of theta phi. This is equal to negative 1, or it's proportional to it. Or actually, this just equals to this one. Yeah, it just equals to it by definition, y n m, and then this is going to be theta phi, and then this is the complex conjugate. You just put a star. This is indicating complex conjugate. Complex conjugate. Conjugate. All right, and now here quickly, just to quickly recap on this complex conjugate slash just imaginary numbers in general. So if we have, this is, let's say we have set up like this. This is the real part. This is how we typically written, and then imaginary is the this y-axis there. So then let's say we had this up to here. This is r. So over here is going to be r, and there's an angle, angles phi. And this height is going to be y. So it's going to be y is on the imaginary side and x is on the real side, like that. So this is going to be r e. This is going to be I phi. That's how you could. That's written like that, and then again it matches Euler's identity. This just equals to, well, equals to x, the real one, plus the imaginary times by y, the height of the imaginary, like that. And where, well, cosine number using just basic Pythagoras. Basic trigonometry. So sine phi, remember, is just equals to opposite over adjacent over r. Likewise for likewise for cosine will be adjacent, would be the x over r. So in other words, then move the r to the other side. So this equals 2, but then just take the factor out the r. This is going to be cosine phi plus I sine phi. And again, this is just Euler's identity. This is Euler's identity that we covered earlier. Euler's formula. Yeah, here I just wrote formula there, and if we scroll all the way back up to Euler, let's see where Euler was way back over here. Yeah, so this is Euler's formula right here we covered earlier. So EIX equals cosine x plus I sine x, and then Euler's identity is EI pi equals -1. Yeah, so this is the Euler's formula, and you can also write it as a matrix and so on, which is pretty fascinating. That's for my earlier videos, so definitely watch that to see how you can do complex stuff in terms of the matrices. All right, anyways, let's go back over here. So now the complex conjugate of this would just be, well, the bottom up there. So this would be, you would go down r. So r is always positive, just the length to this point. So that's r e negative I phi, like that. And this goes like that. And this is, again, height is going to be y. And then this is there. So you could say height is negative y and so on. So negative y like that, and x is still positive. So this equals 2, well, x minus iy, which equals to r, take the bracket out, cosine phi minus I sine phi. Like that. Anyways, I just want to recap on this setup here. I'm going to circle this because it's not really part of our main theme, but just to give you a recap on that. All right, so now that we have this, next setup is, well, we take this over here. So now we want to just show you what this is, this complex conjugate, just to illustrate that. So we take this y and m, the complex, the complex spherical harmonic. So y and m is proportional to p and m, the associated Legendre function of cosine theta times e I m phi. So thus the complex conjugate of this y and m star, do a better star, is going to equal, or is going to be proportional to, let's do the proportional setup like that, of, do like that. Okay, this is going to be p n, so the same thing as the one on the left, cosine theta e negative I m phi. So we just take this setup and make it negative. Again, exactly this. That's a negative. That's a complex conjugate, and this is positive, goes to negative. That's all it is. Just take that. Same thing as this plus iy. Same thing as minus iy, like that. All right, so thus we have, so thus we have it by this definition, so yn negative m. Yeah, so we're going to have yn negative m is going to be, well, proportional to, and I'll just put it fully like this. This is going to be a, actually, we'll just put it like this. It's going to be a function of theta and phi, proportional to, put it from the top, then down. All right, like that. It's going to be proportional to, well, this one here. Yeah, it's going to be proportional to this one here, negative 1 to the power of m. And then this is going to be this, this one now, it's going to be changed to this. And we're using proportional because it's this proportional there. So we're using that. So this is going to be p n m of cosine theta e negative I m phi, like that. So that's what we have there. All right, now going further now. So also note that for this yn negative m term right here, this is the spherical harmonic with the negative m there. We use pnm instead of pn negative m. So notice that even though there's negative m there, we're still using this positive, this plus m there. And yeah, we use that instead. Yeah, and we use that because the associated Legendre equation depends on m squared, not m. So what this means is these are going to be proportional to each other. So these two are actually proportional to them. They're not going to be independent, so you're not going to have just a random different solution. Yeah, right here. They're going to be actually proportional. Yeah, these ones are going to be proportional. Let me see if I could write. Yeah, this one's going to be proportional to each other. Yeah, so they're basically by a constant, so on, and then I'll explain that as we go up here as well. Again, let me just go look at the associated Legendre equation. So if we look at it right here, here's the associated Legendre equation. This is ix squared and so on. And then instead of this one, instead of writing, actually that's the normal one. This is the one. This is the associated. The other one's just a legendary. This is the one we want. And what I'll do is I'm going to replace this second derivative of PLM. I'm just going to call this a y double prime. So that's just make it more generic. So what I'll do is I'll copy this so we can write this down easier. Go all the way back up here. All right. So I'm going to put this right here just so we can see it. Again, that was the associated Legendre equation. I'm going to go 1 minus. Use the t setup there. So 1 over t squared, and then this is going to be y double prime, like that. And then this next one's going to be 2t, then d over dx, that's just the first derivative, so y prime. And then plus, and then change these other ones to our usual n, set up n plus 1, minus m squared. So notice that the only m is there is over there, so 1 minus t squared, and then y equals 0. So we got that, we get rid of it. So now this all depends on m squared. So yeah, so what this means is if we have y equals to, I'll just say, let's say y of t. All right, so if y of t, if y of t is equal to the associated Legendre function Pn of m, like that of t, and this is a solution. So if is a solution, yeah, I'll say, yeah, if this is is a solution, I'll say is a solution. Yeah, so I put the solution, then basically the other one's automatically a solution too. Just put a dot there. So thus, so then this one's gonna be, then y of t, then y of t is also equal to solution. This one is negative m of t is also a solution. A solution. And again, this is all because write it down. I'll rather write it than type it. So that's because, well, m plus or minus m squared is still going to be m squared. Yeah, it's just equals to m squared. It doesn't matter what it's going to be still positive. Yeah, so it does not matter. Basically, this m squared, this is unchanged. So it doesn't change the actual thing. This is unchanged. Thus, yeah, this is pretty a good clear setup actually. This is thus we'll have P n negative m of t is going to be, well, proportional to, it's going to be proportional to Pn of t. Yeah, Pn of t. So in other words, this is going to be a constant multiplied. So that's why we have this, yeah, just make it like this. So basically, if we have it, for example, if we have something like, let's say, k Pnm, that's pretty much what it is, up to a constant. So it could be just equal to like a constant multiplied by that. And then basically when you plug in the constant, when you take out the constant here, all these derivatives, you're just going to get a k out of this whole thingy there. and then divide by k, just all cancels. So that's pretty much what it is. Yeah, so that is that. Yeah, so this is just going to be proportional to it. And yeah, actually, I'm just going to write that, that setup there. So this actually equals to a constant. So this equals to, this equals to the constant, I'll put it over here actually, k n, or actually just to make it appear better, this equals to constant k p n m of t. And what it actually turns out is that there's actually an identity for this where k is going to equal to, well, it's actually going to equal to negative 1 power of m times it by, and this is going to be times by n minus m factorial divided by n plus m factorial p n m of t. So that's what it actually equals to. I don't know what this here is, apparently from Rodriguez formula. I might derive this in a future video. So that equals that, and I'll box this whole thing. Yeah, here I just fix that up and let's box this whole thing in. Yes, we have that box, and also it's right here where k is a constant. K equals constant, like that. And yeah, here just fix that up. So where k equals a constant, and we have it over here. So basically k is this whole giant term right here, negative 1 times, yeah, this is going to be this whole setup there. Yeah, this whole setup there, like that. So that is the, not the m there, this one here. So that is our k. So note that this exact relation is obtained from Rodriguez formula for the associated Legendre function, in which we have the following, in which we have the following identity, which I may derive in a future video. So PL negative m of x equals to negative 1 power of m times by L minus m factorial divided by L plus m factorial times PL m, like that. So this is this one I might derive it in a future video, and here's ours using our t and n setups instead of the x, and so on. All right, now that we have gone over this and basically explained why we're using these two setups here, yeah, so this one here and that, the ynm and yn minus m. So now we're going to look at the definition. So this is the real spherical harmonics nm of theta phi equals this for when m is greater than 0. So we'll look at this one first, right there. So I'll just copy this. All right, we'll copy that. And let's go right here. Yeah, so for m is greater than 0, the definition is, so we'll move it like that. This is going to be, we'll write this as ynm real, the real spherical harmonic, and this is m is greater than 0. All right, so now the next setup is, let's just plug in our setups there. So we have our proportionality stuff. So ynm is over here. Yes, we plug these in. Nm is just Pnm cosine theta, and then e to this one. The other one's same thing, but negative e to the I m phi, and there's a negative 1 m set up there. So let's put that all inside. This becomes, again, this can be proportional to, because we're using a proportionality setup. So negative 1 to the power of m divided by square root 2, and then ynm is going to be, well, Pnm cosine theta, then e to the I m phi. All right, and then the other one's going to be, again, we're doing proportional because we're not including all those random normalization constants. So this is going to be plus, and now it's going to be, well, this is the this part right here. It's going to be negative 1m square to the power of, negative 1 to the power of m, And then, well, now we're going to have a second one. So we're going to times it by -1 to the power of m. And now this is going to be, well, a proportionality constant, same thing, p and m cosine theta of cosine theta. And then this is going to be times it by e negative I m phi. So the complex conjugate of that one, the negative side of it. And all right, here I just quickly shrunk it to fit over there, but I'm also going to write here as y n m real, like that, like that. All right, so now we have this. Next setup, we can go over here and basically simplify all this, but we're going to take out this p and m. So first we have this -1 power of m, like that. Square root 2. Take out, just factor out the associated Legendre function. So we're going to have a p and m of cosine theta. All right, so take that one out. Now we're going to have this setup here, an e. Actually, before we even get to that, so we factor that out. Move it down here. Note that right here, this -1 to the power of m. So -1 power of m times -1 power of m. Well, that's just equals to 2m. Equals to, yeah, -1 to the power of 2m. But now there's a 2 there. So if we have a negative, well, this is going to be an even number. So if you have, for example, if you have 3, 2 times 3 is going to be 6. So you're always going to have a basic factor of 2. In other words, even number. So this is even. So this whole thing equals to 1. So in other words, we could just say, yeah, get rid of that. So it equals 1. Now this one here, p n cosine theta, move that out as well. That's over here. So we're going to get a EIM phi, and then plus E negative IM phi. And again, using Euler's formula, what we get here is, all right, so what this becomes is, well, this equals 2. And again, if we scroll back up to our Euler's formula, so we had R EI phi equals to X plus IY, and then the R there times by the Euler's formula there, cosine phi plus I sine phi. And then for the complex conjugate, the negative side, this ERI phi is this term there. And again, this is, take the factor out the R. Yeah, we have X minus IY, that's the R, then factor out cosine phi minus I sine phi. But in our case, we have M phi, so we replace this phi with M phi. And then this is minus, as the other one's a plus. So we get, this whole top part's going to be, well, this is going to be a cosine. Yeah, cosine phi, and then plus, cosine M phi. M phi, put a bracket like that, plus I sine M phi. All right. And then plus, the other one's going to be the same thing, cosine M phi minus I sine. Yes, minus I sine phi. The sine M phi, like that. All right, here I just shifted it over to the left. So what this means is, well, this I sine phi and this negative I sine phi cancels. And now we're just going to left with this as 2 cosine phi. This equals to 2 cosine M phi. M phi. So in other words, this whole setup equals to now -1 power of M times by 2 divided by, I'm going to put a square root 2 over here, P n M cosine theta times by cosine M phi, like that. But again, and also note that here, this is going to be, well, 2, this right here, just make it for completeness. Calculus book and a lot of areas always try to remove this, simplify this. So 2 to the power of, this is equals 2 to the power of 2. Divided by this, the same thing as writing 2 to the power of 2 divided by 2 to the power of 1/2. So this equals, just get recap on power laws. So divided by, not 2, just 2 to the power of 2, like that. Equals to 2 to the power of 2. Yeah, so 2 to the power of 2 minus 1/2. Yeah. So in other words, this equals to 2 to the 1/2. This equals to square root 2. So in other words, this whole setup is equal to, just simplify it further, but again, I just did it for fun. Negative 1 power of m times square root 2 p n m cosine theta times by cosine m phi. So in other words, but then this is just a constant anyways. Yeah, so that's a constant. So in other words, we just throw it back into our proportionality setup equation, because we already are excluding the normalization constants to get the integral for the probability integral to equal to 1, as I explained earlier in the video. So this means that yn m real is just going to be, so we have here y n m real, and again this just equals to, this equals to, I'll put it for completeness, put the theta phi. This is proportional to, and then we get rid of that whole constant, it just throws it into the proportional to it. That's basically what proportional means, just constant times by it. So cosine p n m cosine theta, and then times by cosine m phi, and this is for this is for m is positive number. M is greater than 0, so we can box this whole thing in. Fascinating stuff. Alright, so now that we have this, going further, let's take a look at the case for m equals 0. Well, the definition is, let's go back up here. The definition is just yn 0. So that's, that's for when m equals 0, and that's because it automatically cancels the imaginary term. So the number of these ones here, we got rid of the imaginary terms, and so on, there's no imaginary terms. And again, we were just dealing with real spherical harmonics, and the reason is because most of the ones that the graphs you see are real spherical harmonics, because a complex one, visually, it's very hard to graph it. Visually, just to grasp it, it's because it involves rotation, so you're going to get like some smudging or smearing or whatnot, and so on. It involves rotation of this phi setup there. It involves this one here, but now we're pretty much multiplying it by cosine here, so instead of rotation, you're just going to get a scalar difference change or whatnot. So you don't have that imaginary I term and so on. Anyways, so for the definition is y, let's try this again, y, okay. Yeah, my computer doesn't work sometimes. Okay, so yn m real. I'll put this as, again, a function of theta and phi. This just equals to yn and 0. And again, this is also a function of theta and phi. But yeah, just put it yn 0. This is for m equals 0. And you could see this by, well, let's just plug this inside. So yn, and then you could also write it that here, 0, real, actually just a normal one. Yeah, so the normal one is put yn and m is 0. So if we plug that inside, this becomes, well, let's just scroll back up to our setup here. So if we recall yn, it's over here, so proportional to this setup. Yeah, so proportional p n m cosine theta and then e I m phi. So in other words, this is proportional to it because we're getting rid of the normalization constant. So this equals, or proportional to p n and then 0 of cosine theta, and then now we have e I times 0 times phi. So in other words, this part right here, this equals to e to the 0, which is by definition equal to 1. Yeah, typically anything to the power of 0 is 1, and e to the 0 is also typically equals to 1 as well, but sometimes not, depending on definition. Anyways, this equals to Pn 0 cosine theta and then 1. Yeah, that's all it is. Yeah. So thus yn m real, let's put it like this, equals to proportional to Pn of Pn 0, like that. This is cosine theta, and this is for m equals to 0. So we could box this in. So it's proportional to that, and we'll put these all together once we get the negative one. Or you could also write this as, you could also just put an or, you can write it as a yn 0 real is proportional to, like this, p n 0 of cosine theta. So again, it doesn't depend on phi here, because the phi just all goes to 1 there. So it all becomes, this whole setup becomes a 1. Like that. So fascinating stuff. There's shrink this, and so on. And I just want to make another note right here. So note that Pn0 is just Pn and is just the ordinary Legendre polynomial. So that's pretty interesting. So if I go back to the polynomial right here. So here is the Legendre polynomial. Let's go all the way back up here. Yeah. So basically, we had this setup here. This is the PNM. This is the associated Legendre. I'm going to copy this. And then if you have m equals to 0, this cancels, this just becomes 1, and then this thing becomes 1, this becomes 1, and then this just goes 0. So we're left with just the basically the ordinary Legendre polynomial. So this is yeah, these all just vanish. And again, you can see them in the screenshots of the equations right here. So this one here, get rid of the -1 power of m. This one here vanishes. You just get this setup right here. Yeah, so I'll just put that down here and just show you. It's pretty fascinating. I just wanted to illustrate that. So thus, this is just the same one here. I'm going to paste it here. So this is that, and then basically I'll put a 0. So then if it's 0, this goes to, well, 0. This goes to 1. This is 0. This goes to 1 as well. And then this one here, if it's a 0, this becomes, well, this whole setup, yeah, that just becomes 0. So this is gone. So this equals to 1 divided by 2n times n factorial times by d and nth derivative. This is of t n, then t squared minus 1 n. And this equals to p n of t. Basically, we don't need to do 0. Yeah, this is equals to that. So fascinating stuff. There's the ordinary Legendre equation, and the other one has the m term. All right, yeah, so we got this now. Now let's go further and look at for m is less than 0. The definition is, and if you look at it, it looks more complicated, but it's actually pretty much the same thing as this one here. So this is the real one for m is less than 0. We have, basically, it's exactly the same thing, but we have these absolute value signs right here. But this one here, absolute value of m, well, when m is positive, it's just the same thing. So these are pretty much the same thing here. Only thing difference is this m is going to be, well, negative now, and it's a +1. There's an I term. And that's interesting. And again, there's a negative. This is also plus. This is a negative now. And this is because, yeah, to get rid of the negative side, we're going to have that sine term where it has, remember this one here, this one we had a cancellation. If you go back here, I'm just showing you, basically giving you a prelude of what's going to happen. This one we had a cancellation of the I terms, but now we're going to have them sum up, we'll add up to each other, and then we'll have a divided by I to cancel out. So these ones would be, the ones I think possibly canceling out. Anyways, yeah, these ones will be canceling out. The other ones will be adding, and then you're going to divide by this I term. So this gets rid of the complex setup, this one here. So anyways, I'm going to copy this. This is for this setup. Copy. Let's go all the way here. All right, so for m is less than 0, the definition is, and we'll put it like this. And I'll put a y. Yeah, this is a y. Put this pen, is it working again? Okay, there's a y. All right, I think pen should be working now. Okay, so y, n, m, real. I'll put it like that, equals to this. And yeah, it's again, it's a function of theta and phi, but that's a given. This is going to be for, this is just going to be m is greater than, less than 0. So what I'll do now, instead of dealing with these absolute value terms, what I'll do is I'm going to let k equals to the absolute value of m. And then what this means is, well, k is going to be greater than 0. So if it's absolute value and m is negative, it's not equal to 0. So it's going to be, well, greater than 0. So m is going to equal to, well, negative k. So m is just negative k, and that is just straightforward, and that's because because k is positive, an absolute value of m, and then m is always going to be negative, so it has to be negative k. So that equals negative k. So then what we get is a y n, and then m is going to be, well, negative k now. So just put that there instead of instead of m there is going to be negative k. And now this is going to be, all right, type real there. This equals 2. Next one's going to be -1, and then m is going to be negative k plus 1. And again, we're doing this just to get rid of this absolute value sign there. It'll make it easier to look at. And then this I then times square root 2. And then times it by, now y and m, well, what is that? We know, I mean, it was ready before we even solve it. Y and k now, absolute value of m is just k, like that. All right, and then we're going to subtract it by -1 to the power of k, times it by yn negative k, like that. And we know what k is right here. And again, this is, this is dealing with k, is greater than 0 now. Yeah. So we could write it like that, just for completeness. So now we go take a look at our k setup. I mean, this part here, y and k, we already know what it's proportional to, as when we went over before we started solving these. So basically, y and m is going to be, well, this setup, and y and negative m is going to be the same thing, -1 power of m times pn is associated with Legendre function with cosine theta. But then now there's an eim phi. The other one's im. The other one's an negative im phi. And the same thing, there's a -1 power of m. All right, so let's take a look at what happens now. So this is going to be equal to, yeah, this whole, this setup is going to be equal to, again, this is the definition there. And it's a proportional. So this is proportional, it's not an equal to. That's because we're just ignoring the normalization constants. So now it's going to be equal to, approximately equal to, proportional to. So basically a difference by a factor. So this is k plus 1 divided by I square root 2 times it by, and then y and k is just going to be, well, p n, and m is going to be k now, cosine theta. And then we have to multiply by the exponential, and it's going to be, well, the m is going to be k now, k phi. And then we have to subtract, now this part here is going to be -1k. And now for the complex conjugate of it, or setup, is going to be now another one. We're going to multiply by again, so -1 power of k. Again, that's why we have this -1 power of k. I can cancel stuff out. And then this is going to be now yn power of negative k. That's going to be same thing, proportional to p and k of cosine theta, and then e to the power of negative I k phi, like that. All right, so that's what we have. And here, just quickly shrunk it over, move it over here. I'm going to write here as a y n negative k, and then real. All right, it's proportional to all this. Now we're going to take out the like terms. But before we do that, we have this part right here, as always, is going to equal to, this part right here is going to equal to -1 power of 2k. And then that's just an even number, so this equals to 1, and that's because this is even. Just for completeness, write it down as well. I'll write this e better. Even, right? All right, so we have that, and now we're going to factor out this p and k cosine theta out of there. And this is going to be, well, let's factor this whole thing out. I'm going to keep writing this. It's not needed because, again, it's just a proportional, this is another constant, but then we do need the I, though. The I is going to cancel stuff out. So that's going to be like that. And then p and k cosine theta. So now we're going to be left with a e to the I k phi minus now e to the negative I k phi. All right, so we have this, and now this is just, again, Euler's formula. So this equals to, this is pretty much the same thing we did before when for m is greater than 0, we went over here. So we had eim phi equals to, well, cosine m phi plus I sine m phi. But now instead of the plus here, we have a subtraction. So now we have a subtraction there, and there's the complex conjugate one. It was just going to be cosine minus there. So we are going to have to subtract it. And again, this stems from here. The EI phi has this version of Euler's identity or formula. This one is the plus one. If you put positive one, it looks like this: cosine phi plus I sine phi. This one's going to be minus. So yes, fascinating stuff. This one is we're going to do both of these, and then but now we have a plus instead of a minus. So again, that's the only difference between this one's a plus, pretty much only difference, and then the other one's a minus. Yeah, it's pretty much one of the only differences. So now we're gonna get a, make some space. This equals to, at the top part here, cosine k now, phi plus I sine k phi minus, now we're gonna have to minus this side, and it's gonna be, well, minus and then another minus there. So we're gonna do I'll do a bracket like this. Cosine k phi minus I sine k phi, like that. All right, here I just moved it over there. So in other words, this is going to be, well, minus, this will cancel. Now we have I sine k phi minus negative I sine k phi. So in other words, those are going to add up. So we're going to get equals to 2 k sine phi. Yeah, 2i. There's an I there as well. 2i sine, put a bracket like that, chi phi, like that, k phi. So put this all together. This is going to be, well, proportional to, this setup is going to be proportional to I negative 1 power of k plus 1. And now we have, again, the same thing. We have a 2 there. So I'm going to put a 2. Actually, yeah, I'll put a 2 here. Yeah, put like that, 2 over square root 2. And then times by 1 over I. Move this over, move this one over to the other side, so we can have it similar to this setup there. There's an I there. Yeah, I'll move the I out. Yeah, so we're gonna have a 2i. It's 2i, like that. Yeah, so those cancel, and then there's gonna be p and k, and then of cosine, like that. And this one here is again, this part here just equals to square root 2. This one here cancels. This equals to 1. Again, the square root 2 is the same exact setup we did above here when we did at the beginning. That's this one right here. Yes, square root 2. Yeah, this one 2 over square root 2 is equals to, well, just subtraction. So it's just 1 minus 1/2. That's just going to be, 1 minus 1/2 is going to be this square root 2. And now we have the I divided by I is cancels. And all this together, this part here, I'll put it over here. This equals to negative 1. Actually, I'll move it down. This equals to negative 1. And this, since this equal, okay, this equal sign is over to here. Is proportional to, but then the thing is, this, we already had a proportional there, so this could be an equal sign, because this term equals to this one equals to this, just to make it more rigid. So now we're gonna go negative k plus 1 times it by square root 2, and then I is gone, and then also we have this part right here, sine k phi, like that. And this is going to be p n k cosine theta sine k phi. So and then this is just a constant, so we could put those inside the proportionality constant. Proportionality equation equals constant. So thus y, and then this is going to be n negative k. Yeah, so y, like here, yeah, write this down, n negative k real, yeah, is proportional to, this is going to be a constant, so to get rid of all that, p n k, write this n a bit better, this one here. All right, yeah, write that n better. This is going to be p n k cosine phi theta times by sine k phi, and this, yeah, this negative k, that's just m. Yeah, so m is negative k. So we'll just circle this. This is and we don't need to do. There's no other k anywhere. Yes, that's it. Or actually, instead of boxing, I'm going to keep this negative k. We do have a k there. We have a p n k, so we have to leave it there. So this is going to be p, negative k, like that. So in other words, thus y n, then replace negative k with m. So negative k is m, and this k is this absolute value of m. So it's going to be m real is proportional to p n of absolute value of m. cosine theta sine multiplied by. Okay, my OneNote wasn't working, so I just paused the video and just added this in right here. So we have the sine, and then of absolute value of m, so the k becomes this, and then there's the phi, and then this is all for m is less than 0, and just box this whole thing in there. All right, now that we have all this, so thus, putting it all together, we obtain the real spherical harmonics in proportional form, basically excluding the normalization constant. So we're going to have a y n like this, and then a real, so the real spherical harmonics are going to be, and its function of theta and phi, but for completeness, is proportional to, now we're going to have a giant equation like this. And let's go start from the beginning. So we have the very first one for basically for m is greater than 0. We have this y n m real is going to be, well, proportional to pm cosine theta and then cosine m phi. So it's going to be proportional to cosine. It's going to be p n m cosine theta. Cosine theta like that. And then this is going to be cosine m. Cosine m phi like that, and this is for m is greater than 0. All right, that's m is greater than 0, and then for m is equal to 0, we have this right here. So m is greater than 0. We just have pn 0 cosine theta there. So that's just it. So let's put it like this. This is pn 0 of cosine theta like that. And this is m is equal to 0. And then lastly, this one is just this part right here. This one we just solved. So pn absolute value of m, and then this is going to be cosine theta sine absolute value of m phi like that. This is going to be m is less than 0. Notice that all these ones are all similar. This one is just cosine. The difference is cosine m phi, and this is going to be sine m phi. But again, these are positive values, and yeah, these are both going to be positive m there. This is going to be, if it's less than 0, we take the absolute value of it. And it's proportional to the absolute value signs of it. And also, you could also write this as, you could write this, basically, I'll write this, you could write y n m real. And this is to make it even simpler, or just more compact, theta and phi. Basically, this is going to be proportional to, like this, where we could take out these factors, p and m of cosine theta, as well as this one here. And that's when, well, when m is 0, that just fits it anyways. So these ones are the same. Like these aren't affected by what the m value is. Like it's not nothing special. So it's going to be p, and what I mean is you don't have this random sign and so on. So we just take these out. So we're going to take them out, but we'll actually, this is actually, if you look at it, this is actually the same thing as writing absolute value sign m. Yeah, because m is positive there. And then absolute, if you put an absolute value sign here, 0 still is the same thing. So we could just take it out as take out the absolute value of m there. So it's the same thing. You could put them in there or not. And then, so we could take out the absolute value sign and then write cosine. This is of cosine theta. And now this is going to be now the only thing that's going to be changing is if we'll have right here, this is going to be cosine m phi if m is greater than 0. But if m is less than 0, we're going to have a sine absolute value of m phi, like that. So that's the only difference. Yeah, and again, when m is 0, well, these all just vanish. Well, actually, this should be, I would say this should be m is greater than, I would assume that shouldn't this be m is greater than or equal to 0, just because you'll have now when m is 0, it's still positive, and then this just goes to cosine is going to be 1. And then, yeah, and this one here is going to be 0, so I think it should be like that. And actually, you could write it like this, but I think the Grok AI just puts it without that, just so that if m is greater than 0, just add this term, just so it doesn't look too messy. And if m is negative, add this term. If m is not there, you just ignore it. If m is equals 0, I mean m equals 0, so ignore it. But it's the same thing as if you put it in the first one. Because again, remember, this one here is just the same thing as pn 0, but it's the same thing as y and 0. So we already got rid of the cosine terms and so on. Let's put this here. Is already equal to y and 0. And again, those ones have the cosine. Those vanish. But anyways, I was really like this just because the book or the Grok AI answer that. Put it like, I'm going to put it like this or this and then box this in. Or we don't have to box anything. Just leave it. Actually, I do want to box this one. This one looks nicer. Like that. So there it is. Alright, and now we're finally on to the last part of the video, and that's basically graphing these real spherical harmonics in Desmos calculator. So here is an amazing real spherical harmonics graph in Desmos calculator that someone made. This is absolutely astonishing. Whoever made this, congrats and thank you. So first of all, if you go here, if you click it, what you'll end up going to is just this part right here. So here it is, and here's some. It's a bit like laggy on my computer here, my laptop thingy, my Surface Pro. So here there's a bunch of the equations and so on. So there it is for some values on it. So but anyway, so note the normalization constants used as well as the same formulas we obtained above. So if you go to it, it shows you this setup here, which is quite fascinating. But this is. So this is they call this the real part, the y real, and that's just basically when m is greater than 0. So we have the cosine m phi, and this is the associated Legendre function p m absolute value m cosine theta, and it's exactly the same setup there. So they have two functions there. This is the cosine one, they call it the real. This is the imaginary one, im. There, and there's the p, there's the m. This one, remember it's l, but we used l, n. And there's cosine and so on to some other stuff. But again, here's the normalization constants. Those are the n. So that's the n one they use. So again, that's why we used proportional there. So it's again the exact same thing. They have the absolute values. They call this m var. We'll explain that in a bit. So they have that m var. So note the associated Legendre polynomials and its giant derivative. So here it is. So this is the associated Legendre. There's the ml, but ours is n, and so on. There's the -1 power of m, and so on. 1 minus x squared, and so on. And then this is, and now it's a they made it as a function of the ordinary Legendre polynomials, and then from here. Yeah, so from here, this one, what they do now is they take the derivative. Yes, they put it in here. So remember that giant derivative there, and it's they just basically take the derivative of it. So and the derivative of the nth Legendre polynomial. So that's quite absolutely amazing stuff there. And they say d is, that's the variable. So basically, whatever the m value you use in here, it gets thrown into here, and then that gets into this function, which is represented by d. And so that's how it looks like. And if you this is 1 divided by n. Well, we have 2 to the power of n. This is just 1 to the n. And let's just have a look at that Legendre general polynomial, the ordinary one. So we scroll all the way back up. This was the setup here. Scroll all the way back up just to see our final solution there. So there's a Pn, yes, so the Pn of t is 1 divided by 2n, there's a factorial, and then there's nth derivative of this. But then this one's going to be, that's Pn, and then we do the mth derivative of it, and so on, yes, of Pn there. So it's pretty fascinating. Put them all together, it's going to be nth plus mth derivative, and so on. So that's quite fascinating. Yeah, so go back here. So anyways, yeah, so this is the dth derivative. That's the mth derivative after you already take the lth Legendre polynomial, and in other words, the lth derivative, because that's why you had the n plus m derivative. Yeah, so that's and it gets something like this giant thingy. Then, anyways, let's to solve it. Maybe for a future video, I'll go explain how exactly they do it. But anyways, since the spherical harmonics are graphed on the sphere, the radial distance needs to be stretched proportional to the magnitude of its value on the sphere. This gives it distinctive lobes. So what they do is, now they're graphing out the r terms, and they're using some of these values there, so r sine and so on. So they're getting the radial terms, but then they have this setup here, which is using, now it's using the ML variables, the actual ones, instead of this M var. So they're using this M var, and they're basically using it as like the maximum of the. So it's using, so if M is greater than or equal to 0, it's going to be plugging in the value of M inside this function right here. Yeah, inside this one here, y real and y imaginary. I'm not going to explain exactly what they're doing, but basically they're throwing these M and N and L, which is our N, inside there, and the theta and so on, and then that function is using it in here. So, and they call this they call these ones here the imaginary. They use M var just because it's like a temporary one. So this is a temporary one that you throw in this one, which is actually being graphed, which is the length of it. And because you see this R max equals the maximum of one of these setups there. So this is basically the maximum lobe and so on, and some other stuff like that. But anyways, the whole idea is they throw it into this setup here. So that gets thrown into this equation and this equation. So it's fascinating stuff. So keep going further, see what else they do. And now we have some basic stuff here. So now we have the quantum principal quantum number and orbital angular momentum quantum number. This is the one we were dealing with. So we were dealing with this right here, L, and yeah, we were dealing with this one here. This is our L. That's actually just our N. So we were dealing with L and M. But these ones in quantum mechanics, they're called the setup here. So I'm going to read this all out, then I'll explain. So note the relationship between the principal orbital angular momentum and magnetic quantum number. So there's a principal quantum number n. So note the relationships between them, and the principal sets the maximum orbital angular momentum, which then sets positive and negative limits of the magnetic. So in other words, this principle is the n used in quantum mechanics, and then this sets the maximum. So this sets the maximum orbital angular momentum. This is the one we were dealing with. That's why we didn't deal with this one. This is just basically the maximum. So where this one is between 0 and n. That's pretty much, I think that's the only place in the whole formula, the whole calculator, that has it. So this one is just the maximum there. So that's pretty much sets the energy level. The maximum is sets the maximum value of n, and then the magnetic quantum number basically is this one sets the limits, positive and negative. There's a negative L, negative positive n. In other words, n and negative n. Yeah, and then this one here is a maximum. This was using our setup. Yeah, this is the L. Again, that's why I don't like using the L. It looks like a 1 or something. They use it like that, and this is negative L. I'll say negative L, positive L. And then where this one here is the maximum is n. Yeah, so then these have maximums of negative and positive n. Now here's some values here. So if you have n equals to 5, L equals to 5, M is 0, you get this setup here. That's the default one, which is quite fascinating. And then also here, for going further, so here are the real spherical harmonics for various values of the quantum numbers. So if you put n is 0, and then L automatically becomes 0, these all become 0. If this n is 0, we just get a sphere. And they all have the exact same values. If n is 1 and L is maximum, make it 1. Otherwise, if you set this as 0, it will just be the same thing as this one. And then you get M is 0, you get this. If you make it the same thing, but M is 1, it rotates. M is 2, it gets it on this y-axis. But then interestingly, if you make n is 2, and then this one's L is 2, you get this setup. But then if you, and then where M is 0, but if you have M is 1, it turns like this. M is 2, it still rotates, and so on. So that's pretty interesting. Then so when it's 0, it acts differently than when it's not 0. So that's 0. This is M is 2. So it's not just a simple rotation as in this one here. So that's pretty fast. And let's go back into the graph and see what we can come across. So again, here's the principal quantum number. Let's change it to, but anyways, before that, again, you can click the spherical harmonics. You can see a whole lot of stuff they're doing. But the general stuff is again, this is what I want to get to, and then everything else is just extra. This is the real one. This is the Y, and this is the this is the M is greater than 0. M is less than 0. And they call that imaginary. But it's the same thing. There's a sine and there's absolute value one. So that's the real ones we set up. And there's the associated Legendre polynomials, and then d derivative of the Lth Legendre polynomial. It's fascinating stuff here. And again, a whole bunch of other stuff. But I will close this. And then you can also toggle access here and on. This is pretty cool. So you can change that. Anyways, so I'm going to make this like this. I'm going to go to n is equal to 0. So let's see what happens. N is 0, L and M become 0. And then if you make this as 1, again, that's pretty much, I think that's the only place where it's dependent, just this one here. So, but if it's still 0, it's still 0, so you would make it n is 1. And then this one you could modify it, and so on. And then you notice it takes a while to load, because there's a lot of other stuff in there. And I think if I go to Spherical Harmonics, this one has like a 684 element list. So it's like literally taking solutions at each different degree or something. And that's amazing stuff here. So you can click this and see elements. Holy. Okay, so let's close this now. We'll see even more. So that's pretty fascinating. Let's just close that. So I don't know how. Okay, that's how you close it. Let's go back into here. And I'm going to make this into 2. Yeah, so notice what happens if you do 2. Becomes, this is the one we just showed. And then if you, this is at m equals 1, m equals to 0. And again, notice it's all integers. It becomes like that. And then you go to, let's do a giant one, see what happens. Oops, slide this here. Okay, so that's 2. Let's go to 10. So now we're going to go into another level, 10. So that just sets the maximum you could do on the n. So there it is. And that becomes like a butterfly. Let's go to the 0. Holy, yeah, okay, this is taking a lot of time to render. And it might blow up my computer. So there it is. That's how it looks like there. Okay, so it's always that weird shape like that. And then let's go here. Okay, let's do this one, and I want to take a screenshot, maybe. Oh, it's going back. It's just taking a while. Yeah, so that's 10. That's pretty ridiculous. Anyways, I'm going to make it like this. Yeah, that's pretty cool. So that's a bunch of stuff there. But you could also change the graph options. You can do lines, do less lines. And it's taken a while to load. You can change the width. Yeah, so it's, notice less lines, looks like that. Go to 77 or whatever. Okay, so there it is. And opacity, make this 100. All the lines, no opacity. It looks like that. Okay, now that's the opacity, so you can't see through it. Let's make it a bit less. All right, let's see what happens here. It's still taking a while to load. This is pretty ridiculous. Okay, I think it's done it. Let's go back here. And I want to take a screenshot. Go back up to here, principal quantum numbers. And yeah, that's what it looks like. And I will do it. Make this closer. Can it go over there? Okay, it's good enough. And I'll take a screenshot and add it. Alrighty, so I'm going to add this to it. So that's basically putting a whole bunch of stuff together and see what happens. Yeah, so that is that. And now there is the maximum quantum number. Alright. So yes, absolutely fascinating stuff. And then yeah, I'm done. I'm done with this video for a while. Alrighty, finally took me a long time to get this. Mainly because I was keep getting distracted. People distracted me and so on. But also wrapping my head around this. Every time I go find something, I'm like, oh, I think I get it. And all of a sudden, there's a random associated Legendre polynomials everywhere. I'm like, what the okay? I'll just say that for another day. Anyways, that's all for today, guys. Hopefully you enjoyed from this epic, long, giant video, and I'll be uploading the sections of this video, and yeah, as well as putting all the notes in a high blockchain and in PDF format. I will erase this, and yeah, hopefully I don't make any other mistakes. Anyways, let's just scroll all the way back up, and yeah, thanks for watching, and hopefully followed along, and finally have some grasp of spherical harmonics, which is quite ridiculous. It's pretty amazing. And again, a lot of stuff deals with this. Again, it's all because of the spherical nature of like reality. And yeah, so that's that. And yeah, so magnetic field and atomic orbitals and so on. And then dealing with this super complicated setup there. And then yeah, I'll definitely be doing videos on the associated Legendre and normal Legendre polynomials and so on. And also quantum mechanics and so on. But now I have an actual decent grasp on spherical harmonics. Anyways, guys, that is all for today. And yeah, thanks for watching. Scroll all the way back up. It's a pretty giant video. Anyways, thanks for watching, and yeah, and again, the reason I'm doing this, one of the main reasons is because of Einstein-Dino's ether theory, which I think it's the real deal. Anyways, that's all for today, guys. Thanks for watching, and stay tuned for another math easy solution.